this COVID.
Oh, is it?
Yeah. So I lost around like 7-8 kgs when I had it actually.
Oh my God.
Yeah.
I was not aware of this one. Okay. So only you, right?
No, the whole family. But anyway, I suffered a bit actually compared to them.
Others. Okay.
Yeah.
When did you have it?
Like, yeah, Francois.
When did you have the COVID? Like many months ago? Or?
Yeah, so I had it during May, June.
May, June.
Yeah. When the second wave was going on in India. Yeah, that time. Yeah.
Mm-hmm.
Yeah. So.
And you have kept the weight off?
Yeah.
That's good. Sometimes it's good.
Yeah, but like that in my case, like maybe like I means like the fever was for continuous 14 days actually. That was the problem.
14 days. Wow.
Yeah.
I'm sorry.
Yeah.
Very Sundar.
Hey, how are you?
Hi, very well. How are you?
Still awake in the middle of the night?
Yeah, I took a nap actually after dinner.
What's the time now? 10 o'clock?
It's 9 p.m., but I got up at 4 a.m. this morning. My son is sick. He had fever last night. He was coughing all night.
Oh, okay.
So we took him to the doctor. He does not have COVID, but he's very snotty.
So glad that
he's 7 years old.
Nice.
Yeah.
Hey, Nagendran.
Hi, Sundar. Good morning.
Good morning.
Yeah, good morning. Yeah.
So I'll be in touch with you after this conference.
Yeah, sure. Yeah, because sorry, I was not able to write yesterday. I thought like I'll write it today, but anyway, we can fix it actually. Yeah.
Sure.
Yeah, Sundar. Thanks. Yeah. Yeah, and congrats. I saw your talk on the day before yesterday, and that planar B6, the first isolation.
Yeah, that's very exciting. Yeah, let's see how JEMIS comes into.
Yeah. I think surely a good result. Congrats. Yeah.
Professor Kawai, how are you?
Oh, hi. Kanasan, how are you?
Thank you. I'm okay.
You are good?
I'm good. Thank you.
Thanks for showing up.
Yes. Yeah. Okay. Good to see you.
That's good to see. I'm not seeing you, but it's good to hear you.
Yes. I'm going to connect it. My video, whether it's working or not.
Money, you can open a video.
It's working. Yes.
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 Hi, good to see
How
you.
are you?
Very well.
Yes.
You haven't changed.
After a long time, I'm seeing you.
That's right.
Yeah. Sorry.
No, it's good to see you. Yeah, you haven't changed at all. You haven't lost your hair like me. That's good.
Okay. See you. Yeah. See you. Bye.
Hey, Ganeshan.
Hi. How are you?
Good.
Good.
Are you having a break also? End of the year break soon? Are you going on the? Do you have holidays coming up or not?
Almost there. So 2 minutes we'll start.
Okay.
No. Yeah.
You want me to take the screen?
Oh, Francois, what did you ask? Holidays coming up.
Yeah, that's what I was asking. Yeah.
Yeah, we missed, I think. Yeah, so because like Christmas holidays will be, of course, there, but it's not that lengthy as in USA actually.
As in America, yeah.
Yeah.
Right?
Yeah.
Mm-hmm.
So of course we have holiday on 25th.
Mm-hmm.
Yeah,
Okay.
but it cannot be like holiday for a fortnight or something like that as you have it over there. Yeah. But The celebrations have started already in USA for the Christmas, as in Germany.
Yeah, we did. I mean, we had a big work party without any mask, like 100 people in one room, and
Oh.
everybody's okay for Texas is okay for now. It's not too bad. It's gonna get bad again, but it's okay.
Okay. Okay.
We are going to restaurants. I'm taking like speakers out to restaurants,
Okay. Oh,
but
that's
I
good.
think after Christmas, it's probably gonna have to come down again.
Okay.
Yeah.
Okay. That means almost you are back to the normal business.
Hi, Frida.
Yeah, I mean, yeah, Texas is almost normal. Even if people are sick, it doesn't really matter. We have a crazy governor.
Okay.
Hi, Frida.
Hey, how's it going?
Hey,
Yeah,
Frida,
good.
how are
First
you?
one.
Good to see you again.
Good to see you again.
Yeah,
And I
Frida
see
was in
Jan is
Texas
already
not very
there
long
too.
ago.
Hey, Jan.
Huh?
Hey,
say?
Federer, how are you?
Good evening.
Hey.
Good to see you.
Hi, Sundar. How are you?
Good.
Hello,
I can
Dr.
see
Yan.
all the early risers. For you guys, it's very early in the morning, right?
Yeah, it's a bit early.
I mean, I remember Krishnan when you back in the day, you know, he wouldn't show up till 11 in the morning.
Yeah, you're right.
Krishna, and all of your secrets are coming.
I mean, but Frida, it's unusual of Krishnan, because like when he was doing PhD, he used to be the first one to come to the lab.
Oh yeah.
Yeah. I think maybe
He's joking.
once he came to USA, I think he became relaxed.
No, he's
No. The first one could still be 11, could still be the first one, right? I just remember all my Indian students always like to, you know, work late.
Yeah.
Yeah.
This is a very typical culture of all IITs. No, they work very late.
It is, right? Yeah.
Yeah.
Yang, how are you?
Krishna, did you have your coffee yet?
No, no Jerry's coffee. Okay.
No, Jerry's coffee.
Okay, so I think it's the time. So we'll start. So far we had two excellent days, and the conference went very nicely so far. And the third day also, it's going to be a very excellent session. And the first session will be chaired by Professor S. Nagendran from IIT Delhi. Nagendran, please.
Yeah, thanks, Krishnan. Good morning. I welcome you all to session 9 of MMM2. We have 3 talks by eminent speakers in this session. The first speaker is Professor Francois Gaboy, who will be delivering a plenary lecture. Though Francois does not need an introduction, I will briefly say a few words. He obtained his PhD in 1994 from the University of Texas at Austin by working with Professor Alan Cowley. Through AVH and Marie Curie fellowships, Francois worked as a postdoctoral fellow and habilitant in Germany till 1998. Currently, he is a distinguished professor at Texas A&M University, where he is holding the Arthur E. Martel Chair of Chemistry. Francois has won various awards. A few to mention are F. Albert Cotton Award in Synthetic Inorganic Chemistry in 2016 and Distinguished Achievement Research Award in 2019. He has been an associate editor for the RSC flagship journal Chemical Science since 2019, and his current research interest includes main group based Lewis acids and exploiting the non-innocence of antimony ligands. Without further delay, I now invite Francois to deliver his plenary talk on main group Lewis acids for applications in anion transport and catalysis. Francois, please.
All right, thank you so much. Can you see my screen? Thank you so
Yeah,
much,
I can
Matt,
see
for this
your,
kind words. We
yeah,
all good?
yeah, it's perfectly fine. Please go ahead.
Okay. So thank you so much, yeah, for hosting me. So thank you, Krishnan, for putting together these conferences. Thank you also to the rest of the organizing committee. It's a true honor to be able to speak in this conference. So today I will tell you about some of our work on Lewis acids with some particular application in the area of anion transport and also catalysis. As many of you may know, we have been very interested in the chemistry of Lewis acid since the beginning of my career, independent career, almost 25 years ago now. And I tend to always start my slides or my talks by reviewing some very basic concepts, such as, for example, the addition of a fluoride anion to BF3, which leads to the formation of tetrafluoroborate. And this reaction releases 338 kilojoules per mole. And that's a considerable amount of energy, which speaks to the high fluoridophilicity of boron. If we travel a bit further into the main group elements, we'll meet antimony, and in particular antimony 5, which we will find as a fluoride anion affinity, which exceeds that of BF3 by about 150 kilojoules per mole, so at 489 kilojoules per mole. And we found that very inspiring a few years ago. In particular, of course, we became aware of it was difficult to miss the prevalent role that this tris-nitrophenylborane plays in the chemistry of main group Lewis acids. This is a molecule that has been used extensively for the activation of olefins, for the activation of small molecules such as H2 or carbon dioxide, for example, in FLP chemistry. So we were very interested in testing whether we could also introduce an analogous series of compounds in which we would look at organo-antimony compounds whose reactivity would be tamed by the introduction of aryl substituents, but which will still display considerable Lewis acidity. And this is something that we started now almost 10 years ago. So really our efforts was to develop a chemistry that was parallel to that of boron based on antimony. And I'm going to carry on with this analogy a bit further. So again, I'm going to come back here to the fact that tris-nitrophenylborane is used as an activator of catalyst for the polymerization of olefins. It's also used in FLP chemistry as per the work of Warren Peers and Doug Stephan. And so we are very interested in seeing whether we could actually make an antimony analog of such derivatives. And so a simple approach is the following. We took tris-nitrophenylstibine and decided to try to see if we could actually oxidize this compound to the +5 state. And we found that this reaction was actually pretty facile. We could pretty quickly actually oxidize this molecule. We see the cycloaddition here of this autoquinone to form this tetrachlorocatecholate derivative. And this compound is bench stable, and it's actually quite Lewis acidic already. If we look at the crystal structure, we see that an autofluorine actually approaches the antimony center here to form a short contact, and that speaks to the high acidity of this molecule. And sure enough, we can let this molecule react with a phosphine oxide, such as triethyl phosphine oxide, to form the corresponding adduct, which can also be characterized by X-ray crystallography. And we have published a couple of papers on this molecule. This molecule is also a very potent main group catalyst. If we try to estimate the strength of this acid based on the chemical shift of the phosphorus atom in this phosphine oxide adduct, which is essentially a Guttman-Beckett test, we'll see that this acidity approaches that of the borane, since the chemical shift are very, very comparable. So this is a very potent Lewis acid. Something that we have done also was to try to look at the influence of the charge on the Lewis acidity of these compounds. And here we went simply toward stibonium cations, such as this tetraphenyl stibonium cation that we have here. We have one with the antral group over here, and one here with a perylene group. These two groups will serve as chromophore. And what we discovered quite surprisingly, that these molecules are able to capture fluoride in water at ppm concentration. Moreover, something that we did not expect, but which was a pleasant surprise, was the fact that the fluorescence of the antral chromophore turns on as the anion is bound to the antimony center. So these are great sensors for fluoride. They can be deployed in tap water or in bottled water very easily to determine very accurately sub-ppm concentration of the fluoride anion. Going back in time, we have also looked at the effect of charge on the Lewis acidity of boron compound, and this was our earlier work prior to us developing an interest in the chemistry of antimony. So many years ago, inspired by the work in particular of Shige Yamaguchi, now in Nagoya, we looked at taking organoborons in water, and we discovered that by simply appending a cationic functionality at the periphery of a borane, allowed us to do that. We increased the water solubility, but in addition, because of favorable Coulombic effects, we also boosted the anion affinity of these compounds, and we're able to discover compounds that actually capture fluoride again at ppm concentration, as demonstrated here in this paper from many years ago. And so, having done this work on anion sensors, we became interested in the possibility of using the same sort of molecules for the transport of anions. Why would we want to do that? Well, I'm not exactly an expert in the area of biology, but we all know that cation and anion concentrations are very important to the health of our cells. So we have a very precise homeostasis in our cells, in particular of chloride concentration. And typically, the transport of these anions or cations is carried out by membrane protein, which will serve as channels. This is a zoom here on one of these channels. This is a CFTR conductance regulator. It's a protein that will transport chloride. And when defective, this will lead to the appearance of diseases such as cystic fibrosis. And so, which is a very serious disease, right? It can be fatal. So given the seriousness of these diseases, the organic community has tried to develop organic molecules that will transport anions in a similar way as those channel proteins would do. And so there is an entire field of beautiful chemistry, which is mostly based on organic scaffold of artificial transporters. These artificial transporters are typically designed such that they will possess a couple of hydrogen bond donor groups which can interact with the anion via hydrogen bonds. Another characteristic of this transporter will be the appendage of long chains or fluorinated group, which will render the molecule quite lipophilic and allow this molecule to partition in the lipophilic part of the membrane. So remember that membrane are phospholipid bilayers. We have two little tails and the polar head over here. So these molecules, because of their affinity, because of their lipophilicity, will partition into those membranes. However, they'll be able to diffuse on one side of the membrane to capture an anion. Once the capture is carried out, then the complex can diffuse, and the anion can be transported on the other side. So this is passive transport, but that's a form of transport that is attracting a lot of interest anyway. So here we are looking not at a channel, but rather as a carrier type transporter. What about main group elements? If a compound that a hydrogen bond with an anion can do this type of transport, we should in principle be able to duplicate this behavior using simply Lewis acidic main group compounds. And when we looked at this field, there was some foundational work by Stéphane Mathilde in Geneva, who used halogen bond donor or chalcogen bond donor as anion transporter. These were pretty much the two types of systems that had been looked at. This system would interact with the anion via an electrostatic interaction, which will be based on the presence of this sigma hole here, which is an area on the potential energy or the potential electrostatic surface of the molecule, which is depleted in density. And there is also we will also see low-lying sigma star orbitals, which are aligned with the sigma holes, which can accept density from the base, from the anion. And that was it when we published our first paper in 2019. But sure enough, as our paper was in review, Stéphane Mathilde cranked out a paper showing that Lewis acidic stibines and telluride can also do this kind of transport. Something else also that prompted our interest in this chemistry is the prevalent role of phosphonium cations in targeting the mitochondria. Phosphonium, in particular triaryl alkyl phosphoniums, have a very lipophilic exterior. They are able to partition in the lipophilic part of the membrane. And because the cells of animal cells tend to have, or they all have a negative electric field gradient, those phosphonium will be attracted inside the cytoplasm. This electric field is actually accentuated when we go into the mitochondria, and so we see this phosphonium as being very good targeting agent for the mitochondria. And something else again, which got even closer to our work, was a paper in a Nature protocol in which the simple boronic acid phosphonium conjugate here was used to measure hydrogen peroxide concentration in the mitochondria. So how does this work? This phosphonium takes this boronic acid into the mitochondria. In the mitochondria, where we have a high concentration of hydrogen peroxide, we'll see oxidative cleavage of the BC bond. And then this poor animal is digested What they end up doing is just a mass spec analysis in which they measure the ratio of the boronic acid to the corresponding phenol. And based on that, they're able to backtrack the hydrogen peroxide concentration in these systems. So obviously, if we look at the structure, they are very reminiscent of the type of system that we had looked at many years ago, which I've already presented. So this is just a repetition of the slide here. So if we look at the molecules that we made several years ago, we do have a phosphonium, which would be a very good cell-penetrating head group, or a head group which will partition us into the lipophilic part of the membrane. And sure enough, we have an anion docking unit here, which will allow us to bind anions. So the hypothesis that we made with Jane, one of my students, was that these molecules could be very well adapted also to the transport of fluoride across phospholipid bilayers. And so Jane went into the lab. She went to make these molecules, which was introduced, I think, by Todd Marder in 1993, this phosphinoborane here shown at the top. And just some of the lights here. And yeah, so we can make this molecule. It's a molecule that we have used extensively in my group for many years. And we can simply alkylate it at phosphorus using any type of alkyl groups. And in this alkylation allows us to make these phosphonium derivatives. And you see that the repertoire of molecules that we have made can be differentiated by the length of the alkyl chain that we introduce on the phosphorus. And this, of course, will allow us to dictate the membrane insertion properties of this molecule. We can also play with aromatic groups, such as this phenol, naphthyl, and anthryl group here, which allow us also to introduce chromophores and also to allow us to ramp up the lipophilicity of the systems. And yeah, several of these compounds have been fully characterized, including by X-ray diffraction. So what about the transport experiment? So once we have made these compounds, we had to learn also how to measure transport. So one most convenient method to measure transport is based on the preparation of vesicles, which are spherical aggregate of about 200 nanometer in diameter, and which possess a bilayer as an external membrane. And we can package these vesicles with a cargo, such as KCl or KF. And then we can interrogate the efflux, that is the escape of the anion, upon addition of a transporter using an anion selective electrode, such as a chloride selective electrode or a fluoride selective electrode. And this is the structure of the phospholipid that we use to make this kind of vesicles. The assay is typically buffered at pH 7 or 7.2, which is quite important, actually, because of the role of hydroxide in this chemistry. And this is what we see. So we have a series here of compounds, which we have all tested. We see that they are lousy at transporting chloride. We see very little efflux, only 20%, and then it stops. We're not sure what's going on here. There seems to be a bit of maybe membrane destabilization and then essentially no transport. With fluoride, however, we see a very dynamic efflux, and we see very nice kinetic release here of the anion, in particular with a group of transporters. Something that we can tell also very quickly from an inspection of this data is the fact that all transporters are not equal. We have some that are pretty lousy, some that are intermediate, and some that are very good. So what's going on? Why don't they all function well, and which one are the best ones? We decided to think a little bit more about the behavior of these compounds in water. And we'll have to bear in mind that we are dealing with Lewis acids. And when we're in water, it is possible for the boron atom to be neutralized by a hydroxide anion to form this hydroxyborate derivative here. And the value of this equilibrium constant is going to tell us at what pH these molecules undergo that neutralization. And so the pKr plus that we can calculate will correspond to the pH at which 50% of this boron is in the hydroxy form. Yeah. And so what we see here is that some of these molecules have very acidic pKr pluses of 4.8, 4.66, and 4.3. And sure enough, if we look at which ones those are the most lipophilic one, or the most hydrophobic molecules. So why are they more acidic? Well, we think that we simply decrease the dielectric constant around the molecule because of their hydrophobicity, leading to an increase in all Coulombic attractions in between these cationic compounds and the anionic gas, the hydroxide or the fluoride. But here we are concerned with hydroxide. All of the other compounds have significantly higher pKr pluses, including this molecule here, which is going to be quite compatible with neutral pH, since it will be only 50% neutralized at pH 7.12. And if we look at the grouping of the data that we have, if we look at the initial efflux rate, their ability to transport, versus the pKa+, we see two groups. We see a group that displays excessive Lewis acidity, such as these compounds, and we believe that they are simply neutralized in water by hydroxide and unable to capture the anion and transport the anion. What we also see is that then we have a set of compounds with a very good compromise in between lipophilicity and Lewis acidity, and this ends up being the best transporters. So increasing the lipophilicity of these compounds is not necessarily beneficial in this context because of the interference caused by hydroxide anion binding. We were also very interested to look at the selectivity of the system. I've already explained that they do not transport chloride well. And in fact, when we did anion sensing, we didn't see chloride binding. I'm actually surprised to even see a little bit of chloride transport here. But we see a great deal of selectivity. If we look at the kinetic parameters, the initial rate of transport, we see an increase by almost 20-fold in favor of fluoride. So these molecules are extremely selective for the fluoride anion. In order to further confirm the role of the boron atom in these compounds, we have also bulked up the boron center by adding two orthomethyl groups. So all the molecules that were met before are two mesethyl group and a phenyl group over here, a phenylene linker. So now we are bulking up this boron center. What is known about this is that we are going to completely block the boron center. And sure enough, when we block up the boron center, we see a complete quenching of the transport activities. So we see a very clear difference, and this allows us to confirm the role played by boron as the anion docking site for these transporters. What about stibonium cations? If we look back at the early literature on the behavior of stibonium in aqueous phases, we see some very interesting paper. In particular, we see papers in which the tetrophenyl stibonium cation has been used to extract fluoride from water. So this is a very crude anion transport experiment in which fluoride is transported from water into a carbon tetrachloride phase. And by the way, if you try to do the same thing with the phosphonium or the arsenium analog, no transport takes place. So stiboniums are much more acidic than their phosphonium and arsenium counterparts. In fact, this has even been used for the transport of F18 fluoride, which is radioactive, and it's a radionuclide used in positron emission tomography imaging. So we looked at a series of compounds, which again are going to differ by the lipophilicity of the structure. We have a phenyl group, a naphthyl group, an entriol, and a pyrene group over here. And when we look at the transport, this is what we observe. By the way, we also decided to introduce in this study, which is our first paper on this topic, a series of bismuthonium cations. And what we found is that the bismuthonium do transport, but they are not great. They are not great transporters. When we look at the stibonium cation, we see a much more rapid efflux. And in fact, if we correlate this to the Lewis acidity of the molecule, we see that the stibonium are more Lewis acidic than the bismuthonium. What we see again is that all transporters are not equal. In fact, here, what we see, the one at the top are the most hydrophobic one, the one with the entriol, or pyrene chromophore or substituent. The same is true for the bismuthonium cation. We see the positive influence of these hydrophobic groups here. We can also couple this. So what we see is that the stiboniums are much better than the bismuthonium. What we have looked at also is to couple the transport with valinomycin. I failed to mention the use of valinomycin in the slide describing this assay in the case of the boron derivative. Valinomycin is a cyclic peptide, which has a high affinity for potassium and which can help transport potassium outside of the vesicles. And so this allows us to conserve electron neutrality in the system. In the absence of valinomycin, we are fighting against the accumulation of positive charges in the center and thereby limiting transport. So in the presence of valinomycin, we see much more rapid efflux. But again, what we seem to clearly see is that the stibonium cations are better than the bismuthonium cations. But really, we don't see a big difference in between this pyrene or anthracene group here in terms of the transport activities. We submitted this paper without any biological studies, and the editor of Chem, Robbie Kling, said, I will publish it only if you do biology. So that's why it took us 9 months to finish this paper. So I have a friend on campus. His name is Jean-Philippe Paulois. He specializes in transport across the membrane of cells, and we decided to, using typically peptides, so we decided to launch a collaboration with him. And so in that study, we looked at stibonium and this stibonium and this bismuthenium transporter, and we decided to deploy them in red blood cells or erythrocyte, human erythrocyte. We're pretty excited to see that the bismuth cation was transporting, I guess, in artificial vesicles, because we thought that bismuth was going to be very innocuous to our cells or non-toxic, because we all know about things like Pepto-Bismol. However, when we added this bismuthenium transporter to our cells, what we saw was that within just a few minutes, we saw a lot of ghost cells indicating hemolysis, that is release of the hemoglobin from the red blood cells. After 7 minutes, there was no intact red blood cells left. Everything was completely hemolyzed. By contrast, if we did the same assay, just looking at the health of the cell with a stibonium cation, we saw no effect of the stibonium. The stibonium was perfectly fine. And moreover, after 25 minutes, we can also image using a DAPI filter. And this is going to allow us to pick up the fluorescence of the enteral chromophore. And we can see very clearly localization of the transporter in those cells. With a bit of faith, we can even think that the transporter is localized in the membrane. We see a halo here defining the membrane of the cell. Next, we wanted to really do an anion transport assay. And so we decided to use the toxicity of fluoride as a measure of transport. So it's known that if we administer fluoride to red blood cells, the cells are also going to undergo hemolysis. So we use hemolysis as a marker of transport. And in this experiment, which was based on this kind of concentrations here, we first tested the effect of fluoride. And fluoride at this concentration of 100 millimolar was not toxic for about 4 hours, but then started showing some toxic side effects. The stibonium, as I said before, is completely innocuous. It does not create any damage in the cell. However, when we combine these two reagents, we saw a very rapid hemolysis, suggesting an acute toxicity. And we believe that this acute toxicity is the fact that we are facilitating the transport of the fluoride inside the red blood cells with these stibonium cations. We are interested now in, so we have discovered up to this point that both Lewis acidic boranes as well as stibonium cations are good at doing transport. And so some of our activities are now focused on the design of transporters that are smart. And by smart, I mean that can respond to the application of stimuli. And one of these stimuli would be, for example, the redox state of a cell. So we remember that glutathione, shown over here, is a reducing agent that will regulate the redox state of cells. And so we wondered if we could activate a transporter using glutathione. So we go back again to some of our work on boranes, on sulfonium boranes carried out several years ago. We had made these sulfonium boranes as cationic boranes and had found that the sulfonium greatly increases the Lewis acidity of the boron atom, both by electrostatic effect, but also via, I think, this chelate effect here, with the fluoride being also interacting with the sigma star of this carbon sulfur bond over here. What we had found also is that we could simply not use glutathione, but simply phenylthiolate to reduce the sulfonium back into a thioether. And when this compound becomes reduced, we lose the affinity for the fluoride, and the fluoride ends up being released. So we thought that this was something maybe that we could use. And so we decided, why not just try something similar with the stibonium cations. And so we targeted some sulfonium stibonium with the idea that the anion affinity and lipophilicity or hydrophobicity of the molecule could also be modulated by reduction, maybe with glutathione. We weren't too sure what we were going to observe, so this was somewhat exploratory. And there was some beautiful work by the group of Mana, who had shown in using this hydrogen bond donor complex here as a chloride transporter, that reduction of this derivative here, which possesses several sulfonium, allowed for an activation of the transporter. In the presence of sulfonium, this molecule is very hydrophilic and partitioned in water as opposed to in the membrane. Upon cleavage of this bond over here, the molecule becomes more lipophilic and partitioned in the membrane and can start doing transport. So that's a very elegant paper, which gave us some inspiration also. So we went ahead and made this kind of compounds. Making this compound can be cumbersome. In particular, this last step here is difficult because we are trying to make dications in which the two cationic units are very close to one another. So there is quite a bit of electrostatic destabilization in these structures. And so we need to build on it. We need to typically use a trimethyloxonium as a reagent. This doesn't go with methyl iodide or even with methyl triflate. We have to use something stronger. But we're able to make all of these derivatives. These are the thioether derivative with the stibonium. We see that a lone pair from the sulfur donates weakly to the stibonium center. We are here using, I guess, those VS max, which is the value of the potential on the electrostatic potential surface of the derivative that is maximum. These values are in kilocals per mole. This is where they are just used. And so what we see, we have made two compounds. This one has phenol, this one has paramethyl groups. Here, these paratolulyl groups, which are a little bit more lipophilic. And this will be very important later. And those interactions are quite weak to the point that we don't really quench the Lewis acidity of the antimony center. We can, of course, also look at the dication, which are the structures here. And what we see is that the VS max value greatly increase in the presence of a dication because the donation becomes a lot weaker. And we are also dealing with dication. So these molecules are a lot more acidic. We also see that the site of maximum Lewis acidity is probably going to be an antimony. So we went ahead and tried to look at the anion binding affinity of these derivatives. We carried out some titration experiments, and we optimized the structure of the chloride complex that we were not able to crystallize. But what we find is that indeed these derivatives, in particular the dications, have a very strong anion affinity. So for the plain stibonium thioethers, we are binding constant in the thousands to 10,000. As soon as we go to the dication, we are binding constant in the million per mole. And then we assayed all of these molecules with respect to transport. What we discovered is that the dications are very poor transporters. They may be too acidic, they may not be releasing the chloride. And so we are doing here just a chloride transport experiment using a KCl loaded vesicle. However, these thioethers, although weaker Lewis acids, are more lipophilic. We think they partition better in the vesicle and show very good transport properties, in particular for the compounds possessing these paratolulyl groups here, which are sufficiently lipophilic. And so the next stage was to try to turn on the system, right, by a reduction with a GSH. So we know that the dications, the sulfonium stibonium, are not active. So the idea is to do a reduction. And so we studied that reduction by NMR spectroscopy and found indeed using NMR traces that we very cleanly convert the dications into the corresponding stibonium thioether derivatives. We are looking at the paratolulyl derivative. We can also do this reaction. So this one is under more aqueous condition. Here we are in D2O DMSO 8 to 2. So we are 80% aqueous essentially. So reaction is slower, but we again see very clean formation of the monocation, as we can tell from the overlay of these two spectra at the end of the experiment. So to prove our concept in the end, we decided to do transport in the presence of glutathione. And so what we'll do here is that we will let the transporter incubate with glutathione in the presence of the vesicle, and then we'll just activate transport at this stage here, and then we start seeing the effect of this. So when we have no glutathione, we see very little transport. 20 macromolar of glutathione, we see greater transport. 50 macromolar greater transport. 100 macromolar of glutathione, we see even much stronger transport. So this tells us that the compound is turning on because of reduction in solution. So we have a reduction in this turn on of the transport experiment over here. So this has allowed us to demonstrate that we can turn on this type of transporters. These dications are very hydrophilic. They will stay in water, partition poorly in the bilayers. When we reduce them at the sulfonium center, we form this derivative, which has a higher affinity for the membrane and can carry out the transport of the anion. Okay, I'm going to finish by telling you a few achievements in the chemistry of tellurium. As I said earlier, Mathilde also introduced the use of tellurium for transport experiments. And tellurium has been an element that we have studied also over the years. I think we may have been one of the first groups to use telluronium cations to do anion binding in 2010 with a student named Ayan Zhao. So what we have decided to investigate here is the effect of oxidation of the tellurium center. If we oxidize the tellurium, telluride to the telluronium, to the tellurium-4 cation equivalent or analog, we'll see a stabilization of the LUMO, which will tell us that the molecule is becoming a lot more Lewis acidic. If we like to sigma hole description instead, we'll see that this sigma hole becomes a lot deeper. That is, the VS max value is going to increase. And so we went ahead to test. So the bottom line that Mathilde had only tested tellurium 2 derivative, wanted to do some tellurium 4 studies here. So with Benyu, Zhao, we decided to make a couple of compounds. This one was known. This one was known. We also made this mixed system here, 1 mesethyl and 1 pentafluorophenyl. And then we can oxidize them with methyl iodide silver BF4 to go to the telluronium cations. Again, in this case, we have 2 strongly electron withdrawing groups, which necessitate the use of a more potent methylating agent, such as trimethyloxodium BF4. We have obtained the structure of all of these compounds. What we observe in every single case is the fact that the BF4 counteranion binds pretty tightly to the tellurium atom here. And we see that this fluoride here approaches the tellurium atom along the direction of the sigma star orbital of this pentafluorophenyl carbon tellurium bond. So if we look at, is everything okay? Yeah. If we look at the derivatives, we see that indeed, if we look at the energy of the LUMO, we see that the LUMO is indeed stabilized. This is taking into account solvation in order to not overplay the electrostatic effect caused by the introduction of a positive charge. What we see also is that the LUMO becomes better defined in terms of its parentage from the sigma star orbital of this carbon tellurium bond. So we see a very nice lobe here, which is out of phase with the sp orbital from this phenyl group over here. And again, if we look at the VS max value, we do see the effect of oxidation. We have a VS max value of 31 essentially kilocalories per mole, and we go to 146 kilocalories per mole here for that sigma hole. So clearly, we are a lot more acidic. If we try to look at the manifestation of this acidity increase by anion binding studies, we can use fluorine NMR and add chloride to the assay. When we do this with a neutral precursor, the mesethyl pentafluorophenyl telluride, we don't see much of a change, indicating weak or no binding. When we do the same experiment with the cation, we see a very nice progressive change in the chemical shift of some of these fluorine resonances. I forgot which one they are. I think they are the ortho ones. And we get a binding constant of about 10,000 for this compound. So telling us that really we can turn on binding by oxidation. So this verifies the effects of oxidation and the acidity increase that we can obtain. We were excited to try to do transport with this molecule. And again, here the idea is to see if oxidation can help. And sure enough, here we are again looking simply at chloride export from the type of vesicles that I've described before. And the tellurium 2 does not transport, while the tellurium 4 or the telluronium cation is a very potent transporter. By the way, we have also managed to do this kind of assays with the bis-pentafluorophenyl derivative, but this molecule is rather unstable. We still do see increased transport, but we also know from an NMR experiment that once we deploy this molecule in water, it undergoes very rapid reactions. We do think that some of it persists and makes it into the bilayers where it gets stabilized by the hydrophobic nature of these bilayers. So just to finish the last story, we are trying to explore these concepts also in the area of catalysis. We know that anions are prevalent also not only in biological systems, but also on transition metal catalysts. And this is one of the first molecules that we had used many years ago to catch fluoride here with a telluronium molecule, by the way, the telluronium center. So the idea is to chelate chloride here. So we were pleased to see that the high affinity of these molecules for chloride. Could we make a bifunctional version thereof? And it looks easy, but it was actually pretty difficult to build these molecules. We rely here on the transmetallation reaction that starts from boronic acid, and which essentially is triggered by the elimination of BF4, really, from these reactions. We had, where are my conditions? We had cesium fluoride to this reaction, and no, BF3 here, only in that step. And so we can essentially end up eliminating BF4 from this reaction, and we form a bond in between this ipsocarbon atoms here and the telluronium or this tellurium 4 starting material here. So this allows us to also make this monofunctional derivative as well as these bifunctional derivatives here. And again, there is no surprise, the BF4 binds to the tellurium along a sigma star orbital. We are pleased to see that in the case of this dimethylxanthine base system, we see evidence for anion chelation with 2 BF4 bridging the molecule and binding at some of the sigma holes present on these tellurium centers. It's difficult to see sigma holes because we have such an accumulation of positive character at the center of this molecule. And this really speaks again to the cooperativity that can arise in this type of structures. If we look at the LUMO and LUMO +1 and LUMO +2 and LUMO +3, we see that they are all sigma star orbitals oriented along, again, the carbon tellurium bonds. And this allows for the binding of multiple anions. We decided to look at the chloride ion affinity using a spectrophotometric titration, in which we are going to look at the increase in the concentration of the tritium cation by ionization of triphenyl chloromethane or trityl chloride. So trityl chloride as in the cationic form will show a very distinct UV absorption spectrum. This is actually an experiment that was done by Victor Gutmann probably like 60 years ago to estimate the acidity of a number of main group halides. It works extremely well. And so by simply measuring the absorbance from this tritium cation, we can back calculate a relative K value for the chloride ion affinity of these derivatives. And what we see is that the chloride ion affinity of this bifunctional derivative exceeds that of the monofunctional analog by 3 orders of magnitude or 4 orders of magnitude even. This is my last scientific slide. So we are very pleased to be able to deploy these compounds in catalysis. We can certainly activate gold chloride bonds. We are looking at the propargyl-amide cyclization reaction, which works extremely well with the bifunctional and does not work well at all with the monofunctional system. We can also activate platinum chloride bonds, which are more robust than the gold chloride bonds. In this case, we're going to need 2 equivalents of the tellurium chelator to catch each of these 2 chlorides. And here we are looking at the enine cyclization reaction. And again, we see a much greater conversion when we use this derivative when compared to the monofunctional derivative. All right, so the take-home message that Lewis acidic main group cations are great at transporting. We can use redox to inform the transport properties of these compounds, and we can also build in some selectivity of fluoride for over chloride. And these are just two little snippets. I need to thank my group. The students who have done the work that I presented are Jane Park. She's right here. She's graduating in a couple of months. She's going to work with Kit Cummins at MIT as a postdoc. And Ben Yu, who's in his 4th year, with a student from Fudan University. I need to thank the ACSPRF, the NSF, the Welsh Foundation, and Texas A&M for funding, and you for your attention, and the organizer for making part of this program. Thank you.
Yeah, thanks, Francois. Wonderful talk. I hope you will be okay with taking a few questions.
Sure.
Yeah, thanks. Yeah, Ajay, please go ahead with your question.
Professor Gabay, this is Ajay speaking.
Yeah,
Can
hi,
you hear?
Ajay, how are you?
Fine,
Yeah,
thank
sure.
you. Yeah. So I was curious to know this antimony cation which you prepared, the tetraaryl antimony cation few years ago, and the tellurium cation. If you now try to compare these two, can we see any differences in the reactivity, or can we see any parallels?
To tell you the truth, we haven't done that very simple experiment. My perception is that the stibonium cations are more resilient. They're a bit more stable in water, but we have not compared them. We have not done comparative studies. So
because I was looking at the tellurium cation. Perhaps if the methyl group is replaced by a perfluorinated aryl group, then
yes,
we can make a direct comparison.
We get into issues of stability but yeah, we should look at actually we do have. I mean, one of the last structures that I showed is a triphenyl, a triaryl tellurium cation. We haven't done the comparison, so I can't really answer it. What we know from the work of Gutmann is that if you compare tellurium tetrachloride to antimony pentachloride, antimony is going to win. So if you look at chloride ion affinity trends, antimony typically wins. So I would put my bet on antimony, but it's a subtle difference, and I think you can tune it using using the substituents, as you rightly point out. Okay.
Yeah. Thank you. An excellent talk.
Yeah, Sundar, please go ahead.
Hey, Francois, it's a very nice talk, beautiful chemistry. I just wanted to know your bis tellurium dication compared to a tellurium monocation. So any idea how the tellurium NMR would look like of these two?
Yes, we have them all. They are not very telling. They are clean. That's all I can say. We see single peaks,
But
but it's difficult to say. We don't treat tellurium NMR. It's finicky. The trends that you will see are not like what you will see in the chemical shift of a proton as becoming more acidic, shifting downfield. These larger elements, the NMR or the chemical shift of this larger element is often complicated by the paramagnetic contribution to the chemical shift anisotropy. That is especially when we are relying LUMOS. So things can shift in different directions. It's not a very good predictive tool.
so you don't find any general trends of these?
No, we don't. In fact,
Oh.
we find no trends.
Okay, thank
So
you.
we still measure them for just for compound purity. Yeah.
Okay.
Yeah, Ganesan, you can go ahead actually.
Okay. Professor Gabay, I like to ask you, how do one measure the anion efflux?
How do we measure it?
Yes, I'm wondering how do I measure
Yeah, we just measure
anion
it with an electrode. Do you see this here? Yeah, so we have an electrode here. This electrode is hooked up to a voltmeter essentially, and the voltage of the electrode is going to change as the chloride anion concentration increases. So the chloride is encased in the vesicles, and the chloride escapes and then makes it to the electrode interface here and gets detected.
Oh, okay.
Yeah,
I see.
it's like a pH. It's like measuring a pH, but we are just measuring chloride concentration as opposed
Okay.
to proton concentrations.
Okay.
It's pretty
Yeah.
straightforward. Making the vesicle is a pain. It takes half a day. Yeah, it's a difficult problem.
I have another comments since that antimony is attached to some polyaromatic compounds, are they not harmful to the cell?
Are they not what? Toxic?
Harmful to the cell because some pyrene molecules such as pyrines are attached to the.
Yeah, I'm sure they could be mutagenic, right? They could intercalate. Yeah. In the long run, you don't want to have them around. Yeah, but yeah, red blood cells don't have a nucleus. I don't know. I don't think they have. Yeah, they are not really alive anyway. They are just packages of hemoglobins. They are very simple cells. But you are right that on the long term, that may be an issue.
Thank you very much. Thank you.
Yeah, if there are no more questions, I again thank Francois for accepting the invitation and delivering a wonderful talk here. Thanks, Francois.
Thank you, Nax. Thank you so much.
Yeah, sure. Yeah, thanks
I
a
need to
lot.
stop my share. Yeah, stop share. Yeah.
Yeah.
Okay. Bye.
Thanks a lot.
Thanks.
Yeah, see you then. Yeah. Yeah, the next speaker of the session is Dr. Yang Qin. He obtained his PhD degree in 2006 from Rutgers University. After a couple of postdoctoral stays, Dr. Yang joined the Department of Chemistry and Chemical Biology at the University of New Mexico in 2010 and became an associate professor in 2017. In 2020, he moved to the University of Connecticut, and his research group focuses on designing and synthesizing conjugated organic and polymeric molecules, organic and inorganic hybrid materials, and they are looking at their applications in energy and the environment. He is the recipient of various awards such as NSF Career Award and NIH NM INBRI Award. The title of his talk is Cross-Conjugated Polychalcogenylene Vinylenes. With these few words, I now invite Dr. Yang to go ahead with his presentation. Dr. Yang, please.
Oh, thank you, Dr. Rajendran, for this kind introduction. And I would like to thank the organizers for putting together this wonderful symposium, as well, especially for the Krishnan for the invitation. So Krishnan and I actually went back for quite some years now. I think in the early 2000s, when I was a grad student in Frieder's group, Krishnan was a postdoc. And so the one thing I remember most is Krishnan is kind of very accurate on his timing, or punctuate on his timing. So every afternoon at 3 p.m., he would actually go to every lab and grab everybody in the lab and cries out, "Coffee, coffee!" And we will go out to a coffee stand, which is called a Jerry's, and we all sit down and have coffee there. And to be honest, that's probably not the best coffee I ever had, but we really enjoyed the time together. So I was really disappointed that we could not meet in person this time, but hopefully we'll catch up later on in other occasions. So thanks a lot. So today there's a slight change of my presentation title. I decided to give you 2 short stories on what we have been working on that are tightly associated with this central scheme of this conference, which is the materials and molecules containing main group elements. So can you see my screen well?
Yeah, sure. Yeah, sure. Please go ahead.
That's great. So the first story, we'll talk about how we incorporate cross-conjugated elements into polycyanidine vanillines and polycyanidine vanillines, a pretty prototypical conjugated polymers, and change their electronic properties. And the second topic is we recently started project in our group is try to make ionic metal organic frameworks, and that's derived from a borate tetrapodo ligands. So before I start, I would like to thank my group. So my group kind of shrinked in size after the move. So now I have 4 group members, 1 postdoc, and 3 grad students. And throughout the past 10 years, we have a lot of collaborators, but especially I would like to thank Dr. Dan Dickey from University of Virginia, who actually did all our X-ray studies on the MOF crystals. And I would like to thank NSF as well as USDA, that are the main funding sources for the research I'm talking about today. So the first topic we have been working on for the past 10 years now is for synthesizing conjugated polymers for organic photovoltaic applications. So conjugated polymers are basically conducting or semiconducting polymers. They are composed mostly of aromatic groups connected together, and along the main chain of the polymer, you will find a path of carbon chains that have alternating double bonds, single bonds. So every carbon atom is sp2 hybridized, and it has a p orbitals that can overlap and that have electron delocalization along the main chains. That give you the semiconducting properties as well as conductivity after doping. So this is a very prototypical conjugated polymer called P3HD, stands for regional regular poly3-hexosilane. It's one of the most studied conjugated polymers because it can be made from a cross-leaving polymerization process. It's stable and high crystalline and has a relatively large band gap, about 1.9 electron volt. So the state-of-the-art conjugated polymers used in organic photovoltaics are these alternating donor accepting type of conjugated polymers by combining electron-rich and electron-poor units in alternating fashion along the main chains, and by taking advantage of the so-called intramolecular charge transfer interactions, you can actually further narrow the band gap of these molecules, as well as fine-tuning the positions of the frontier energy orbitals of the resulting polymers. So what we are especially interested in is also one of the prototypical polymer called polycyanidine vanillines. The difference between PTVs and polysilophane is basically there's 1 more double bond between every siphon units along the main chain of the polymer. Because of the double bond is very small, that actually eliminates the steric hindrance between the aromatic groups. So PTVs tend to be more planar than the polysilophanes. That leads to a lower band gap, about 1.7 to 1.8 electron volts, and high crystallinity and charge mobility, as well as environmental stabilities, and recently discovered actively singular fission processes that are actually very intriguing, that you can actually get 2 electrons out by absorbing 1 photon. But however, this polymer has a very peculiar electronic structures, because the lowest excited state has the total symmetry the same as its ground state. So that leads to a very short exciton lifetime on the picosecond levels. So this very short exciton lifetime leads to very non-fluorescence properties of these polymers, as well as the charge extraction becomes very extremely difficult in device applications. So many examples of OPV devices employing PTVs or have power conversion efficiency about less than 1%. So what we are especially interested in is mostly from a fundamental level. Can we actually use this PTV scaffolds and develop synthetic methods toward structurally diverse PTVs, and somehow we can actually reorganize their excited states energetics, for example, by raising the 2 AG states above its 1 BU state, then we can actually lead to more efficient single efficient as well as fluorescence and the longer exon lifetimes. So in order to do that by keeping the PTV skeletons, one way we can change is the heteroatoms as the aromatic groups. Another position is we can actually put another substituents directly on the aromatic groups. And if the B here functional group is conjugated, we can actually tune the conjugation between B and the silophene mentions and somehow use this so-called cross-conjugation scheme to change the electronic properties of the resulting polymers. So traditionally, PTV are synthesized by these so-called Vedic type reactions or elimination from precursors, McMurray coupling or cross-coupling reactions. And these reactions are, however, not suited for the purpose of the structures we are targeting because they're either not compatible with many functional groups as we want to install, or they can generate a lot of defects during the process. So the method we choose is metathesis. The metathesis is basically a catalyzed reaction swapping substitutions in a double bond to get new vinyl or ethylene molecules. So if a monomer have 2 double bonds on each side, through the metathesis reactions and remove ethylene as a byproduct, you can actually drive the metathesis reaction towards polymerizations and end up with polyaridine, vanillin type of polymer structures. So we have applied this ATMET methodology on this dipropynyl silophene monomers and successfully prepared PTV derivatives that has very well-defined structures. But here our group is arcuate groups. So in order to install cross-conjugated aromatic groups, our methodology is like this. So we actually started with a tribromo silophene monomer, and by controlling cross-coupling with 2 equivalents of propynyl tetrabutylene reagents, we can install 2 double bonds at the 2 and 5 position of the silophenes. That leaves the 3 position with the bromine groups. And this bromine group can be exchanged with other halogens as like fluorine, chlorine, and iodine, and all these halogen monomers can be polymerized by ATMET polymerizations to afford PTVs that have an arcuate chain as well as different halogens. To our surprise, the electronic properties like absorptions and frontier energy orbitals are all very similar, despite there are different halogen groups attached to it. So, but one of the polymers that has bromine substituents can be conveniently used to actually diversify the structures through the so-called post-polymerization modification reactions. In this case, we use steady coupling reactions, for example, with the tin reagents of a silophene, and protected silophene has an aldehyde groups, and then convert the aldehyde group with the electron withdrawing cyanoester groups. So we actually test these 3 polymers that have every silophene repeat units along the polymer matrix has another silophene which is cross-conjugated at the side 3 positions. So when we look at the UV-Vis absorption spectra of these polymers in both solutions and as thin films, the black curve is the PTVs without any cross-conjugated side chains, and the other ones are the ones with aromatic side chains. And you can see with the cross-conjugation, the absorption window is much broader. We see a new peaks in the UV and the blue region that's originated from the sidechain itself. But when the sidechain has strong electron withdrawing groups, like the blue curve shown here, which has the cyanoester group, which is strongly electron withdrawing, we actually see a new peak evolved in the lower energy region, all the way up to about 800 nanometers. And we ascribe this peak to the main chain to side chain charge transfer interactions. This has not been observed in previous PTV examples. And all interested in, as we talked about previously, PTVs are non-fluorescent because of the low-lying non-emissive excited states. But with the strongly electron withdrawing groups, we can actually observe low energy fluorescence, and not most likely originating from the mentioned side chain charge transfer states, and that becomes more emissive. So this is one of the few examples of fluorescent PTVs. And we can actually apply the same methodology to selenophenes, and because selenophene has a low-lying d orbitals that can actually participate in the pi star of the aromatic systems that can actually stabilize the pi star orbitals, actually lower the LUMO of the polymers and further reduce the band gap. So this methodology is very similar. We made this dipropenyl and the 3-bromo selenophenes, and through the Artemet polymerizations, we make the so-called PSV, that stands for polyselenoline vanillines, that has a bromine groups attached to the 3 positions. And then we use steady coupling, which install the same, exactly the same cross-conjugated cross-conjugated aromatic groups as side chains. So when we look at the absorption spectra, they actually look very similar in the PTV case. The only difference is all the spectra are shifted to the lower energy. That leads to a lower band gap because of the reason we just talked about. And we also see this mentioned to side chain charge transfer interactions. And that's the PSV polymer with the strongly electron withdrawing side chains. And that has a band gap as low as about 1.4 electron volts. And also by this so-called charge transfer interactions and the cross-conjugate side chains, we can actually fine-tune the HOMO-LUMO energy levels of these polymers. For example, by using the strongly electron withdrawing side chains, we can reduce or lower the LUMO levels of these conjugated polymers. And that's the main reason why this polymer has the lowest band gap. So we put these polymers in OPV devices. I will not go through details of the device physics here, but I would just directly jump to the conclusion is, so most of the original PTVs without sidechains or PSV without sidechains has very low power conversion efficiencies. So for PTVs, it's about 0.5%. For PSV, it's about 0.2%. So it's very lousy performance. In the PTV case, if we have the cross-conjugate sidechain with some electron withdrawing properties, we can actually increase the efficiency to about 1.6 and 1.4%, which is about 3-fold increase, although they do not perform very well compared to the current standards. And in the PSV case, the best performing polymer is the brominated polymer that can increase the efficiency from 0.2 all the way to about 1%. So by structurally diversifying these polymers, we can actually increase their performance. So right now, we're still working on how to further install even stronger electron withdrawing groups, such as cyano groups, directly on the mention of PTVs that may actually disrupt the electronic structures further and improve the electronic properties of these polymers. So I think I have a few minutes left. I will switch gears a little bit. I'll talk about our recently started project that involves metal organic frameworks. It actually MOF, it's also called porous coordination polymer, stands abbreviated as PCP. It has a IUPAC definition. So MOF is a coordination network with organic ligands containing potential voids. So it's very simple definitions, but which basically the MOF is also very simple to make. in a sense. You basically mix a inorganic ions, metal ions with organic ligands, and you cook it up in a certain environment, in a certain solvent, certain temperature, and they will crystallize into very well-ordered porous crystals. And these just shown two examples of ZIF8, that's a combination of zinc 2+ with 2-methyl-imidazole ligands, and HCUS1 is basically copper 2 with trismic acids. And so these microporous crystals has large surface area and tunable pore volumes and tunable pore sizes. And you can actually tune the surface functionalities for different applications. So the properties of these MOFs can be tailored for a wide variety of applications. And for example, catalysis, conductivity, magnetism, sensing. And this is a pretty comprehensive review of what MOFs can be used for. As you can see, almost any applications you can think of, people have been trying to use MOF, trying to apply MOF in them. But what we are really interested in is a so-called ionic or charge-separated MOFs. So most of the MOFs actually are neutral because of the metal ions are immediately charge balanced with the ligands. In most cases are carboxylic ligands. So there are no exposed or isolated charges within the MOF systems. So the ionic or charge-separated MOFs, on the other hand, will have isolated or exposed ions in the systems. There's several structural motifs shown here. You can have free cations, free anions, or anions on the ligands, or you have anions on the nodes or cations free, or you have anions and cations both on the nodes. But they are exposed. So they can actually impart influences or properties those charge neutral MOFs cannot. For example, if you insert ions in the pores, you can actually fine-tune the pore volumes and pore opening sizes. You can actually tailor design specific interaction with gas molecules, which we'll be talking about with our examples. And since you have exposed charges, you can have organized internal electric fields, and theoretically, they can interact with gas molecules such as hydrogens. And these ions can be used for ion exchange and conductivity applications, as well as catalysis, sensing, drug discovery, and nonlinear optics and magnetisms. So to synthesize ionic or charge-separated MOFs, I think one of the most applied methods is to use charged ligands and combined with charged metal ions. So one of the charged ligands have been applied widely is the so-called boron imidazolate ligands. Borate is basically boron with 4 imidazole ligands that gives a negative charge on boron. And then the remaining 4 nitrogens can use as coordination ligands to bind metal ions to form a porous network. The reason why these ligands are interesting because of the angles between NBN kind of mimics the angles in the zeolitic imidazolate framework. In this case, it's zinc imidazole or zinc and zinc, or at about 145 degrees, and that's comparable with the borosilicates and as well as zeolites angles. So they can form similar structures as natural zeolites, but have more tunabilities in terms of pore sizes as well as functionalities. So you can use this tetraimidazolate borate ligands and combine with different metal ions, you can actually get different MOFs, which has fixed charges or at isolated charge at fixed locations with different topologies. But one problem with this ligands is the ligands is actually not symmetrical. So if you rotate these ligands around the BN centers, you can have the second nitrogen on each of the imidazole ligands pointing in different directions. And this structure flexibility is good because you can actually tune the structure to very different final topologies, but that also makes the prediction of the structure is very difficult because of the flexibility of the ligands. So our thought here is, can we design a borate ligand, use nitrogen as a coordination ligand, but in a tetrahedral fashion, which is rigid, has no flexibility in terms of the structures. So we have to make the ligand straight. So for example, we designed the ligands like this. So it basically reminds you, the center looks like a tetrakis pentophenoborate, but at each of the 4 positions of the aromatic rings, we can install a pyridine ligands. And there's a triple bond spacer in there. I'll show you why that is in a minute. And this ligands, no matter how you rotate the single bonds, the nitrogen and the boron always have a tetrahedral angles. So here is the synthetic scheme of this ligand. We started with this molecule, and basically this is the 4 position of the tetraphenyl ring, and the make a borate ligands and to protect the TIPS groups. And then through a Sanagashira coupling, we can install the pyridine ligands. And then if we combine this tetrahedral pyridine ligands with copper-1, which is also a tetrahedral coordinating metal ions, we could potentially form a diamondoid-like structures. Indeed, we call this MOF UNM1. And the single crystal structure, which proves it does have a dialet net topology and crystallize in the tetragonal crystal system, and all the boron and copper 1 centers are tetrahedral in nature. However, these crystals are from a space Feeling model, you can see they are tetral or 4-fold interpenetrated. That actually leads to a not so high surface area from deep PET measurements. It's about 620 square meter per gram. So we subjected this MOFs to a gas selectivity absorption measurements by look at the absorption and desorption isotherm of CO2 as well as nitrogen at different temperatures. What's most interesting is at about 313 Kelvin, you see a very large hysteresis. So this is the absorption curve, and here is the desorption curves. So there is a large hysteresis at this temperature. That means at this particular temperature, there's very strong or relatively stronger interactions between the CO2 and the surface of the pore surface of the MOFs. And that leads to ideal selectivity between CO2 and nitrogen of about 100 at 1 atm, and particularly at 313 degrees Celsius. So our next step is we actually want to reduce the interpenetration degrees in order to increase the surface area. That might actually increase the gas uptake properties. So one way we can do is we think the arm of the borate ligand is too long. So we want to get rid of the triple bond. And this is the way we do it. So we started with the dibromo tetrafluorobenzene. This is just one of the bromine and make the borate, and then use a Suzuki coupling, basically replace the bromine with a pyridine ligands. And if we combine this ligand with copper-1, we indeed also get a MOF structure, which all the copper-1 is tetracoordinated, or the boron is also tetracoordinated, but it crystallizes in a I think it's a triclinic structure or monoclinic structure. But because of the shorter ligands, it becomes a 2-fold instead of a 4-fold interpenetrated monoclinic system. However, structure becomes unstable upon solvent removal, so it collapses, becomes non-porous. Now, we still don't know exactly why that is, but we are actually trying to optimize the reaction conditions to see if we can actually make different crystal structures as well as more stable MOFs with copper-1. However, if we use cobalt 2+ as the metal ions, and we actually obtain a very, very stable crystal structures. And this is a cubic system. It's very symmetric cubic system, to our surprise, because when you look at the structure, the boron is tetracoordinated. Every boron has 4 cobalt according to the nitrogen ligands, but every cobalt only has 3 nitrogen coordinated, with the 4th ligand as a nitrate ion. And because of the +2 cobalt nature, which means there are also some free nitrate ions in the pores and not resolved by the X-ray crystallography. And because of asymmetric structure of a cobalt, so we are kind of surprised that the crystal substance is actually very symmetric cubic system. And this system is also 4-fold interpenetrated. So now we think there's a free nitrate ions in the system, and the nitrate is not a very good coordinate ligands with metals. So we think we can actually exchange this nitrate ion with other different ions. And indeed, we can actually anion exchange this nitrate with other different anions just by soaking the MOF in a water solution with other anions in large excess. So we can actually exchange it with fluoride, chloride, bromide, iodide, or cyanide or azide. And you can actually see the color drastically changes to different color, depends on what anions is in there. So we actually confirmed anion exchange by IR spectroscopy. And it's basically by look at this peak, which is characteristic of nitrate ions stretching mode at about 1385 Wilm numbers. After the anion exchange reactions, this peak almost disappeared in all those exchange samples, accompanied by appearance of the absorptions of the exchanged ions, such as the cyanide or the azide. And we use XRD to confirm the structure actually did not change during this exchange reactions, which also confirms that these MOFs are actually water stable. And the surface area is not very high because of the 4-fold interpenetrations, as well as inclusion of free ions to balance the charges in the pore size. Except of the UNM6 cyanide, which has the exchange cyanide groups, we do not understand at this point why the cyanide MOFs has such low BET surface areas. So we subjected to the same gas absorption activities at different temperatures. We observe very similar phenomena. We do see some hysteresis, but it's less than what we saw with UNM1 case. But the ideal selectivity at 313 Kelvin reaches about 1,000. And this is not mostly come from the very low nitrogen absorptivity at this temperature in the MOF, not necessarily from high CO2 uptake. This is the last slide I will show. We also use this MOF to do some catalysis, for example, of the CO2 fixation or CO2 cyclization to form cyclic carbonate, because this reaction that normally catalyzes with the Lewis acid and the Lewis base through this catalytic cycle. And in our MOFs, we have cobalt ions, which can be exposed because the nitrate or other anions can be fractional as a Lewis acids, and these anions can act as a Lewis base. So we use this in the solvent-free conditions, but by soaking with a, I think in this case with our group here is a methyl propylene oxide, and we can actually achieve up to about 93% conversion at about 115 degrees Celsius after 3 hours, after 72 hours. And generally, the bromide version performs better than the nitrate. We basically think the bromide is a better nucleophile than the nitrate in the so-called catalytic conversion reactions. So right now we optimize the conditions and study the catalytic performance with other anion exchange MOFs. So with that, I would conclude, and thank you all for your invitation and your attention. And if I have a time, I would be happy to answer you with any questions.
Thanks, Yang. Excellent talk. I think we may have time for just one question, actually. Yeah, Rajesh. Yeah, Rajesh, go ahead.
Hi, sir. Good
Go
work.
ahead.
Sir, I have only one question. In last work, did you check that software scope? Did you vary the different software of epoxide?
Can you say that again?
In last question, did you check with the different epoxide?
You mean this?
Instead of propylene oxide, did you check with the different oxide like the
Oh.
butylene oxide?
Yeah, no, we only had propylene oxide. We only checked that. We didn't check different oxide yet, but that's something we definitely would like to check on, because then the size of the epoxide will be different. They may have different.
Yes, sir, definitely. Because this pore size is also looking very less.
What's that?
Pore size of MOF looks less.
The pore size is actually not very small. I think it looks pretty small, but I think it's about, if I remember correctly, it's a few angstroms. It's not that small. I think it's between 5 and 6 angstroms.
Okay, sir. If it is 5 to 6 angstrom, then it is fine. It is 4 interplanetary. That's why I asked. Okay, sir. Thank you, sir.
Okay, thanks.
Yeah, Anantaraman, yeah, please go ahead, but be very brief.
Okay. This is related to the different colors, what you get it because of the anion exchange. So what is the origin of this?
Oh, I think it's basically the coordination environment of cobalt becomes different. That's our guess.
Okay.
Yeah, because they have different strengths.
So, okay, per sites, how many you can include these gas anions?
How many? I think the nitrate can be replaced with a lot of different ions, because the nitrate, I think, in water do not coordinate cobalt very strongly. We have not tested to exchange the other ions between the other anions, because like the cyanide, I would think there would be much stronger coordination. It's probably harder to remove, but the nitrate can be easily removed.
So that means, are we allowed to say it's like a mixed anions are present on the cobalt still? That's why this fine tuning on the color is coming to you.
I think the nitrate can be completely replaced with other ions, because we don't see that in the IR anymore, at least the most of it.
Okay.
And that changed the coordination environment of the cobalt. So that basically changes the DD transition energetics, and that the color becomes different. Well, but when you look at the UV vis, the lambda max is only very slight different from different species, different exchange MOFs, and that but that slight different give you different colors.
Okay. Thank you.
Sure, thanks.
Yeah. On behalf of the organizers and on my personal behalf, I again thank Yang for his wonderful talk. And yeah, thanks, Yang. Yeah, let us move on to the last talk of this session. The last speaker of the session is Dr. K. Geetharani. She obtained her PhD from IIT Madras in 2012. After her postdoctoral stays, she joined IPC, IISc Bangalore as an assistant professor in 2016. She has won various awards. Some of the recent ones are the NACI Young Scientist Platinum Jubilee Award in 2019 and SCRB Women Excellence Award in 2020. With this very brief introduction, now I invite Geetharani to deliver her talk titled Homolytic Cleavage of Diboron Compounds by diazobutadiene derivatives. Geetharani, please go ahead.
Yeah, thank you, Professor Nagendran, for your kind words. And first of all, I would like to thank the organizing committee and Professor Krishnan for inviting me for this conference to deliver a lecture. So today I will be discussing about a very recent result which we got it on the homolytic cleavage of diboron compounds by diazobutane derivatives. I hope you are able to see. Yes.
Yeah, it's fine, Geeta. You can go ahead. Actually. Yeah.
So let me begin with a simple introduction of different type of boron reagents. When we talk about source of borons, the first thing comes in our mind is the diboranes, which is a B2H6, and this was being mainly used in variety of reactions, like at the initial stages when the boron chemistry started emerging for many hydroboration type of reactions. Then the source of boron has been emerged to trihaloboranes, and then followed by that it move on to a trialkoxyboranes. The source of borons and the boron reagents actually helps in developing a synthesis of organoborane compounds, like as I mentioned here, as I shown here, that the organoboranes are nothing but the organic compounds having carbon-boron bond, and we all know that it is one of the important reagent in Suzuki coupling reactions, and which is being awarded a Nobel Prize in 2010. That's because of this organoborane compounds can be converted into a different type of functional groups. Now, how does this synthesis of organoboranes begin? In the earlier days, that people use that borate as a reagent for synthesizing this organoborane compounds, where they particularly used very reactive reagents like lithium and magnesium. Then people also explored the boron trihalide as a reagent for synthesizing these organoborane compounds, where the selectivity was most of the time the problem. The availability of diboron reagent made this process very simple for the synthesis of organoboranes, like that's mainly due to the stability of the diborane reagents. And some of the diboranes listed here are currently very much in use for the synthesis of organoborane compounds. It's not only the stability, and it is also easy to isolate the compound once it's been synthesized. When we talk about the diborane reagents, for any kind of catalytic reactions for the synthesis of organoborane compounds, the important step in the reaction mechanism is the cleavage of this diborane bond. How does one can cleave this diborane bonds? Here is the overview of different methodologies where we can cleave the diboranes. It can be cleaved either in a heterolytic manner, or it can be cleaved in a homolytic way. Here particularly, I just given an example where the homolytic cleavage can be happen with the different type of nucleophiles or metal transition metal compounds, or even organic substrate as a homolytic cleavage reagent, and by using a simple base like pyridine substituted base. So to elaborate this example, here I have shown that the alkene diboration reaction, it can happen in the presence of without the metal catalyst, that the diborane cleavage can happen, but it does require a very reactive diborane reagent. Then later, the metal catalyzed borylation reactions occurs, in which one of the very important step is the cleavage of the diboron bond by the help of the transition metal complex, where even there are evidences that metal boryl complex formed by the cleavage of diboranes. For example, the cobalt triphenylphosphine compound can cleave this B2Cat2 and gives this cobalt boryl compound, which further reacts with the substrate and undergoes these organic transformation reactions. This is also true with the palladium type of compounds, where the one of the step is the cleavage of the diborane compounds. And very recently, different type of cleavage has been reported for this diborane. For example, like sp2, sp3. I mean, you just react the diborane with any kind of base, particularly the Lewis base and take any strong nucleophile, it can actually coordinate to the one of the boron atom, and it gives this the diboron becomes one boron becomes sp2 and the other boron becomes sp3, and which actually proceeds with the diboron cleavage. But in most of the cases, this type of Lewis base coordinated or through the sp2 sp3 hybridized boron cleavage, when we use the strong nucleophile, it actually undergoes a homolytic cleavage. But there are also some examples where you can actually cleave the diboron in a homolytic way by using a simple mild base. And there goes an example of the cleavage of diboron. In the year 1995, Todd Murder has identified that simple picoline, upon reaction with B2CAT2, they have isolated the bis adduct of this diboron compound, where they observe that there is an elongation in the boron-boron bond. If you see that in normal B2CAT2, diboron reagent, the boron-boron bond distance is 1.68. However, upon coordination with this picoline, the boron-boron bond got elongated, and then the bond distance becomes 1.713. This was the first evidence that one can actually weaken the boron-boron bond without any transition metal catalyst. And later on, it took a decade to come up with a different type of reactivity and taking into an advantage of this diboron cleavage for using a different type of azine heterocycles, where Sukhinov reported in 2012 using this pyrrocine derivative. He reacted with the B2PIN2, where they can actually cleave this diboron and get this NN borylated 1,4-dihydropyrrocine compound. And this is not only applicable for the diboron cleavage, they also explored this one with the silaboration. They could cleave this silyl boron bond, and also the hydroboration was achieved for the pyrrocine derivatives. Later on, they took this compound as a catalyst, and they further developed this 4,4-bipyridine catalyzed diboration for the pyrrocine derivative, by which they could able to transfer this boron to an 4,4-bipyridine compound, and they can able to get a different type of borylated pyridine derivative compounds. Then the work was further continued with cyanopyridine type. This is a very interesting observation, and there are many reports are coming up with this based on this results, where they have taken this cyanopyridine and then reacted with the B2PIN2, and they observed that the pyridine stabilized boryl radical, which can actually activate or transfer this boron source into a different type of organic substrate. By using this borylated pyridine radical, they actually achieved the reduction of azarines, as well as coupling with pyridyl phosphonium salts, and also they could able to get the aryl borylated product by using this as an intermediate and cyanopyridine as a catalyst. And recently, the studies also shows that the isoquinoline can actually cleave this diboron and gives this carbon-carbon coupled product. Why I am elaborating these two is that they propose that these two type of reactions, although it is a cleavage of diboron, they actually undergoes a different type of reactive mechanisms. Here they propose that it is a homolytic cleavage and the radical formation, but here the isoquinoline type of diboron cleavage actually undergoes via 3,3 sigma-tropic rearrangement reactions. So this is the mechanistic DFT calculation for the diboron cleavage by the cyanopyridine, and there are many more DFT studies been coming up with this this reagent using cyanopyridine. How does it actually cleaves this diboron? And as you can see from here, this is the energy diagram, where they have shown that the first step might be the coordination of the one cyanopyridine unit to the B2PIN2, which actually makes this sp2sp3 hybridized boron, and then the possibility of other pyridine can coordinate to the next boron unit on the same this transition state in this intermediate, and then which actually undergoes kind of concerted mechanism to form this carbon-carbon bonded compound, where the diboron is now completely cleaved, and which then further undergoes cleavage of this reaction and gives this N-pyridyl boryl radical. And also this report actually says that the radical is actually centered on the C4 carbon, by which they can also use this as a source of carbon radicals. So keeping this in mind, we were actually look at the example of the isoquinoline unit, where they propose that the intermediate can be like this, forming via 6-membered concerted mechanism. This one actually gave us the clue that what about if you take a diazobutadiene, which can actually cleave, can it be cleave the diboron bonds? Then, because as it is having a 2 nitrogen atom linked via conjugated bipons, and there are possibilities that both the nitrogen atom may coordinate to 2 boron atoms of the diboron from the same phase, and we would be also able to get similar kind of compound. So with this idea in mind, we begin the reaction of 1,2-diazobutadiene derivative, where we first initially took this isopropyl substituted diazobutadiene and reacted with the B2Cat2. The reaction was very quick. In 15 minutes, we actually observed the change in the color, and the boron NMR shows that peak at 25.6 ppm, which is actually corresponds to the 3 coordinated boron nitrogen compound. And the proton NMR was very interesting, as we expect that if it is going to be a symmetric compound, that there is going to be only one type of isopropyl unit for the N substitute, this isopropyl group. However, the proton NMR actually shows that there are different types of isopropyl groups, which gave us the clue that the geometry is, although it looks like a symmetrical, it is not the proton of the isopropyl units are not under the same environment. And also the C13 NMR actually gives the we did not see any peak in the isopropyl unit group, which is suppressed. So there are 2 possibilities. One can expect that either there is a rotation about this carbon nitrogen bond and this compound is still in the isomeric form in the solution, or say there may be some other factors playing, which actually leading to a different type of isopropyl unit. We were lucky to get the crystal structure of this cleaved diboron compounds, where we can see that it is a cis-configured compound, and the boron nitrogen bonds are within the single bond range, and also there is a formation of carbon-carbon double bond with the backbone carbons. Then when we look at the top view of this this crystal structure, we actually observed intramolecular hydrogen bonding. There is a hydrogen bonding between these oxygen of B2Cat2 BCat unit and between this and the CH proton of this isopropyl group. As you can see from here, the H14 and the O1, the bond distance is it is actually 2.484 angstrom, which is clearly in the range of intramolecular hydrogen bonding. So then we want to confirm that why there is that's the reason you can see that there are two different types of isopropyl groups from the proton NMR. And we further want to confirm this intramolecular hydrogen bonding. So we have done this variable temperature NMR, which clearly shows that when we lower the temperature from room temperature to -50 degrees centigrade, we see the slight downfield shift of the proton NMR and this corresponds to the methyl group, and the peak at 4.23 corresponds to the CH proton, which is H14. We could able to see the clear septet at the very low temperature of -50 degrees centigrade. Also, the C13 NMR gives started giving the carbon corresponds to the isopropyl group upon lowering the temperature. So this gave us the clue that there is an intramolecular hydrogen bonding, which actually leads to a different type of isopropyl unit in the proton NMR, and which may also give the stabilize the cis conformation. Then we move on to the reaction of different diborons with the same DIPTAP unit, where we explored BPEN, B2-neop2, and other boronic diboron compounds. But however, no diboron compounds except this B2-thio-Cat2 does react. When we did this, this may be because this may be because of the highly Lewis acidity of the B2-Cat2 units and comparable Lewis acidity of this B2-thio-Cat unit. Then we wanted to look at the possible reaction pathway, since this is giving us this product. As I have shown in the previous example, there is a possibility that 2 units of the diazo unit can coordinate. And in our compound, we have the 2 nitrogen atoms facing towards this. So this can actually undergo via a concerted mechanism, and which is actually giving this product. Then we want to explore the reaction of this diboron cleavage with the other diazine, dibutadiene. When we took this mesityl substituted diazobutadiene, upon reaction with the P2-Cat2 in room temperature, we actually expected a cis product. However, we isolated a trans product from this reaction mixture. As you can see, the proton NMR, which is clearly of a single unit with a methyl group of this mesityl unit, and we did not see any differentiation in the protons of this methyl as well as this benzene proton. And the crystal structure shows that it is now we get this trans geometry with the mesityl substituted 1,2-diazobutadiene. The boron nitrogen bond and the carbon-carbon bond distances well with comparable with the single bond and double bonded distances respectively. And we further want to convert this. We want to know whether any kind of cis-trans isomerization is playing a role in the solution state. So we thought of further substituting this BCAT unit with the acyl group, where there are examples that by which we can actually stabilize this compound in a single isomer form. So when we did this acetyl chloride, the trans geometry was observed in this case of acylated product. Then we were thinking why there is a change in the geometry when we use a isopropyl group, we get this cis geometry, and when we use a mesityl compound, we get this trans geometry. Is there like diboron bonds are cleaving and giving a boryl radical which is attacking to the diazobutadiene? So to confirm the radical formation, we actually carried out the radical reaction reaction studies, where we took this diazobutadiene with the B2-Cat2. When we did reaction with the tempo, we actually did not see any change in the product yield, which gives the 99% of 3. And then when we again did with the 1,2-dihydroanthracene, there is no decrease in the yield, which clearly shows that there is no radical formation in this reaction, which means there is no boryl radical is forming. Then this is the same case with when we use the mesityl substituted 1,2-diazobutadiene also. And then we thought that, okay, maybe the product is forming, then it is maybe undergoing an cis-trans kind of photo-assisted isomerization after the reaction is completing. and giving a thermodynamically stable product in each case. So we have carried out this reaction in a dark as well as in the light to find it out any photo-assisted cis trans isomerization is possible for this different geometry observed in the above reactions. However, the results shown for compound 3 and 4 for diisopropyl and mesityle group, we did not see any change in the UV visible absorption spectrum, which clearly indicates that there is no light assisted isomerization is happening. And as I mentioned, there are two kinds of mechanism generally proposed for the cleavage of diboron unit by using a different kind of azabenzene compounds. One is a kind of a cooperative mechanism where the two pyridine is simultaneously coordinating with the B2-pin2 unit, and which cleaves the boron-boron bond and gives this boryl radical. The another one is that it's a 3-3 sigma tropic rearrangement type of reactions. So, and also we want to see that whether it is the same diazobutadiene is coordinating to a 2 units of B2-Cat2, or it's a 1 diazobutadiene unit coordinating to one B2-Cat2 and cleaving the boron-boron bond. If we expect that this kind of compound, then the trans geometry is actually we can get the trans geometry, because we can say that okay, this unit is coordinating to this diboron and cleaving this. However, in the other case, we got a cis isomer where we possibly expect that simultaneous coordination of both the nitrogen atom to this one. So in order to clarify this, we actually did a crossover experiments with one equivalent of diazobutadiene and with 0.5 equivalent of B2-Cat2 and B2-Cat2. However, we did not see any crossover product. Like we did not see the compound 4, which is only having a B2-Cat2 unit, where we obtained in 38%, and the B2-Thio2 unit of 62%, which clearly indicates that this is not the intermediate. The reaction is proceeding via to give this trans product. So still, this is the only possibility of formation of cis product in the diisopropyl unit is possibly due to the favorable hydrogen bonding and the mesityle group where the hydrogen bonding is lacking. So in order to further confirm that cis product formation, we went on with the dimesytyl acinaphthalene compound, where we restricted the carbon-carbon rotation in this cis isomer. And then we reacted with the B2-Cat2, and here also the reaction was very quick, and we only get this the boron-boron bond cleave with the cis compound. This is also been confirmed, and here also we see that the evidence of hydrogen bonding from the proton NMR spectrum. So with this, I will conclude this work with where we actually taken this diazobutadiene derivative. This is one class of reagent which can actually cleave this boron-boron bond homolytically by the coordination of nitrogen atom to the boron atom. Although this is not going to radical mechanisms, this is we conclude that this is proceeding via a concerted reaction pathway where the 6-membered intermediate is 6-member transition state is possible, and the boron-boron bond cleavage is also accompanied by the formation of new pi bond in the DAP unit. The geometry of across this double bond is mainly because of the substituents at the DAP, nitrogen atoms, and also it is mainly because of the intramolecular hydrogen bonding. So with this, I will actually move into a different type of work, which is also other part of work we are currently working in our group. Our group also carry out reactions of, exploring the base metal catalyst for the borylation reactions. So I would like to brief a little bit about the our recent result on iron-based catalyst for the borylation of unactivated alkyl halides.
Geeta, sorry to disturb. You may take more time because I think we may have to conclude. I think considering the time.
How much time I have, Nagendra?
Yeah, I think like already we are well above the time actually. I think 10:15 should have been the ideal time, but yeah, so.
Okay, if that's the case, then maybe I will just skip this one.
Yeah, a very brief idea you can give, and then maybe you can conclude. Yeah, if you can. Yeah, that's the request.
Okay. Yeah. Okay, so our group is actually working on cobalt and iron-based catalyst for the borylation of alkyl aryl halides. And I just thought of highlighting this work because this is our recent work where the important of this work is that so far the iron catalyzed borylation reactions report mainly used this very reactive organometallic reagents, and in our case we have we just used a mild base and we could actually achieve alkyl halide borylation of borylation by using an iron catalyst, and our catalyst is it's a iron amide, which is easy to prepare and the stable compound. So there's here is the optimized conditions where we, as I mentioned, that iron amide is the catalyst which is being used in 10% mole with a simple base of sodium ethoxide. And we actually optimize the reaction conditions for various primary, secondary bromide, chloride also. And then we also found that the system is very efficient for the tertiary bromides as well. Here are some of the substrate scope. As you can see that it is very well with the bromide, primary and the secondary bromides. And then we were able to also get this chloride substituted compounds in a very good yield of the alkyl borylated compounds. So the mechanistic study clearly shows that the reaction actually proceeds via the radical mechanism. So with that, okay, I would move on to the acknowledgement. I would like to thank all my students for their efforts, and particularly the work of diazole butadiene cleavage was carried out by Piyush and Naresh, and the iron is recently being developed by Shima. And I also would like to thank all the funding agency, IISc, SERB, Inspire, CSIR, and STARS for the financial support. And I thank all for your kind attention. Thank you.
Yeah, thanks, Geeta, for a nice lecture. I hope like you can take a few questions, but I think time is running out already. So maybe a single question we can take. Professor Murugavel, please go ahead. Professor Murugavel, you are muted. Actually, please unmute and ask your question.
Geeta?
Yes.
Good talk. See, in the last part, you are using an iron bis-hexamethyl disaccharide as a catalyst.
Yes.
The advantage what you get by using sodium methoxide or sodium methoxide in place of alkyl lithiums and grignards is lost by using such as air-sensitive compound. You said it's sensitive, is stable. I don't think so. All metal amides, 2-coordinate amides are, I think, quite unstable.
Iron 2 amide is quite a little bit unstable, but this was also achieved with the iron 3 amide, which is actually similar. I mean, the iron 3 amide compound also gave same.
Oh, you're using iron 2 because your slide says iron 2. That's why I'm asking.
Iron 2, we mainly focused, but Iron 3 also gave us a similar,
Okay,
same
thanks.
ratio. Yes, but Iron 2 is quite unstable.
Quite unstable. I mean, all metal amides are unstable.
Yes.
And especially two coordinate system of iron, cobalt, nickel, all of them are even more unstable. Thanks.
Yeah, thanks. Sakya, yeah, you can go ahead, but please be very brief.
Yeah, thanks. Hi, Geeta. Nice talk. So, how do you compare the reactivity of your diazobutadiene with N-heterocyclic carbons?
Okay. N-heterocyclic carbons, you see that they are actually, if you do the reaction of N-heterocyclic carbons with any kind of diboranes, there are examples that B2PIN2, they undergo different type of reaction, like ring expansion reaction. They don't actually homolytically cleave like the way what is this diazobutadiene does. If you see that N-heterocyclic carbene, where one of the boron get actually inserted between this carbon nitrogen bond, so the reactivity is completely different in case of NHC with the diborane.
And any idea why? Any idea why does they do? Why do they behave differently?
That's maybe because that this is not that very strong base as like N-heterocyclic carbene.
Yeah. Okay. Yeah. Yes, Sakya. Thanks. And yeah, thanks, Geeta.
Thank you.
Yeah. If there are no more questions, I would like to conclude the session by thanking all the speakers, Francois, Yang, and Geeta, for giving excellent lectures. Further, I would like to thank Krishnan for providing an opportunity to chair the session. Yeah, Krishnan, please, you can take over.
Yeah, okay. Thank you, Professor Nagendran, and also all the speakers of this session. And we also would like to invite all the participants who have joined a bit late, and good morning to everyone. Okay, since we are running a bit late, so we will start the next session immediately. So the chair for the next session is Professor S. Natarajan from IISc. Professor Natarajan.
Thank you very much, Professor Nagendran, Professor Krishnan, for this opportunity to chair this series of important meetings, which has been, I think, second in the series now. And the first speaker of this particular session is Professor
Natarajan, Geeta should unshare her screen. Geeta.
Yeah, but I am trying. I'm just trying to close it.
First to put escape. Let us first come out of the full screen.
I did
first.
everything.
Then you start clicking what other probably should work.
I did.
Okay. Okay. So the first speaker in this particular session would be Professor Murugavel. And Murugavel is someone who is very well known for this community here, not only in India, but it's also in abroad. And it's a great pleasure to chair this session. And Murugavel, the floor is yours.
Thanks, Natarajan. Thanks for keeping it short, so that I'm starting 5 minutes to begin the schedule.
Oh, okay. Okay.
I'm just kidding. Yeah. You can stop me whenever you want. Okay. So I have to share the screen. 1 second. Start broadcast. There I go.
Yeah.
PowerPoint. Yes.
Yeah, there
okay.
Okay,
good. So let me begin by thanking the chair first, and then the organizers, Krishnan and Sharnappa in particular, for fighting hard and having it 1 year late and not abandon it at all. Many conferences got abandoned. For example, my own Goa conference has not been done for 2 years. But I like the spirit in which these guys have postponed by a year and then holding it online. I'm just going to slightly, to be more generic than the title I've given here. I thought looking at the talks which I've been listening the last 2 days is morely main group based stuff. Talking a 40 minutes lecture on magnetism would be probably overkill. So I'm going to still have magnetism. I'm going to enclose it in a much broader, wider topic where I'm going to talk about the esters of phosphoric acid, be it alkyl or aryl, and their use as precursors in new generation phosphate materials for energy, environment, and whatnot. Okay, so I also take pleasure in dedicating this lecture to Professor S.S. Krishnamurthy, who would be turning 8 in a few months, actually, in 2022. Actually, those of you who have been listening to the lectures, I think the last couple of days, would have realized that at least, if not more, about 60% of all lectures that have been given are given by either Krishnamurthy students or his grand students or his grand students. Okay, so Krishnamurthy kind of symbolizes the main group of the P block main group chemistry in India. So he would be turning 80 next year. So happy birthday, sir. Okay. See, it's nice that Natarajan is chairing the session. I think he's one of the early guys who worked on metal phosphate framework materials extensively when he started his independent career in JNC. Phosphoric acid is, as you know, is a tribasic acid, 3 protons. You can kind of kick them out one by one and make a dihydrogen phosphate, monohydrogen phosphate, and orthophosphate anion. And these forms can combine readily with metal ions under a variety of conditions. You have to underline this term, variety of conditions, because the medium could be acidic, basic, neutral, okay, and so on and so forth. Okay, it could be aqueous, it could be organic. As a result, what happens is that these reactions are often uncontrolled, mostly often uncontrolled. However, as Natarajan and Professor Rao has shown in the late 90s, I would say, that by using a suitable template and amine, you can actually drive this reaction towards more open framework solids rather than the condensed metal phosphates which have been exposed to for a very, very long time. So these framework solids, however, would have these are essentially anionic frameworks with the cations occupying often the pores or the extra framework space that is available within the structures. Okay, much of these reactions are carried out at high temperature and high pressure. As a result, I think phase purity you can actually direct. I'm not saying that's not the best way to do it, but obviously what happens is that impurities in multiple phases are something which you can avoid when you can perform this reaction. Okay, the status of this science when we actually really jumped into this area has been reviewed in a couple of times. The chemical reviews which is shown here kind of summarizes much of the work done by Natarajan, Professor Rao, and us on metal phosphate chemistry until that time. And the accounts article 2004 talks about is more of a concept rather than an article on published research, where we talk about how a bottom-up approach in material science, especially in metal phosphate chemistry, would yield much better results than what it is about 16 years back this was done. Since then, a lot of things have happened. Okay, so this is a very, very old molecule. As I said, is a very old molecule. I'm going to tell you just 4 short stories about 7-8 minutes of each. The first story would deal with monoaryl ester. You have been seeing these organic substituents in the last couple of days. Again, a recurring theme in mineral chemistry, the 2,6-diisopropyl or DIP, which is more famously called as DIP phosphate. And the second modification is just compromising this aryl group and the stability by somewhat an unstable ester, where you put a methyl ethyl propyl simple an alkyl group on the phosphoric acid. That's a story 2. And the story 3, I would talk about if we increase the number of alkyl groups on the phosphorus acid. So from tribasic acid go to dibasic acid, now we become a monobasic acid, more like a carboxylic acid. And then finally, if time permits, only if time permits, if Natarajan is kind enough, I would talk a little bit about the story 4, which is actually a deviation from the phosphate esters, which is phosphonamides. Much of its chemistry has been yesterday dealt with Bhumi in his lecture on the palladium clusters. Okay, so let me, I think with this short introduction, let me just directly jump into the story of diisopropyl phosphate. This can be made in multi-gram scales. Actually, often, if you have a good pair of hands, you can make it in one go about 70 grams, 80 grams, even 100 grams. And is perfectly stable for many, many years. You can store in a bottle and then use it. Okay, so we use this as a building block. I'm not going to go to much of this cartoon what is shown here. So essentially, we thought that we can start all the way from the left. Let me just take the all the way from the left, the phosphate anion, and build smaller rings and put the ring over ring and make cages and turn the cages into zeolitic materials. So can this be done in a laboratory? Unfortunately, as I said before, if you mix phosphoric acid and a metal salt, you are going to get a continuous metal phosphate within a few seconds. The precipitation, what most solid state chemists do. Solid state chemists normally precipitate metal phosphates from two aqueous solutions, one of metal salt, other one is of that the phosphoric acid. Okay, so we have been fairly successful, if not fully, in realizing this target of starting from all the way in the left and moving all across and then going to the right and making zeolitic solids. I'm just going to take only a couple of examples that are published in more recent times and highlight this. For example, this phosphoric acid, I put N minus because the parent acid is a tribasic acid, whereas my ester, where I have compromised one of the hydroxyl groups by an aryl oxy group, is only dibasic, so it's 2 minus. So when phosphoric acid is combined with aluminum, it forms AlPO4 because Al is a 3+ cation and PO4 is 3- cation anion. So the moment you compromise one of the acidic protons by an R group, now you have to look for 2+ cations, and they are plentiful, I would say, in the periodic table compared to the trivalent cations, which are more stable. In fact, aluminum we leave, I think we have very few: scandium, yttrium, and lanthanides, and expensive gallium. Okay, otherwise, so the phosphoric acid chemistry is rather limited to very few trivalent cations. Now, but you have the entire first order transition metal series open before you the moment you make the monoester. So we did this, we took the monoester and reacted with the metal acetate, zinc, cobalt, manganese, or whatever it is, and then you form this 4-4 ring, which is one of the most commonly occurring building blocks in many of the natural as well as synthetic zeolitic frameworks that we know. Okay, so by performing the reaction in the absence of any huge donor ligands, only in methanol, you make a transient molecule, which is a methanol cubane, and use collidine. You can use any base for the matter. I think collidine has 3 methyl groups. It gives an extra solubility to the system, so you can make lots of crystals and convince yourself and others that you do have a discrete molecular cluster rather than the 2D layered solids, what people like Clearfield, and Alberti, reported in the 70s for the corresponding phosphonic acids. The phosphate esters thus behave differently from the phosphate esters. Okay. As I said, I think it's just not restricted to zinc. You can essentially, if you have a good pair of hands, as I said, I think you can just move across the periodic table and make all these T4 cages. Once you make cages, then this published work, I'm not going to go in the detail. You can just arrange them in 1-dimensional, 2-dimensional, 3-dimensional motifs by just using hydrogen bonds as the glue. Okay, as you can see from the title of the slide, you just use hydrogen bonds as the glue because apart from the pyridine hydrogen, what I used earlier in the collidine, now I strategically put an ortho amino or ortho hydroxy, ortho ethyloxy or ortho methoxy groups. As a result, I can form a defined number of what I call as the intracubane and intercubane hydrogen bonds, and using this you can make the solids. I think this is, as I said, is a old work. And subsequently, we even used the morph strategy of using a ditopic spacer such as bipyridine, not restricted to only bipyridine, anything like a bipyridine, and then you can take these cubanes and just see them as a tetrahedral structures, phosphorus being ignored just for the sake of understanding the structure. So essentially, anything which is tetrahedral will give you a diamondonoid network, like Yagi's famous MOR5 system. So you can build diamondite. This is the more of a blackboard strategy. Actually became a reality a few years later, where we could use leaving groups such as DMSO or methanol, and incoming groups such as bipyridine and bipyridine derivatives. This could be anywhere between 7 angstroms to 25 angstroms in length, the end-to-end or end-to-end distance. And then you can make isomeric systems. As I said, it could be either diamondonoid or could be even other kind of solid state lattices, what we know of like Kagome lattice in the solid state. Okay, so you can make much of this porous solids and do some science over this, catalysis if you want, and gas absorption, other things. But however, I must warn you that I think these are heavily organic group decorated systems. These are more hydrophobic than hydrophilic. So the utility is, I think, restricted to some point. If you closely followed what I've been speaking for the last few minutes, I've been always making connections between one zinc from a cubane to another zinc of another cubane. it is always zinc to zinc connections. Okay, so it's essentially you are left with the 4 connected networks. In the later years, when actually Kamla started to work on para-substituted systems of this dip phosphate, she elegantly shown that phosphorus can be linked to zinc of the other cubane. So essentially, you can go from a 4 to 8 connected networks. And we showed this. Again, I'm not going to go into the details. So this is the modification she did. She chose to put an amino group in the para position. This amino group, this result is exactly same as the one what did about 10 years before this piece of work. But the difference is that you are decorating this cubane with 4 different amino groups, which is just dangling out. And then you can get a little bit more creative and convert. I think I just skipped the slide. I think you are using here a tetrazine bipyridine elongated system and build frameworks. But what is more interesting at a later time, what we did was we converting this amino group into an acetyl group by just a simple reaction with an acetic anhydride. And this particular system, in a 1-part reaction, you take this ligand and take this zinc acetate and mix it together. So essentially, you form a cubane with the 1, 2, 3, and 4 dangling, acetyl groups. So the phosphate forms, 4 bridges, and the acetyl group forms 4 bridges. So you have 8 connected networks coming from, and this system beautifully crystallizes. And you can do a crystal structure. And again, as I said, you can convince others that I think you do have a system where all the 8 corners of cubane are connected to 8 more cubanes and make much more robust systems of this type. Okay. And the interesting point is that the NH groups in this, acetyl group point towards each other and form a beautiful hydrophilic surface or hydrophilic well, if you want to call it as, in these zeolitic systems, which are very different from the first set of molecules I described before, which are more of hydrophobic. So you can essentially play between hydrophobicity and hydrophilicity by switching between a para hydrogen containing phosphate and a para amino containing phosphate. Okay, just moving on. Then strategy 1 was to use hydrogen bonds, and the strategy 2 was to use ditopic spaces as bipyridine and tetrazine separated by pyridines. And a third strategy, if we can put 4 amino groups in the para position, why not put all other functional groups? So we started decorating these cubanes with cyano, formyl, amino, and so on and so forth. This is just one example before I move on to the next story, that I think you can put a formyl pyridine in your reactions of using choline, and then you can get a tetraformyl cubane. So that can be truncated for a better understanding as a tetrahedral zinc cluster with the 4 formyl groups. Pretty much like what the COF guys do by combining bisamine or triamine or tetramine with the corresponding the aldehydes. You can make a imine based COF systems, but starting from a phosphate cluster. So essentially, this what I would call it is a more morph like COF in the sense that you're forming a formyl amine condensation to form an imine. Morph in the sense that it is still a zinc cluster. Pretty much akin to the MOF5 of Omariagi. Okay, so this is what we do. So you make this tetraformyl system and then use this. It could be any benzidine and benzidine derivative, tetraisopropyl. I think I probably have here. So you can buy some from shop and you can synthesize a few from your own lab, and you can use any of this hindered and unhindered benzidinic or paraphenyl diamines as spaces and build. The beauty about this system is that you have this in each hexagon you have a 6 × 2 12 ship-based linkages within the system, and this could be used to harvest metal nanoparticles and do further studies. The next slide probably talks about a little bit about it, but I'm not going to really get to the details. I think you can do a bit of catalysis and other things. Okay, moving on. The other thing is that you can also pre-synthesize. Actually, this is another strategy. Pre-synthesize. Let me just quickly go back for a second. You can pre-synthesize. You can take this amine and react with the pyridine, not pyridine, the aldehyde, the CHO, this pyridine. Form the ship base before and use the ship base, and then you can actually do this reaction 2 ways. When you do in the first strategy of cubane plus linker, you get a not so very crystalline system, much more like COF. But if you do the other way around, you are a MOF chemist now, you can actually make single crystals and you can solve the crystal system of the systems. And the chip bases, what I talked about, are sitting in all these places. Okay, so essentially now we have ways of making cubanes, decorating the cubanes with the functional groups. You can use hydrogen bonds, you can use covalent coordinate bonds, and you can use imine linkages to put them together in 1, 2, and 3 dimensions and make porous solids, and you can use for a number of purposes. And on another day, I would have given this as a full lecture, but now I just want to move on from here. And just to show that, I think there's a burning question while we are carrying out all these reactions. How does these structures really form? Is there a spontaneous self-assembly of 4 such zinc cations and 4 phosphate anions coming together and form a cubane? Or there's some kind of hierarchy at play where you just form one link and then forms a ring, and the ring forms a double ring, pretty much like the cartoon which is showed in the beginning of my lecture. So you go step by step from a discrete tetrahedral molecule to all the way to big structures. Okay, there's a number of there's 2 students or 3 students who worked in the last 7-8 years have knowingly or unknowingly or directly or indirectly attended to this problem and synthesized, I think, 2 important polymers. Again, I'm not going into the details. One is a square wave polymer and the other is a staircase polymer. So if we have 2 4-member rings that are formed, and this is P double bond O and this is zinc, they should actually come face to face and form a cubane. This happens all the time. 99% of the time, when you set up a reaction between a phosphate ester and any metal cation, you get a cubane. That's a solid, a product you get every time. That's what is preferred. Although the symmetry will tell you that the P double bonds would like to be trans to each other rather than cis. So assuming that they are trans to each other, then you will have this one side is being fused and the other side being open. As a result, you will have a tubs form. The tubs combine and tubs grow and to give us what is called a square wave polymer, what we are taught in during our +1, +2 mathematics. Okay. Suppose if this doesn't happen face to face and it makes in a more randomized way, you will end up in a staircase polymer. This particular polymer is more interesting for further studies because if we can take this polymer and use a suitable template, I think these are crystal structures. These are just not cartoons. You can actually make these molecules. So the key lies in the conditions and the substituents. The details are not important today. Okay, so you can actually direct these reactions towards either a square wave polymer or a zigzag polymer or ladder polymer, and take the ladder polymer, and then at any as the polymer grows, if we can cut this polymer at any point of time by using a template and then cyclize it, is what you take this P double bond O and bite this zinc, and take this P double bond O and bite this zinc, you should start getting structures of this type. Okay. Which are called double 6 rings and double 8 rings, which are known in 0D structures. Double 6 are quite prevalent, whereas these are not so very common. There are a few, maybe a handful of zeolites, 5, 6 natural zeolites, which do have a double 8 ring, but the molecule systems were not known prior to 2016, 2017. Okay, that's when I think Sandeep managed to make these compounds. Again, the details I'm not going to go in, other than to say that water was used as a template of all molecules, which goes and sits. Okay. And coordinates and form a double 6 ring, and use a molecule of acetonitrile by making acetonitrile go inside and encapsulate and make. So essentially, you can use a water-assisted or acetonitrile-assisted cyclization of this. Either the single 6 rings form and then they dimerize, or you form a single 4 ring and then it grows as a ladder polymer and then cyclizes to give you. These molecules are extremely stable. You can actually, as you can see from the mass spectra of these compounds, you can actually remove one by one these periodic molecules, and still the cluster does not, really. So the reason why I'm talking about this molecule is that you saw in my first part of the talk, first part of this story, that you can take a 4 molecular systems, D4R systems, and make 8 connections. So this has got 12 vertices and this has got 16 vertices. If you can only find ways of combining these double 6 rings and double 8 rings to form framework structures like MOFs, you would have new topologies emerging in the coming years. This is a topic probably we have moved away in the recent times because we got busy with other things. But I think this is still worth the problem to investigate whether you can have a 12 connected and 16 connected, phosphate frameworks in the future. Okay, that is where I'm going to close this story. So this is what happens. You have this and this grows this way. And at any point of time, you cyclize the system, and probably you can even make bigger systems. This is actually my colleague Naresh Patwari did calculations on this system, and he feels even D10R is not an unrealistic target. One day we should be able to do this. So quickly, the second story is I would say a short story. This is, I think, for many years we have been wondering about the possibility of substituting the aryl by alkyl, because having only one alkyl group on the phosphoric acid does not present a very stable system. Often these are prone for beta hydrogen elimination because an alkyl group is essentially a CS2, and CS3. Okay, the beta hydrogen is closer to the oxygen, so essentially an alkene is given out and undergoes essentially get a phosphoric acid back. However, I think there were some literature reports. I think so. Gulzar, who joined somewhere in the mid 2014-2015, worked on the systems, and then he could stabilize. I mean, they were reported earlier, but they were kind of described as a very unstable species. So, if one is going to make these kind of clusters, how are these going to behave? Are they going to behave to their phosphoric acid cousins, or it's going to behave more similar to the mono aryl phosphate esters? So there was a question. In fact, I think the mono alkyl esters try to be closer to the mono alkyl phosphoric acid rather than the aryl phosphate esters. This is what happens. This is again a long story. It started by Gulzar. Now there's another student by the name Anuj is working on this and expanded this chemistry to alkali metals, alkalinate metals, and so on and so forth. But I'm just taking one single example where we have used copper as the metal. This work partly done with Vaidyanathan's group in IISER Pune, who has done this supercapacitance work for us. Okay. Anyway, I think when you combine these identical conditions to that of the aryl phosphates, what I described in the story number 1, but the result is completely different. No double 4 ring, what you have been getting last time. What you are getting now is a layered solid. So this is an alkyl methyl compound, this is ethyl compound, this is isopropyl compound. All three differ only in the inter-layer distance by about 0.1 nanometers, okay, 1.2, 1.3, 1.4 nanometers, because you are adding a carbon extra when you go from left to right, okay? So this is the compound. The beauty about this compound is that you can take this compound, okay, I think you can decompose this. I talked about thermal instability. So this is the powder XRD of this compound, which is the metal organic polymer. You heat it to 200 degrees centigrade. As you can see, at 200, there is an action here going on. At 200, you lose all the organic part, namely the methyl, ethyl, propyl as methane, ethylene, and propene, and make a solid state metal phosphate material, which only goes on to crystallize, okay, with the time and with the temperature. At 800 degrees centigrade, you get nanocrystals of the corresponding metal phosphate, which is the pyrophosphate, Cu2P2O7. Okay, that's what on a normal day I would have done. But what struck me was that I think this, if you have two phenyl groups, there will be a pi-pi interaction between the layers, and the layers will be held together. When we took this, we could grow single crystals and do the structures. However, when we took the single crystals and saw under a same micrograph, it is like, more like a mica structure, actually, such a beautiful layered solid. It is a single crystal, but still you can physically see these, layers. So we are intrigued by this, ease by which you can actually, separate these layers into single sheets. In fact, I think, sorry for this font. I think why this font is so smudged. You sonicated either DMF or ethanol or propanol, whatever solvent you have. Essentially, you can make this single crystals go into single sheets, and the single sheets, as you can, as you would expect to show Tyndall effect, they do show, and these are indeed single sheets, we thought, and then we went on to further investigate this. And these again studies done by Gulzar with another student of ID in IISER Pune, where you have done the kinetics of exfoliation. I keep it short. So you start at 0 time and exfoliate over 40 minutes at 15%, if I remember correct, is the power of your sonicator. You essentially get a height of about 1.5 nanometers. So you can see that it's just not one. You can pick a colony of plates and measure its height profile in the AFM, and really see that it's somewhere between 1 to 1.5 nanometers, which are single sheets. So at 40 minutes of exfoliation, you do get just a single sheet metal phosphate. Okay, so you can also follow this also by ex situ high resolution TEM studies. This is one of the single crystals high resolution TEM, which is about, you can see 100 nanometers is the scale that is shown. So it's really a large crystal, which is the bulk, which is very, very dark image. Okay. Now you take this and then somewhere go and park yourself somewhere here. Some amount of exploration has been achieved. Now, if you look at its time, you already see that the images become lighter. You can actually see through the layers. Actually, I don't know whether you can really see. You can see through the layers in this STEM image. And now you go on and completely exfoliate it after 40 minutes at 15% power. You actually get a single sheet. Okay, the corresponding SAED, microgram and the diffractograms clearly tell you a single crystal versus a partially exfoliated the ring pattern, diffraction pattern with almost no spot containing diffraction pattern. Okay, so I think I just wanted to tell you that you can actually pick up the cell parameters and match it with your single crystal structures. I think that's not important. So again, these are details of how we went about. I think using a 3-electrode system and using 70% of the material and some support and binder, we constructed electrodes. And found that I think the neutral sodium sulfate is a better medium to construct our capacitors and supercapacitors vis-a-vis an acidic medium or a basic medium. Acidic medium is bad. Cycling shows the drop in the intensity. Okay, the current intensity falls, so it's not good. The base is not bad. However, as you can see, the rectangular opening of the CV is not good in the case of basic medium. So we did all our experiments in the near neutral conditions in 1 molar sodium sulfate. Okay, so again, these are details. You can take the bulk sample, you can exfoliate, you can bulk sample, you can burn it, or you can exfoliate and burn it. So this is bulk, exfoliated, no, bulk and bulk burnt and exfoliated and burnt. As you can see that in the next slide. So the topmost curve is the one which is exfoliated and burnt. So essentially what you've done is you've taken a single crystal, pretty much like the graphene was removed from the graphite by using a Scotch tape. Now here you use sonicator and taken one layer and put it on a substrate and heated it at 300 centigrade, and you formed a single layer metal phosphate material on a glassy carbon and constructed the electrode. So this is your at 10 millivolts per second CV shows the best result for the 300 degrees exfoliated sheet, and you can see the charge discharge curve is again very good for the exfoliated sample. And the recycling, again, you can see that the numbers are not very high. So the capacitance is not very high. This is not the best super capacitor one can build, but the idea is important. You can take a 2D layer material, peel it layer by layer, and make a 1D metal phosphate material on a glassy carbon, and then build a device, and that performs better than the bulk material. I think that's what is the, and these are again details. I think as you can see, I think the electrical double layer and the Faraday capacitance has been factored into 71%, 29%. Generally, this is turned out to be a good method of enhancing the supercapacitance by making a 2D layer solid. Okay, now quickly jumping into, I have 25 started. 35, okay, I'm at 29 minutes. Okay, so the second, the story number 3 is actually I'm just loading an extra alkyl group. Earlier I had a methyl ethyl propyl monoalkyl phosphate. Now I'm increasing the stability, I think, by putting a second tetramethyl group. Exactly the reverse happens. By putting a second tetramethyl group, now you have 18 beta hydrogens available for its self-decomposition. So there are 18 beta hydrogens. So this compound is far more unstable than methyl or ethyl or propyl monoalkyl phosphate, what I spoke in the story number 2. So this is, in fact, my entire journey with the phosphate chemistry began in the beginning of 2000, 2001 with this system. And we showed over a period of time that you can make ditetracybutyl phosphate polymers of this type, because unlike the previous case where you had 2 OH groups giving a 2D sheet, here you have only 1 OH group. This ligand is more like a carboxylic acid or benzoic acid. Like a benzoic acid form a chain polymers. This compound, or a phosphinic acid for the matter, diphenyl phosphinic acid, this would form more often than not 1D polymeric chains. The beauty about it is that it has an inorganic core and decorated by an organic sheath above and below, or I would say around it. I mean, the way is a 2-dimensional representation. So it's essentially is like a steel pipe coated with acrylic organic paint. So what is inside is inorganic, what is outside is. So when you start heating the sample, the organic part says bye-bye at a very low temperature, 150 degrees in this case, for cadmium phosphate, and forms a ceramic phosphate at temperatures as low as around 300 degrees centigrade. If you want to make a cadmium, PO3 to metaphosphate, you would require temperature about 700, 800 in a conventional way. But here you can make it at even at 300 degrees centigrade. Okay. So as I said, this is a well-studied system in my laboratory. We have written a lot about it. I'm not going to talk about it. But what happened in the recent times is that Sonam, recently working for a PhD, who just completed, wanted to actually expand this chemistry from beyond transition metals, and then she chose such a stupid starting material like calcium hydride. So this phosphoric acid diester can be neutralized just with the calcium hydride and form a calcium polymer. The cation being bigger, you have two more water molecules which are there. So this is essentially the polymer, which is a linear polymer, inorganic core and an organic sheath. And its thermal behavior is pretty much similar to the earlier one. Only thing is you have the water molecules which are coordinated walking off first. Then here you have isobutene. Then there's a condensation. So you can follow this by an in situ or a ex situ, high temperature powder excited studies. This is a polymers, and then you just go, increase the temperature from 200, 400, 600. At 600, you form the alpha form of the metaphosphate, and just don't relent. Just keep heating further and further. And about 800 degrees centigrade, you form the beta form. So essentially, this clever student of mine actually didn't stop with just making two different forms of alpha and beta phosphates. She went on to, I will skip this for want of time. She took this one polymer and made 1, 2, 3, 4, 5, 6, 7 different forms of calcium phosphates, of which I would pick this particular, not that one. Where is that? This one. I'm sorry, this one. This is the hydroxyapatite, which I think is used in a lot of bone transplant and in the dentistry to a large extent. I think hydroxyapatite. We could make this from in solution as beautiful nanocrystals. I think, as you can see, these are the hydroxyapatite nanocrystals. And so this kind of chemistry gives you the breadth and width, not only to make one side supercapacitors, but also you can use this kind of compounds, provided you choose the right metal ion. You make a very environmentally friendly and then body friendly, I would say, calcium metal, and then make useful nanocrystals of transplant materials, such as hydroxyapatite. Okay. Now the story, fortunately, does not stop here. And then we just went on to revisit some of our 2002 studies. I think about 20 years later, I think 2002, we published this particular compound where cobalt acetate reaction with dietitious phosphoester formed this polymer. Recently, again, with the help of my colleague Subbu in the department, we have looked at its electrocatalytic behavior for essentially, we can do many catalysis. Okay? I'm just talking only about one particular catalysis, namely the OER. So again, I'm going to cut a long story short. I think this goes through all the thing. So the strategy is that this is a material that is developed in Subbu's lab, which is what we call as a NCF or nanocarbon florets. Okay, it's like a flower. Okay, you can see there's a same picture, there's a temperature. So this is the nanocarbon florets, which have a large amount of voids within this florets. Okay, and then we actually perform the reaction in this particular florets by combining cobalt acetate and dietitious phosphate, and essentially form the polymer inside this thing. And for some reason, I think this was decomposed at 150, 200, and 250 degrees centigrade. And we went on to do this, electrocatalysis, and we found out that the compound which is in between performs better. I mean, I'm just telling the climax in the beginning of the movie. That is that the material which was decomposed at 200 degrees centigrade was better. So that kind of triggered an alarm. So we went back and looked at. We started to worry more about the compositions. When actually looked at the Raman mapping of these materials, which are heated at 150, 200, 250. This is a Raman spectrum of the pure dihydrogen phosphate, S2PO4, cobalt twice, and this is cobalt PO3 twice. And if you actually do the mapping of the sample, which is heated at 150, you see it's predominantly green, saying that it's mostly dihydrogen phosphate. The sample which is heated at 250 degrees centigrade is predominantly the metaphosphate. The one which is heated at 200 degrees centigrade is a physical mixture of both dihydrogen phosphate and metaphosphate. So once you realize this composition is neither this nor that, which is a mixture of these two, by actually forming histograms, this is the 150 material, this is a 200 material, a 250 material. The 200 material is a combination of, all the phases. Then it turns out that I think there's a large amount of work that has been done, both the likes of Nosora and Don Tilley from Berkeley on the active form of cobalt. I think actually which cobalt phosphate, which form is more active. It turns out that I think this particular study has shown us, thrown some more light into this studies that the manipulation of the Bronsted acidity, I would say, because the PO3 twice is completely devoid of Bronsted acidic sites, whereas the hydrogen phosphate is full of Bronsted acidic sites. You need to kind of really make a right balance between these two material, and you can make really again, I think for a point of time I'm not going to go through this. I think just go to show you the table. I think show that I think the material which is made that 200 degrees centigrade shows some of the lowest onset potential or over potential for any material that has ever been made, okay, for water oxidation. Among cobalt phosphate, this is the best, because as you can see, there's one more which is at 320 millivolts, but I think that is a highly basic medium, whereas all our studies are done under the phosphate buffer with a 0.1 molar solution and the near neutral conditions. So as a third application, I just shown you that one can actually not only build capacitors and make building materials, but can also use them as electrocatalysts. I think pretty much, I think I'm going to close this by leaving some time for questions. The story 4 is actually the phosphoramide chemistry, where you place the highly acidic OH group by weakly acidic NH group, and go on and step into far as at least an unexplored territory of molecular magnetism, which you started about 5 years back. And I just probably just show you the conclusion slide of the chapter, the topic 4. I think those of you who are interested, I think probably can have a look at, I think these two papers especially, which kind of summarizes our magnetism work. The one is just appearing in quantum chemistry, which is much more comprehensive and a more perspective in 2018 in ChemCom. So that will give you an idea about, but these are again made from main group molecules. So essentially, I think probably I've done some justice to the title of the symposium. Okay, how main group molecules can be turned into material. Phosphoric acid could be one of the simplest and most stable and easily accessible starting material one can think of, just by esterifying them with alkyl and aryl 1 or 2, making it tribasic, dibasic, and monobasic, and looking for the correct metals, main group or transition metals or lanthanides. One can actually kind of go into porous solids, batteries and capacitors, and electrocatalysts and magnets. So I think phosphoric acid chemistry is still not done and dusted. I think we still have a lot more to explore with this. I think let me thank my group. I think let me just kind of Gulzar, I think is here, who did the monoalkyl phosphate work, the supercapacitor molecules. Sandeep did much of the bulk of the D8R chemistry as well as the magnetism. Did not speak about it. Sonam is the author of all the calcium chemistry that is described. And I'm missing someone. I think the present. I think there are a lot of people. I think Sonam is again here, and then some of these people are working on now these problems. I'm looking for Anuj. Yeah, Anuj is working on the monoalkyl phosphates. I think, and some more magnetism work with this guy. So let me just again conclude by thanking all my former postdocs, PhD students, and everybody else, and generously thank the generous funding of my research through various projects, and Rajaraman for all the calculations, Subbu for electrocatalysis, Vaidhi from Pune for capacitor work, and the overseas collaboration with the Wensdorfer for microsquid, and Jacob Narus for high pressure magnetism, which I did not speak about it. So I thank you all for your passion listening, and if still there's, I have left a minute or two, let me take some questions. Thank you.
Okay, and you just left with 1 or 2 minutes. If there are any quick questions or comments on the presentation, it's welcome.
I'm already coming out of the presentation.
Sure.
So I don't have to probably go back and show something. Okay.
Yeah. Any comments from any of the participants?
Yeah. This is Anantraman.
Please carry on.
So it's a wonderful talk, sir. It's a wonderful talk. In fact, I thoroughly enjoyed from the beginning on the phosphate chemistry. But I'm a bit curious when you talked about the hydroxyapatite. have you anytime tried on the, like artificial model of, the taking this hydroxyapatite as one of the application for the any biological things? Have
Yeah,
you tried any of this?
there are a couple of chemical engineering groups actually, which we wanted to talk to them actually, how to use this, aqueous or semi-aqueous solution of this, and then actually grow, in a porous bone system, how to do a filling with these materials. I think it's to be done. I think by the time Sonam graduated and left, so I think probably needs to be done. I think the way we could grow this from solution within a few hours, these nanocrystals, I think we can definitely use them to, fill, especially the bones which are become very porous. I think can be strengthened using this at least in the laboratory.
Exactly. That's where the arthritis and other things. This could be one of the.
That's the word, arthritis. Yeah, I was not getting the word.
So,
okay.
Yeah. Yes, so that's one. And second part is, it's a fantastic thing, and you have done the ring expansion from the zinc to like other things by taking the COF approach and other things. But have you also parallelly tried on the phosphorus center, like the phosphate group OR to something else?
So that miserably failed. No. That's a 15-year-old unsuccessful story. Using. Mari is also there in the slides. Marimuthu has been working on diphosphate esters, and bisphenol, putting 2 phosphate esters. So these, miserably failed because of solubility reasons. Actually, unfortunately, we are not able to keep the solubility going.
Okay.
We get amorphous material all the time. No, we are trying for 15 years now. We have some success, but not to the extent of doing the metal expansion. It still is through the bipyridines and the imine linkages through phosphorus is still tough. Yeah.
Okay.
But that's what we indirectly done through Kamala Soka by having acetyl group in the para position. It's not both side phosphate. One side phosphate, other side is acetyl group.
Yeah.
It's essentially the same. Yeah.
See, in the interest of time and to maintain, because we still have some more lectures to go, I would, on behalf of the organizers, I would like to thank Professor Murugavel for a very fabulous, fundamental, and exciting research. Thank you very much, Professor Murugavel.
Thanks, Natarajan. Thanks. Nice to see you after a long time.
Yeah, well, I'm here always.
Yeah.
Okay.
Yeah. Bye.
Sure. Bye. Yeah. So the next presentation today is by Professor Arnab. And Arnab, are you around?
Yes, sir. Yes, sir. I'm here.
Yeah. Please carry on. Start. So that we'll, you have half an hour. So if you can finish it by about 25 minutes, we'll have 1 or 2 minutes to have an active discussion. Okay.
Okay. Can you see my slide now?
Sure. Yeah. Please continue. Yeah.
Okay. Very good morning to one and all. And first of all, I would like to thank the organizers, especially the Krishnan and Saranappa, for giving me the opportunity to present our research on the topic of metal complexes of inertocyclic carbon ligands and how the ligands actually impact their catalytic activities. Before going into the topics, I would like to give a brief introduction about the carbene. As you all know, carbenes are electronically neutral species and its derivatives, and in which the carbon center is covalently bonded to 2 univalent groups of any kind or a divalent group. And that the presence of these 2 electrons makes the carbenes more reactive. And inertocyclic carbenes, basically, this is a special type of cyclic carbene having at least one of these amino substituents, which provides the stability to this inertocyclic carbene. The story of inertocyclic carbene has started long back when Wanchlik started to synthesize that, but he was unsuccessful. Rather, he ended up with an alkene, which couldn't be disproportionated to the corresponding free carbene. And later, Ophuls and Wanchlik started synthesizing that. They got access of the corresponding metal complexes. However, the free carbene was still out of the reach until in 1991, Arduino isolated this inertocyclic carbene by using a very bulky adamantyl group. And after that, the chemistry of inertocyclic carbene started flourishing. So now there are several factors which actually controls the stability as well as the reactivity of inertocyclic carbene. The first of all is the inner atom. Because of the sigma electron neutron effect, it basically stabilizes this non-bonding sigma orbital, whereas the pi electron donation from the lone pair of nitrogen increases the energy of the p pi orbital and thus increases the energy gap between the sigma and pi orbital, which is commonly known as a push-pull effect. And this stabilizes the single state of the carbene. And further, the cyclic nature of the intercyclic carbene also stabilizes the bent singlet state. And initially, when Ardingho isolated the carbene, he was not sure whether the steric bulk or the electronic nature of the substrate is actually stabilizing the intercyclic carbene. So rather, it was observed that in case of carbene, its electronic factors are more important than the steric factors. However, this by changing this R substrate here, we could control the steric nature of the intercyclic carbene as per our need. And also the backbone substrate here, for example, chloro or methyl also change the sigma donation ability of the intercyclic carbene, and also the number of substrate in substrate and the position of the in substrate also affect the electronics of the carbene, which will come back in the later slide. There are several methods available to quantify the electronic nature of the intercyclic carbene. First of all is the Tolman electronic parameter, which is a very classic way for the phosphine. Here also, this also can be used for the NAC based chemistry. However, it needs to use the nickel tetracarbonyl, which is basically volatile and bit of pyrophoric nature, and also the limited resolution of IR method limits the use of this method. Later, Carty modified this method by using the corresponding iridium and rhodium complexes. However, still rely on the IR spectroscopy. So therefore, it limits the applicability of this method for a subtle difference in the electronic tuning. So recently we come up with an idea that we could basically use the 13 CNMR chemical shift for this carbene signal for quantification of the, or at least the qualitative identification of the electronic nature of the carbene. The advantage of this method, because 13 CNMR generally shows very little light bonding as well as shows greater accuracy than the other method based on IR spectroscopy. As you see here, so based on this coordination to the metal center, as well as if it's a free carbene, it's resonant more than 200 nanometers, and if it is a different types of carbene, and depending on the coordination to the metal center, it's the chemical shift value spans over 150 to 190 nanometers, and that gives us an idea about the coordination, this sigma donation behavior of the intercyclic carbene. So after this, Ardingho isolated this carbene, and this found application in widespread areas, starting from the material chemistry as well as the stabilization of the reactive main group species, and more importantly also in the homogeneous catalysis. And in homogeneous catalysis, these are the two main type of ligand, NAC ligands are utilized. One is of the individual NAC type, which is type of Ardingho type of carbene, and other one is the mesionic type of carbene. So we are basically interested in the hydride transfer reaction, and this simply because it is a key reaction in several important catalytic transformation. For example, different hydroelementation reaction like hydropotation, hydrosilylation, so on and so forth, and hydrogen storage or release, as well as the alkene isomerism process. So as this NAC ligand act as a very good ancillary ligand for this type of homogeneous catalysis, we thought that how this change in the NAC ancillary ligand affects the catalytic application of this complex will be interesting, because that will give us crucial information for the design of the future efficient catalyst. But when we looked at the literature, we saw that there are very few examples which studies these things in detail. This is one of the examples, as you see here, just by changing the orthometallism from the pyridyl to the phenyl ring, is basically changes the activity of the corresponding metal complexes. With the pyridine orthometallation, that catalyst is less active as compared to the phenyl-based orthometallic complex, because it is more electron rich, providing better activity. So then we thought of like synthesizing a series of orthometallic complexes where the electronic nature of the complexes could be varied by just changing this substrate here, or even the NAC donor, starting from the individual NAC to the triazole NAC. In the other system, we thought of utilizing this unsymmetrical chelating ligand, where the secondary donor can be changed from the triazole to the individual NAC or to the triazole. With this idea, we have synthesized a series of these NAC complexes, which could be isolated in very good L, and also could be characterized by common analytical technique. So we wanted to look at this, how this substrate change the electronics of these complexes. And here we see that when you look at this 13 CNMR chemical shift, is basically changed consistently with the change of the substrate. As you see here, this nitrosubstituent case, the chemical shift value is the most downfield shifted, whereas if you have the methoxy group, this is the least chemical shift values observed. Just to compare, we use the very classical method of this electrochemical analysis, which also supports the idea that the methoxy substituted group is the most electron rich, whereas the nitrosubstituted group of the complex is the least electron rich complex. So with this idea, we just wanted to check whether this subtle change in the electronic behavior of the metal complex would have any implication in the catalytic properties. So we chose the very simple reaction here with the reduction of this carbonyl group. And what we surprisingly observed that this catalytic activity basically changed substantially. As you see, the nitrosubstituted compound gave a yield of about 34%, whereas this methoxy substituted group gave a yield of about 95%. More importantly, when you plotted the percentage of the yield of the reaction with the chemical shift value, it changes linearly. So that shows as the electron richness of the metal center increases, for example, in the methoxy substituted complexes, the activity increases, whereas if you have a nitrosubstituted compound, their activity decreases. Now, why does it happen? Just for example, if you take the methoxy group, which is known to be a good pi donor, and therefore it actually donates some electron density towards the ruthenia by p-pi conjugation, and this is facilitated by the planarity, which is supported by the orthometallation. With this, we will move on to the second ligand system. This is the ligand system which could be easily synthesized starting from the alkynes substituted imidazole salt and the azide by simply click reaction. And from the NMR, we see that this is most acidic and could be deprotonated. That's what we see. We could synthesize the corresponding triazole appended metal complexes. But what you see that the coordination of the triazole could easily identified from the NMR, as we see here, is the diastrophic nature of this bridging CH2 group. Also, the parasamine proton appears as a 4 doublet, presenting indicating the loss of symmetry of the compound. Now, further, as we planned, this nitrogen lone pair could be alkylated, giving the corresponding triazolium proton, and then it will be like a bisazolium salt, and under suitable condition, it could act as a heterodiethyl ligand with a 2 different NAC ligand. And accordingly, we could isolate the corresponding metal complexes can characterize with the crystallographically as well as the NMR studies. As you see here, this clearly shows the coordination of 2 different carbon center. One is about 173 ppm for the ruthenium, and one is about like 160 ppm for the corresponding triazolidine coordination to the metal center. So once we have these 2 types of without one triazole, one triazolidine, we thought of synthesizing the very commonly utilized symmetrical BCNAC ligand, and we got the similar complexes. And if you see at the potential value, it suggests that this triazole-based complex is the least electron rich, whereas this triazolidine is the most electron rich, and this symmetrical BCNAC ligand coordinated complex is in between. This, when you track this reaction, here also we could see that this basically affects the catalytic activity of this complex. The complex 13 gives about 80%, whereas this triazole-based complex gives about 50%, and this symmetrical BCNAC coordinate complex gives yield about 65%, which correlate with this electronic nature as supported by the electrochemical analysis. Further, the similar tuning can also be possible in case of even reduction. With this, we wanted to understand why does it happen that electron-rich complexes provide better activity than the electron-poor. So what we did, and that the this standard reaction condition, but without any using any substrate, we tried to isolate the intermediate, and after about 20-30 minutes, you could isolate a compound where it clearly shows the formation of hydride, which is manifested from this peak at minus 10 point, around 10 ppm, minus 10 ppm characteristic for the ruthenium hydride. All the other signals supports this type of hydride formation. And this was supported by the ESI studies. And further, what we observed that this, when we treated this ruthenium hydride with the carbonyl compound, substantial amount of this alcohol formation was observed, which proves that is the real active catalyst in this reaction. Further, what we see that this electron-poor substrate undergoes faster reduction as compared to the electron-rich substrate. So that inherently indicate that the hydrate transfer reaction and probably the rate determining step. That gives us an information why electron-rich complexes are more active, because as the electron richness of the metal center increases, the hydricity of this ruthenium hydride bond also increases, which in turn increase the transfer of this hydride to the carbonyl group, resulting in a better catalytic transformation. So with this idea of like simple hydride transfer reaction, we took up a multi-step hydride transfer reaction. So this is a simple reaction between this alkylation of the alcohol, and this is basically a green reaction where water is produced as a only byproduct. But however, we're not sure whether we'll get the similar type of activity or not. We synthesize several other complexes, including also the 1,2,4-triazole as well as the nitro group. And when we looked at this chemical value, what we see the 14D complex with the triazole, 1,2,4-triazole as well as the nitro substrate provided shows that it is the least electron-rich complex. And with this idea, we applied all the catalyst in this reaction with a very low catalytic loading of 0.01 mole%. And what you see, this provides contradictory conversion in 8 hours. And from that, we could also get this 92% isolated yield. And all the other complexes perform shows inferior activity as compared to this complex 14D. And more importantly, the catalytic loading also could be reduced further. It goes to 0.001 mole% in 10 ppm level and providing the high Tonneau number of 68,000. So I'm not going to the substrate scope. There are all the different types of substrate, including the aromatic, heteroaromatic, as well as aliphatic can also be alkylated. And also with this low catalytic loading, this reaction can also be done in higher this gram scale reaction. So after having this monoalkylation, we thought whether we could do the dialkylation. As you see, once this position is alkylated, so reactivity of this CH proton gets decreased. And that's why the dialkylation is not very less reported and reported to be very difficult. So we then took the challenge, and indeed this catalyst catalyzed the second alkylation. However, we need a higher catalytic loading, which is quite reasonable. And further, we ended up with the ketone, which could be justified that as this double alkylation happens, the electrophilicity of this carbonyl bond decreases. So therefore, reduction of this carbon bond becomes more difficult. And further, we could also utilize the methanol as an alkylating agent to get the corresponding N-alkylated species, and diverse N-methylated compound could be isolated in butane. So we have done several control experiments to prove the mechanism. I'm not going to detail, but I would like to draw your attention in this reaction where we have used the deuterated benzyl alcohol. In this case, what we see that in the product, deuterium gets distributed over the alpha and gamma phase, which says that it is only possible if this deuterium gets transferred to the metal, and then in the last step, it is then this alpha beta saturated species gets reduced by the metal hydride. So that's why we wanted to see that whether it's really a metal hydride is acting as a catalyst. We similarly, and then we did the reaction, and in about 1 or 2 hours, we isolated the intermediate, and which clearly shows the formation of the ruthenium hydride species as here from the very half-fill shifted ruthenium hydride peak. And also it's supported by the mass spectrometric analysis. With this, we propose a mechanism for this reaction. First, this alkoxide is formed and then undergoes the standard beta hydride elimination to generate the hydride. And then parallelly, that diol condition between the ketone and aldehyde provide the alpha beta unsaturated ketone, and then it gets reduced by the hydride to provide the first ketone form, and then ultimately to the alcohol. So until now, I have shown you the reactivity of the monometallic system. But this now I'll move to the bimetallic system, especially the heterobimetallic system. It has many advantages because a multiple catalytic transformation can be done using a single catalyst, and more importantly, mechanistically distinct 2 or more catalytic cycle could be done. As you see here, this metal center M catalyzes the reaction from A to B to C, and then C undergoes further reaction and with the D and produces the product. But even though it looks like fascinating, but there are a lot of challenges. First of all, one metal center should not quench the activity of the other metal center, and the spacers should be strong enough to maintain the integrity of the complexes throughout the reaction, and also both the metal centers to sustain the catalytic condition of the two different reactions. Nevertheless, NEC has been found to support this type of metal complexes, and then here, as you see, this palladium is supposed to catalyze the CC bond formation, whereas the iridium catalyzes the N-alkylation. But the reported system actually uses the similar type of donor, so that makes it difficult to get a monometallic system and then go for the bimetallic system. We thought of using different donor, as we have this ligand, we thought of using this, but we face the problem because this bridging is so small that it just gives a mixture of product. So then we just increase the bridging spacer here using this phenyl group, and design this to have two types of ligand. So I'll move on to the first ligand. So in this case, this A compound A could be synthesized starting from the 4-aniline, and then the standard Ullmann coupling protocol will give this compound B, and then it's alkylated with the product ligand. When you looked at this NMR here, proton chemical shift, it clearly shows that this proton is more acidic, therefore selective deprotonation metallation is possible. Indeed, when you did the reaction, we could selectively get this iridium and palladium complexes, and in about 70 to 80% yield. So there is no problem of like a mixture of product formation. And as you see here in the proton number of the palladium complex, so there are two backbone protons still intact. So therefore, further metallation for the heterobimetal complex formation is possible. So these two complexes could be characterized crystallographically. But we are just thinking whether this change of the coordination mode here is just a palladium complex, whereas it's an iridium complex with the orthometallated, which change the these properties of this triazole backbone, where we have these two protons. Okay, so we looked at this in details, and this when you looked at the NOESY NMR of this palladium complex, it clearly shows this H3 proton is correlating with this aromatic proton, and H4 proton correlating with this ethyl proton. So that shows this H3 proton is here, which is the most downfield shifted proton. When we looked at this iridium, just scenario is just completely reversed. This proton basically correlate with this N-ethyl proton. That shows this C5 position is more downfield shifted. So we are curious whether this such a small changes in the behavior of this triazole proton will have some implication in the metallation behavior or not. With this, we just reacted this iridium complex with this gold as well as the palladium complex. What we see that this gold and palladium coordinate at the C4 position rather than a C5 position, keeping this position intact. So most of the literature reports says that one of these backbone positions are always blocked because it is normally synthesized by the click reaction between the azide and terminal alkyne. So they did not have this issue of this C4 versus C5. But in our case, we do have this issue. So then we looked at the literature in more details. We found only one example where both the backbone positions are unprotected. And in this case, they got the metallation at the C5 position. But here it is orthometallated. So we thought it might have some implication on the C5 coordination. Then we synthesized this complex, basically simple ligand, and then went forward with this palladium complex synthesis. Here, surprisingly, what you see, we saw the coordination at the C5 position rather than the C4 position, as we have seen here in case of iridium. So that clearly shows that this orthometallation from the iridium definitely has some influence on the reactivity of this C4 and C5 position, therefore controls the metallation at the this C4 position. With this, we also went on this heterobimetal complex formation from this palladium complex. In this case, what we see, the metallation happens at the C5 position rather than C4 position, what was observed in case of iridium complex. So both the complex could be characterized crystallographically, which clearly confirms the position of the metallation. So what we see here, that the coordination mode of the first metallation, whether it's an orthometallated or non-orthometallated, decide the position of the C4 and C5 of the second metallation at the 1, 2, 3 triazole ring. And this is a quite new mode of reactivity. What we believe will open up new area involving this unprotected 1, 2, 3 triazolium chemistry, which currently we are working on. For the second ligand system, we then went forward and we could clearly isolate the corresponding iridium and palladium complexes here. And it clearly still shows that the presence of this downfield shifted photon, which is still intact, that gives us a space for the second metallation, and these complexes could become characterized from the crystal structure and mass spectrum also. Indeed, we took this iridium complex, we could get the corresponding palladium complex also, gold complex as clear from this NMR. As you see from the 13th NMR value, it shows two distinct peaks at 170 ppm corresponding to this iridium carbon bond, and one at 154.5 ppm corresponding to palladium carbon bond. And this compound also we could get the corresponding crystal structure. So what the main idea of installing two different metals at the same ligand system is to see whether there is any cooperativity between the metal center here, between these two different metal here, here between iridium palladium or iridium gold. So to find out that, we first need to synthesize the corresponding diametrically complex where the same metal centers are attached and the two different metals are on the two different ligand system. So there is no sort of cooperativity possible between the metal center. For that, we have synthesized the homobimetallic complexes here. And as you see here, both the complexes could be characterized properly. So with this idea, we basically, we then went on to the to apply in two different reactions. As you see here, we have chosen this basic reaction as a proof of principle. One for this palladium is supposed to catalyze the CC bond formation, while the iridium should catalyze the transfer hydrogen reaction. With this, we perform the reaction. As you see, complex 23 having this iridium and palladium connected by a single spacer could catalyze the reaction nicely, giving you about like 90% yield of the desired product, whereas these other two complexes here, 25 and 26, where the homobimetallic complexes are present, in this case is shows inferior activity because this palladium is mostly capable for this CC, or this iridium is for the transfer hydrogenation, as clear from this entry number 6 and 7. Then we just combine these two complexes here in half equivalent. What we see, still the activity of this combination of these two complexes are quite less as compared to our heterometal complexes, which gives you like 90% of the yield. So this definitely says that there is an cooperativity between these two metal centers connected by a single framework. We wanted to check with the other reaction whether it is uniform for the other transformation also or not. For that, we have taken this hydrodefluorination, which is and the transfer hydrogenation process. So as you see, there are three products possible. First one is the desired product, and then second is just a hydrodefluorination reaction, and the third one is just a transfer hydrogenation process. So with this, when we apply this complex 23, what we see that it gives us almost like more than 90% conversion to the desired product, whereas the other two complexes here, 25 and 26 combination, give only 70% of the product. So that clearly shows that the installing two different metal centers at the ligand system, single ligand system, definitely have advantage over the two homobimetallic complexes. So even though getting some information about the mechanism is quite difficult for this system because there are two different metal systems and catalyzing two different catalytic reactions. Therefore, it is difficult to get some idea, but we looked at the reaction profile for this reaction. What we observed that at the beginning of the reaction, we see a lot of this compound G, which is just a transfer hydrogen product in about 55% yield. As time goes, the amount of that decreases. And at the beginning and throughout the reaction, we did not see any of these hydrodefluorinated products. This is just about 10%, less than 10%. So this shows that as soon as this acetophenone forms, it undergoes the reduction by the iridium center and goes to the final product. So and this initial appearance of this in high yield shows that this hydrodefluorination is the slowest step as compared to the corresponding transfer hydrogenation process. With this, I would like to conclude that I have shown you synthesis and characterization of various orthometallated and unsymmetrically chelating ligands containing the ruthenium individual NEC complexes. possessing varying electronic properties, and substantial tuning of their catalytic efficiency of this metal compounds is possible both in hydride transfer reaction as well as the boring hydrogen process. And more in the heteroatomic part, I have shown that the new coordination mode of the 1, 2, 3 triazolidine donuts is possible. Just by changing the first methylation, we could really control the metallation at the backbone, either C4 or C5. At the end, I have shown you various homo and heteroatomic complexes and their catalytic activity in tandem catalytic reaction, which shows some sort of cooperativity between the metal center. So I'd like to acknowledge my student, who is Prasita and Rajiv, who have done this heteroatomic part. Somnath and Shiva have worked on this electronic tuning of the metal complexes, and also the funding agency who have supported us for doing this research. And thank you all for your presence.
Okay. Thank you very much, Professor Arnab. And we can have 1 or 2 short questions. Anybody? Okay, I have a small, your reactivity with the fluoro substituted is really impressive. But thing is, have you attempted the coupling with other substituent, like for example, the chloro, the bromo, the iodide? Does it gives higher conversion? Usually the iodo substituted one definitely gives a much higher CC coupled product. The earlier one.
This one.
Yeah, bromo. So have you tried the corresponding other halides?
We chose this bromo because iodo cases we know that it will give the product. You can do it with the iodo also. No problem.
Because the idea is to try the chloro substituted. So I was wondering when within the Suzuki Miura coupling, you have whether you attempted anything because you still use the noble metal as the center for catalysis. So I was wondering whether it is possible.
So we have attempted this iodide that works, but that is quite obvious that it will work. We have attempted the chloro, but in this case, there are 2 reactions we are catalyzing, not a single reaction. So in this case, we did not have yet success, but with the monometallic system, we could do it. But here, here idea there are 2 different catalytic process has to be catalyzed. One is there, and this is with the another one. So 2 different metals would catalyze 2 different reactions together. So that was the idea. So therefore, we chose this isn't just a proof of principle. We are currently working on other reactions to really see that that idea works or not.
Okay. Yeah, related question is that have you attempted? Of course, you have put 2 different noble metal again. Have you ever attempted any other element?
So we are currently working on putting the base metal on the system and to see that currently we are working on this base metal to see that whether such type of cooperative between the metal center is possible or not. So currently,
like for example, if you take for example a cobalt.
Yeah, that's what we are doing.
Like that, if it is there, it probably would be slightly a bit more attractive, especially if you can control the catalysis, even in a reasonable yield of 70-75%, should still make it a very, very interesting system.
That's what we are working. We are working on nickel and cobalt now, so to find out whether such type of things are possible.
Okay. So, any other questions?
There is one hand, Anukul.
Yes.
Yeah. Okay.
Yeah. Arnab, nice work. So I have one question because I can see there are the many multi-dented ligand based on NHC, either homoleptic or heteroleptic. So what about their isolation as a free carbene? Is it possible or it's a challenge?
So this is a problem because we still are using just an alkylated species because corresponding aromatic substituted to one is difficult to synthesize. To get by because here it's just simple N-alkylation using alkyl bromide will do the job. But if you want to have the corresponding aromatic one, the synthesis is really challenging.
So you mean you mean the N-aryl? You mean
N-aryl, because if you have the N-aryl, then you can attempt to isolate the corresponding 3-carbene and then go for the further reaction. So here we are using the alkylated species and in situ we generate the carbene and metallicity. So for us, it's no need to have the corresponding free carbon generation.
No, that is fine. That is perfectly fine. And that these speakers are serve the purposes. That's no doubt about it. But in general, for example, further development on the isolated carbon chemistry, because for example, in literature, there are not so many, few known about the carbene compounds having a 2 carbon moiety isolables and like a few carbons known.
Yeah, I know. So
Yeah,
in that case, we have to use the aryl group here to have the corresponding stability for the free carbon isolation. Otherwise, it will have subsequent reaction, side reaction, and we won't be able to get the corresponding.
Basically, here is my question. For example, if you consider the monos only the one unit or one scaffold of carbene, that is even stable with a methyl group.
Yes.
Methyl and methyl is a stable. It's a liquid, but it's a stable. But then what could be the reason that when you have a 2 such moiety not stable?
First of all, we have to get the, for example, here we are using 2 different types of imidazolium salt. Their acidity is different. So we have to get that.
Or not, forget about this one. Other one, whenever you have a 2 imidazolium.
Then it's possible. It's not impossible. It's possible.
Okay. Yeah, and Anukul, probably you could both discuss later.
Yes.
Because we are just slightly overshooting at time.
Thank you, Arnab. Thank you, Professor Natarajan.
Thank you very much, Arnab, for a wonderful presentation. And I'm sure that there's going to be a lot of other discussions on it, but due to the scheduling, so I just have to close it. Thank you very much.
Thank you, sir. Thank you.
So the next presentation would be Professor Prabhu Shankar from IIT Hyderabad. Prabhu, are you here? Please carry on.
Yes, I am available. Thank you very much, sir, for your kind word. And very good morning, very good afternoon. This is Prabhu, faculty from IIT Hyderabad. So title of my talk is Exclusive Gold Hydrogen Bond in Gold Carbenes. Let me begin my talk with, what is happening? Yeah, that's fine. Hope you can see my second slide, acknowledgement slide.
Yeah. Go ahead.
Okay, very nice. Let me thank the members of main group Molecules to Material for inviting me to share our ongoing research work. And particularly, I'm thankful to Dr. Krishna, Dr. Srinivasan, and Dr. Saravanappa, NISER Pune. Thank you very much. This work is not mine. Of course, the owners are sitting here. And I thank all my co-workers. Also, I thank my collaborator, Professor Osamu, Ritsumeikan University, Japan, for the fruitful collaboration. And I thank the Department of Chemistry, IIT Hyderabad, for the infrastructure. And of course, my sincere thanks to the funding agencies. So I especially thank DST SERB for the financial support and DST JSPS for the support. So I do get a little money from IIT Hyderabad as well for my research facilities. So I thank IIT Hyderabad too. Right. So a little information about our department. We started our department in 2010 with 6 faculties and 14 students. And so we, in fact, this is our first batch students. We had 7 students in the beginning, and current faculty strength is 18 and student strength is 220. And we took this picture before the COVID lockdown. So therefore you will not see mask anywhere. So please excuse me. And so what you see here are the department buildings. So we call them as an academic building. So block A, block B, and C. So the total workable space is 3 lakh square feet, and chemistry department was lucky enough to get a 10,000 square feet from these buildings for both academic and research activities. So my lab is located in the 3rd floor. Soon we will get our own department in IIT Hyderabad. So this was actually, we started the construction way back, and then it got terribly disturbed by COVID lockdown, and the work construction was stopped. And then, as you can see, no one is working here. And so this is our faculty housing. And so now later we started our construction during the lockdown period itself. and it is shaping up very well. And we expect to get our department in March 2022. And if it all overs and our department will look like this, not exactly, but you can see the real picture of our current building. And so the front one, what you see here is an auditorium, and where we will have a capacity to host 200 delegates, 200 to 300 delegates. Right. And so with this information, just wanted to tell you that in March, most likely we'll be shifting our department from temporary building to our own building, which is not very far, just 200 feet away from this particular building where we work. And what we do at IIT Hyderabad is following. And I'm a main group chemist and work on particularly heavier P block elements such as antimony, bismuth, tin, lead, and gallium. Also, we do focus on filled d orbital, the lead transition metals with the filled d orbitals, such as coinage metals as well as zinc group metals. And so using these elements, and we try to build a catalyst, luminescent materials, and also we investigate structural and bonding aspects. And through collaboration, I do even medicinal chemistry as well. Right, my today's talk will be on structural and bonding aspects of gold. Particularly, I'll be discussing about the nature of gold hydrogen bonding. To be specific, it will be on gold sp3ch interaction, okay, in gold carbon compounds, which is absolutely rare and very challenging to achieve this particular interaction. We do not have a kind of protocol to just directly get this particular interaction, and unless you really attempt with the multiple examples and so on and so forth. So, and also we have investigated the role of this particular interaction in emission properties, right? And remember, here we are talking about gold 1, okay, which has got a filled d orbitals, and the interaction between gold 1 with hydrogen, that to CH3, sp3ch hydrogen atom, right? And so the hydrogen bonding in general can be classified as agostic interaction or pseudo-agostic or anagostic or simple hydrogen bonding interaction. So, the point is what would be the bond angle and bond length between gold and the hydrogen source. And so therefore, remember, so the question comes, do you think that gold can form a kind of agostic interaction with the hydrogen? The answer is absolutely yes. So I have listed out some examples here. As you can see, gold can actually participate in interaction between alpha hydrogen. So this you call it as alpha agostic interaction. Also possible to see beta agostic interaction with the gold and gamma agostic interaction with the gold. What it means? It means the question here about interaction between a gold and hydrogen. Do have interaction. Now the point is, how about agostic interaction, which is very special and which is actually a kind of an origin for CH activation. Okay, it is also possible for gold to participate actively in CH activation. So this particular, therefore, it is important to understand the interaction between gold and the CH interaction. So, but if you look at the literature, you may surprise. See, for example, let me take you through the transition metal elements. And if you look at the early transition metals, okay, where you have empty d orbitals, which can nicely form an agostic interaction, which is well-known fact. Okay, there's no question about it. We call this particular interaction as a 3-center 2-electron bonding. Okay, mostly covalent in nature, right? And the bond angle between carbon hydrogen metal is roughly about 90 to 140. And the bond distance in between a metal and hydrogen is 1.8 to 2.3 angstrom. Now, if you move towards the mid-transition metals, the complication begins, because where you may see a kind of back donation. As a result, you might see a kind of mixed interaction. Okay, you may see a augostic interaction as well as hydrogen bonding interaction. One has to be very careful while assigning this particular interaction. So now the case is very clear. If you work on late transition metals, where the bond angle between a carbon hydrogen metal increases. So typically you see 110 degree to 170 degree, and also the bond length, okay, the hydrogen metal bond length increases, and it is in the range of 2.3 to 2.9 angstrom. Okay, so this particular interaction is known as anagostic interaction or a simple hydrogen bonding interaction, metal hydrogen bonding interaction. Also, where we see 3-centered 4 electron bonding in nature. It is basically an interplay between electrostatic and hyperconjugation. Now, if you look at the gold, it is even more complicated. Okay, the gold is located here. And allowed to exist in a lower coordination number for various fundamental reasons. However, the metallobasic character and electronegativity of gold can stabilize the hydrogen bonding. Okay, and also for various reasons, it is possible, therefore, to see hydrogen bonding with the gold. Right, and but remember, we do not have a kind of system to clearly understand, okay, the nature of gold hydrogen bonding. This remains unclear at present. Thanks to Professor Schmidbauer for highlighting this particular aspects in 2019 and published this highlight on proof of concept for hydrogen bonding to gold. Okay, and this particular highlight is purely based on the work done by Professor Starka. Is actually from Czech, and he worked on this particular molecule. This is a simple gold carbene molecule, where he observed a hydrogen bonding interaction between a gold and NH hydrogen. Okay, look at the hydrogen bonding distance. It is just 2.58. It is almost close to the border of augostic interaction. Okay, and look at the angle. Angle is 158. Okay, it's quite an interesting molecule and very unique molecule too. So what he did, and apparently he concluded this particular highlight by saying this: over less than 5 years, the situation has changed completely with the appearance of a set of publications dedicated to the question posted. Okay, therefore, if you look at the literature, you may get an even more clear idea about gold hydrogen bonding interaction in gold carbenes. And so the pie chart, what I have shown here, clearly, it says that the literature related to metal N-tetracyclic carbene is absolutely well known. While if you look at the literature related to gold N-tetracyclic, is very limited. Okay, and gold carbenes do have a great potential in medicinal chemistry as well as catalysis. Also, now it is possible to use gold N-tetracyclic carbenes for OLED applications. Now, I have splitted up the publications of gold N-tetracyclic carbenes based on simple gold carbene complexes versus a gold carbene complex with hydrogen bonding. So the green bar represents the molecular system of this type, and the red line represents the molecular system of this type. Look at the number of publications related to the gold carbene hydrogen bonding in N-tetracyclic carbene gold complexes. Very, very less. And and therefore, particularly if you look at the interaction between a gold and sp3ch, it was not known at all for quite some time. So by keeping this in mind, what we did, we introduced a very long alkyl chain to the carbene end portion. Okay, it's just heptyl 7-carbon chain. On the other side, so by the way, here we have a provision to see a kind of interaction, hydrogen bonding interaction between gold and sp3ch hydrogen. And the other side, what we did intentionally, we introduced a polyaromatic ring system, anthracene, where this CH, okay, this is of course sp2 CH can also have provision to interact with the gold, and so we succeeded in isolating the crystal structure, and what you see here is actually an interaction between a sp3 CH with the gold. The bond distance is 2.869. It's just a mononuclear gold complex. Usually gold even forms a dimer or even associates through orophilic interaction, gold-gold interaction, which is absent here. The other interesting aspect is this. Okay, so this is an important paper published by Professor Desiraju. I would like to draw your attention to this work. So the title itself starts with the misassigned CH copper agostic interaction and so on and so forth. And what it means basically, it is possible to clearly differentiate the hydrogen bonding interaction using single crystal X-ray analysis. Okay, what one should do, one should look at the carbon hydrogen bond distance, which I call it as a small r, and also it is important to look at the carbon metal distance, which I point here as capital D. Right. Also important to look at the angle between a metal, hydrogen, and carbon, theta. Okay, then the fourth aspect is one should also look at the distance between a metal and hydrogen, that I call it as small d. Now the solution is very simple. Okay, if small d and capital D are comparable, small d and capital D are comparable. Okay, if metal, hydrogen, carbon angle is less than 100, then you call it as an acoustic bond. Okay, also known as intermolecular pseudo-acoustic bond, IPA. Okay, now how about hydrogen bonding? In the case of hydrogen bonding, and the small d, okay, is always lower than capital D, and metal CH angle is always higher than 100 degree. Okay, the D value is somewhere between 2.3 to 2.9 angstrom. So then you call it as hydrogen bond or anagostic bond, also known as intermolecular multi-center heteroacceptor hydrogen bond. Good. Well, sorry, I forgot to mention here. And here in this case, the angle is less bent, while in this case, the angle is more bent. Good. Let us look at our molecule. And here in this case, the small r value is 0.97 angstrom, and small d value is 2.86 angstrom, and capital D value is 3.40. Okay, which is very clear. And then theta, if you look at it, theta 2 value is 115.77. So therefore, small d is lower than capital D. The angle is above 100. So therefore, we call this interaction as intramolecular multi-center heteroacceptor hydrogen bonding, IMH. So which is also known as a 3-center 4-electron bonding due to electrostatic and hydrogen hyperconjugation. Now the question comes, what will happen to this molecule if no hydrogen bonding? To understand this, what we did, we performed a DFT calculation, also TD-DFT calculation, that I'll explain a little later. And the outcome of this particular study is quite interesting. And as you can see here, there's a nice electron cloud overlap between gold and hydrogen. Right, and so therefore it is clearly supporting our experimental result. Okay, this is point number one. Point number two, we have also optimized the same structure without a hydrogen bond. Okay, what happens to the ground state level is that the energy of the molecule without hydrogen bond suits up. So therefore, it is very important for this case to have hydrogen bonding interaction, that too with alkyl group, not with acridine CH, which is sp2 CH. Okay, when we exposed our crystals. Okay, this is actually the single crystals of this carbene compound. When we exposed our crystals directly under UV lamp at 365 nanometer, we saw a very nice blue emitting property of this particular material, remember, and this particular molecule also shows an intramolecular hydrogen bonding interaction between chlorine and CH. So all these weak interactions do contribute to this particular emission. Also remember the molecular packing, so which we call it as an aggregation. Okay, molecular aggregation also has a clear contribution to this particular emission. So, it is important also to study, therefore, the photophysical properties of molecule. The reason behind is it is therefore possible to fabricate OLEDs using N-heterocyclic carbene, specific light emitting N-heterocyclic carbene derivatives. Thanks to Professor Crick and Adam for fabricating working models of OLED using using this N-heterocyclic carbene complex, and they prepared quite a few complexes and fabricated the OLED using this particular material. Okay, therefore, it is important to understand the photophysical property of this material in solid state form. Okay, not in liquid state form. It is absolutely of no use. And so therefore, what we did, we used the single crystals of this particular material. Okay, and excited at 320 nanometer and absorbed emission at 445 nanometer. Okay, this emits a blue color, as you can see here, and the emission of single crystals of this particular molecule, it emits a blue color. We have also quantified the emission using a CIE plot, and the values are here. I'll not go in detail. What is important here is the contribution. The major contribution comes from acridine. Also, we do see a poor contributions from carbene, metal carbene derivatives. Okay, this particular emission is fluorescent nature because the lifetime is a nanosecond scale. Okay, and quantum yield is very much appreciable for this particular family of material. Okay, so therefore, the hydrogen bonding interaction, what we have observed in this material is an intramolecular multi-center heteroacceptor hydrogen bonding, which we commonly call it as 3-center 4-electron bonding due to electrostatic and hyperconjugation. Okay, emits a blue color, and the color comes because of the molecular aggregation, weak interactions that exist in this particular crystalline form. The question comes, can this particular alkyl group alone contribute to the emission of the material? The answer is yes. To investigate this, what we did, we have developed quite a few derivatives starting from butyl to pentyl to hexyl, and similarly we have also replaced anthracene by acridine. Okay, and developed a similar family of materials. And I will just cut short here. I will not go in detail. I'm going to wind my presentation in another 1 minute. And so what you can see here is actually the emission properties of these materials. Very interesting. In terms of their emission nature, this is something very unique. As you can see here, this particular molecule, okay, where you got a 1, 2, 3, 4 carbon atoms. So this is a acridine-based molecule, emits a yellow color, while none other materials, none of these are very similar. They're all somewhere in the blue zone. Okay, so therefore, I can clearly tell you that N-alkyl group has a key role in solid packing, orophilic interaction, and gold hydrogen bonding, properties. So also it tunes the sigma donor and pi accepting nature, which I have not discussed here, and also terribly affects the thermal stability of these materials, and also contributes to the excitation emission wavelength through molecular aggregation. So what happened to the quantum yield? It's again interesting, as you can see here. And so the quantum yield of acridine derivatives are very less compared to anthracene. Okay, out of the 4 anthracene molecules, these 2 are even more interesting. So, for example, the 4 carbon atom molecule and 6 carbon atom molecules have very high quantum yield compared to other derivatives. With this, I thank you all for your kind attention. Thank you very much. Thank you, sir.
Thank you, Prabhu, for finishing in time. And we can take a few questions.
Natarajan, VC here. Can you hear me?
Please.
Yes, sir. Yes,
okay, Prabhu, congratulations, nice results. So you mentioned that we have this anthracene and you put this alkyl group with a view of finding out also whether sp2ch can also interact. But the crystal structure clearly shows that your anthracene actually has no chance because it's perpendicular to the AuCl. Have you looked at a possibility of putting a hinge like a CH2 or something? Then you can check out whether there is a competitive thing in that CH interactions.
Oh, that's a good idea, sir. We have not done that particular work. I completely agree. We couldn't see the CH, sp3 CH hydrogen bonding interaction with the gold in those cases. I completely agree with it. It's a nice idea, sir. I will try that. We have not tried yet.
But would the CH2 will have an effect on the emission then? If you have a CH2, what VC says is correct. You'll have a nice sp2ch gold interaction, but you may actually destroy your emissiveness actually rather.
Yeah.
Balance out both. Yeah.
Yeah, we never know, sir. We'll try. We'll see that. Thank you very much.
Yeah. And Prabhu, have you looked at the length of your aliphatic carbons? C2, C3, C4, etc. You mentioned that C4 and C6 has the higher quantum yield compared to the others.
Yes, sir.
Have you ever, made a systematic study of on the other side whether the length of the number of carbons has any effect and why only a C4 and C6 have a larger quantum yield compared to, for example, C5 and C7?
You are right, sir. So if you look at these alkyl groups, have their own way to fold it in the crystal packing. So the folding nature of alkyl group contributes to the aggregation of the molecule. So this particular emission comes from the molecular aggregation. So when it disturbs the aggregation, you lose the quantum yield.
Okay. So, I was just trying to, Murugavel just made a, move it from the aromatic backbone to an aliphatic one, and he came up with the exfoliation, etc. I was wondering whether if you go from an aliphatic to an aromatic on that side as well, there will be a pi-pi interaction, whether that may do something about it. I don't know. I was just,
That's a good idea, sir. We'll check it. Yeah, we'll check that literature also. We'll check it once. Thank you very much, sir. Thank you.
Any other questions?
Anant is trying to ask something.
Yeah, Anantharaman, please.
Yeah, sir, I'm here.
Yes.
Prabhu, it's a very nice results you got it. And then as Professor VC also mentioned, one is about the second part on the anthracene side, whether you can find such interactions. And second thing is, do you also see a pi-pi interaction, like, the gold pi interaction with the aromatic compounds?
Unfortunately, no. We have not observed any pi-pi interaction in none of these cases.
Okay.
I'm very surprised. Yes. Usually these polyaromatic rings forms a very nice pi-pi interactions, so which is very common in most of the cases, but not in our case. I really do not know why.
Okay. Fine. Thank you.
Thank you very much.
Yeah, I have one quick query.
Yeah, please.
So Prabhu, nice work. Congratulations. So when you talk about this metal and the CH interactions, right? Whether it's acoustic or unacoustic, one can monitor by NMR as well. Did you check the NMR and get the corresponding peak for that interaction?
Unfortunately, not in our case.
Okay.
Professor Francis Gabay succeeded recently, only in his case, published in JACS, only in his case, he could actually see this interaction in solution state also, which would be even more interesting. So, it doesn't exist in a solution state.
Yeah. Most of the cases they see in the solution state because the interaction is stronger, that will uphill hit the CH
Yeah.
proton. But in your case, you are not able to see that one.
No, no.
Okay. So now I'm just wondering, what is the distance between your carbon and gold?
So that we did not see any deviation in the carbon gold distance. We have also checked clearly in all the systems. They're all well within that range. There's no deviation in the carbon gold bond distances in most of the cases. I completely understand. So sometimes if it shows a very strong interaction with the hydrogen, in principle, we should see a kind of disturbance in the sigma donor and pi accepting system, which is absent here. So we did not see any deviation in the carbon gold bond distance. So Tilakara has gone.
Yeah, Adi Narayan.
Yeah, yes, sir.
Hi, Adi.
Prabhu, actually, very nice overview about gold hydrogen contacts. Could you able to hear me?
Yes, I can hear you.
Yeah. So the thing is that have you tried to abstract the chloride, gold chloride?
No, we have not
the
done
cationic complexes. Maybe
No,
here,
no.
just this may be my question is little bit expanded version of Professor VC and Professor Anantaraman. If you make them cationic gold, because you have anthracene attached to the nitrogen center, it may show some sort of metal pi interaction. You might have a beautiful the molecular architectures in the solid state actually. You may guess,
I
right?
completely agree. A very good point also. By knocking off chlorine, you will be eventually adding one more carbon to that particular system. As a result, you would end up in getting a kind of homoleptic carbene gold complex. Am I right, Adi? You wanted to say that?
Yeah, what will happen once you remove the chloride, then two gold atoms may come close. It may show
No, it doesn't go in that way. It doesn't go in that way. By the moment you knock off the chlorine, you will add one carbene to the gold center. As a result, you make a homoleptic gold carbene.
No, where is the carbene? No, there is no carbene, extra carbene. You are not giving extra carbene.
No.
So what will happen? You are making it monocationic, right? So gold always likes to have another gold. So you may build up dicationic species.
I understand.
So then two golds come close and becomes a dication.
Yeah.
So because you have anthracene, it may give up some. It may give new bonding modes.
Could be
gold pi contacts actually.
Sure,
Maybe
possible.
You may please try this out.
Very interesting. Thank you very much. We'll look into that. Thank you.
Yeah. Thank you so much. Thank you.
Okay, if there are no questions, thank you, Professor J. Prabhashankar.
Thank you, sir. Thank you.
Thank you, Professor S. Natarajan, for hosting this, chairing this session. Yeah.
I think there is internet problem in IAC. That's why both Tilakara and Professor S. Natarajan logged out.
Yeah. Okay. Once again, thank you, Professor Prabhashankar, for the nice talk. Okay. Yeah.
Thank you very much.
Yeah. Thank you. Yeah. So with this presentation, yeah. Now I will invite ACS Mr. Ajay from ACS to deliver a short talk.
Yeah.
Yeah. Ajay, are you around?
Yeah, I'm there. Thank you so much.
Please. Yeah.
I'll be sharing my screen, and good afternoon to all. So let me share my screen. So could you please confirm that the screen is visible?
Yes. Yeah. Ajay. Yeah. Please.
Okay. So thank you so much. And of course, this is a great congregation of great scientists again from Indian scientific community. So I'm Ajay Jha from ACS Publications, and I'll be sharing some glimpse of what ACS as a society is doing in India and across the globe. So again, first of all, thank you, Dr. Krishnan, for giving us this opportunity. And again, the organizing committee of MMM2, NICER, to invite us to this platform and share our initiatives with the Indian scientific community. So this is an opportunity for me to share what ACS has been doing, and again give you a flavor of what are the initiatives that are going actively for the researchers, early career researchers, or the Indian scientific community specifically, in terms of careers or writing publications or writing projects and other things. So if we go back to the history of ACS, so it was founded in 1876 by Professor Charles F. Slander, one of the chemists from America. And in 1879, the flagship Journal of American Chemical Society came into existence, which every chemist loves to publish in and aspires to read again. From there, from 1876, the journey has been quite flourishing. We have now 2,000 employees all over the world, 2 primary locations in DC and Columbia, and again, 30 plus international presence all over the world. We have 180 plus local sections, international chapters, and one of the largest scientific communities we have built in terms of membership. So if we talk about the impact that ACS publication has created within these years, we all know that we run by this tagline of most trusted, most cited, and most read. And the stats clearly show that why we stand here. And as you can see that in the last 2 years, we had a total citations increase by 550,000, which is around 15% increase across the portfolio. Around 10 in the 10 categories, our journals were listed as most impactful, and that makes a lot of difference. And on the usage point of view, ACS readers grew to 170 million article downloads. So this is something that creates an impact all over the scientific community. And we are thankful to the Indian scientific community who has actively been publishing and been a part of this, this glorious journey. So recently we launched 9 gold open access journals, specifically focusing the European researchers who are now mandated to publish their articles into open access journals. But again, we have taken into consideration the active scientific community of India who wants to publish in these journals. They could find a venue for their research in different genres like biomedchem, engineering, materials, measurement science, inorganic chemistry, and physical chemistry. And the APCs are really subsidized around $500 US. So and again, we are not going to compromise on the quality, because the deputy editors, the associate editors are again related to those established journals at ACS portfolio. For example, if I talk about ACS Organic and Inorganic Gold journal, the associate editor or the deputy editor is again involved with the highly established journals like JOC or the Organic Letters. So the quality is never going to be compromised. And of course, some of the people in this community is again on the board as editorial advisory board member, and we are proud to have them. So the association with ACS from India goes back to 1913 by a JACS paper by Professor Neel Ratan Dhar. So this is the long association that we have, and we are really proud of that. So in terms of the publication, we have consistently been growing all over the years. And as you can see, the published outcomes have grown all over the years from 1459 to recently in 2020, more than 2,500. And again, if we talk about the editorial presence, it has also grown, and we are greatly thankful to the people in the scientific community who have agreed to be on our scientific journals and promote it in all the possible capacities, and have that trust into the scientific community in terms of the rigor and the peer review process that we have established in the past. We have active collaborations with the partners in India, government bodies like Department of Science and Technology, SCRB, Indo-US Science and Technology Forum, CRSI. And from time to time, we host events and provide sponsorship to them in different kind of events, and try to leverage the kind of scientific resources and products we have to bring to the scientific community. As one can see here, we are in all the fronts actively associated with the scientific bodies. As we can see, one of the editor-in-chief of ACS Applied Material Science, Professor Kirk Shah, is meeting with the President of India, discussing about the initiatives that, in terms of the material sciences, that ACS has been focused and extending its portfolio journals and how it is going to impact the society. We have been doing ACS on campus, which has been a flagship event all over the world, and India has been one of the prime locations. This is one of the outreach events that happened in Indian ACS on campus. Then we have been actively organizing workshops, whether it be DST ACS publishing workshop or author workshop or scientific sessions. We have been actively using this platform to increase the awareness among the scientific community around publishing good articles, drafting proposals and all. And again, India has been the highlight in many of the virtual collections from journals like Physical Chemistry Letters, Applied Material Interface, and other new journals at the same time. This is a glimpse of how we have been doing even in the time of pandemics, and we were able to host more than 10 events in 2020, 2021, and attracted more than 65,000 registrants and 26,000 participants from more than 2,000 universities in India and across the world via these events and programs. So the highlight is on the DST ACS publication workshop. So this is a program that is run in collaboration with Department of Science and Technology. It is funded totally by them. And initially it was an on-site program, and we used to visit the other institutes, the regional institutes in India. As one can see here, we visited the 5 on-site locations in the different parts of the world, from north to south. And it was a huge hit. Covering all those aspects of writing, manuscript writing, scientific communication, careers, webinars, etc. And till date, we have been able to attract more than 13,000 registrants on this particular platform. So it's a great place. And in future, whenever we have this program launched, we would request the attendees to join and leverage it. Again, we have ACS India webinars, a global program which we brought to India in Indian time zone. And it focuses on many of the diverse topics relating to careers, writing projects, how to start up, and then work-life balance, and how to make the most out of your PhD. So these are some of the burning topics that we generally discuss when we are in the research life. So we generally try to capture all those points and make the scientific community aware on those aspects. So, and the list of speakers has been great. The dais of this scientific community as well as the industrial scientific community have been the speakers like Professor Anubhav Saxena, the president of Pidilite Industries, again, the Department of Science and Technology, ex-secretary, Professor Ashutosh Sharma, and the list is long. So then this is an ongoing active program, ACS Science Talks. This is a program where we invite our high-profile speakers, scientists, again, editor-in-chief, associate editors, and editorial advisory board members to share their thoughts around the work, the scientific talks. And then this is a direct conversation around the kind of science that they are doing and how the scientific community should get inspired of it and how they could define new problems in that particular areas of research. So till now we have had around more than 80 talks in this session, and the list is long. And we have a virtual ACS Science Talk library where one can go and visit all those past lectures and get benefited from it. If I talk about the other quality resources that we have ACS Reviewer Lab. If you want to excel in the review process and again understand what are the aspects that a reviewer takes into consideration while reviewing an article, this is a good tool. This is a free product provided by American Chemical Society. Then ACS Author Lab, how to write effectively a manuscript, draft proposals, and how to know about the basics of ethics and plagiarism. So these are the things that one can find here in these three resources: ACS Reviewer Lab, ACS Author Lab, and the ACS Guide to Scholarly Communications. Of course, we have a blog, ACS Axial, which keeps you updated with the latest events, the different kind of updates on the editorial level at American Chemical Society. Then you want to have any kind of help regarding any assistance while writing a manuscript, then one can access this ACS Publishing Center. We have a lot of YouTube videos from the editor-in-chief, the associate editors, on what are the different aspects of writing a manuscript, what are the challenges while writing a manuscript, and one can easily go to this ACS Author University and leverage the insights that the ACS editors have, or the ACS staffs have provided from their huge and vast experience. So this is all I have from the ACS publications. And again, we are a society and we have this ACS membership. So the new membership is coming to roll on in 2022. And this is something that I would request all of you to visit and see how this is going to be helpful for you, because now we are going to have different tiered membership as per the requirements of the scientific community people. So this is all from my end. And this is the new website that ACS in India has. So here one can be updated with the latest events, whatever programs we are organizing, what are the initiatives which we are taking, and be updated with this. So if you want to connect us, these are the platforms: Facebook, Twitter, Instagram, and LinkedIn. Feel free to associate with us. And again, if you have any query, please email us or contact on this number. So thank you so much. Thank you for your kind patience.
Yes, thank you, Ajay. If any student have any doubts or any clarification, I think most of them, they are well aware of ACS. So
great to know.
Yeah. Okay, so so on behalf of the organizing committee, I once again would like to thank all the speakers of both the sessions and the chairs of the sessions also. And we'll be back at 2:30. And in between, there will be a poster session from 30 to 45. Students who are presenting 30 to 45, be online. If the judges need anything, they will contact you. Otherwise, they are fine. We'll be back 2:30. Yes, thank you, Ajay.
that 5:30 they'll
देखो ना
Good afternoon, Alcaraz.
Hello.
Hi.
Hey, Jeeves, how are you? How are you? Good, good. Good? So, everything is fine? Hi? Everything fine, everything fine. Okay, perfect.
Students can interact if anybody is interested with Alcaraz. So he'll be kind of happy to answer. We have some time. So, Alcaraz, how about the PhD position in France?
My position?
Yeah, PhD work, PhD.
Yes, actually, I'm working at the CNRS. CNRS is a research agency. So we have several agencies in France. There is the university, and you have also the CNRS, which is the French National Research Center. And as a CNRS member, you can do your research either in a proper research center, there are some, or to do your research in the university, but you are paid by the CNRS actually. So what is the particularity of the CNRS is that you only do research, and the position belongs to you. I mean, if you want to change for any place, you just make an arrangement with another lab, another university, and you can move.
Oh, okay, okay. So
that's the specificity of the CNRS. And you don't teach?
No teaching?
No teaching. Oh, you can a bit, but no really teaching.
Oh, okay. So PhD students?
Yes, yes, PhD students, postdocs, and normal life
okay.
researcher. We don't teach, but we are in the lab, and we are interacting with students also.
Okay. So suppose any students want to join in your group. So what is the procedure?
The procedure is just to be in contact first, to discuss, and the point is that generally the students, so for a PhD or for a postdoc, must be paid. So that's the rule in France. So the funding is very important, and so generally, so we can find sometimes funding from the national funding or European funding, or we have to work on that. That's very important. Okay. But that's mandatory for coming in the lab. But first of all, I would say to be in contact and to discuss, and we can also ask for joint programs or something like that to collaborate, to facilitate the venue of students and postdocs, of course.
Okay. So what is the time period for PhD?
The time period is 3 years.
3 years. Okay.
Yes. 3 years.
So yeah. We have a 5 years period. That's.
Yes, but it doesn't include the master period here. So because
you don't have any coursework in France.
Sorry?
You do not have to pass any courses or comprehensive exam before you get into lab.
Actually, it's not really classes, but you have to accumulate. It's called points with some formations and with extra specialization, including participation to congresses, working in another lab for a short period abroad, and doing some specific formations. So that's the rules for the, it's called the doctoral school. So it includes many formation inside. But I think it's more or less the same everywhere.
Okay.
Do you have any update on the IMI board
Huh. It's a pain. It's a pain. I don't dare to say something because each time we start to organize something, you know, the outbreak is arriving and we have to stop everything.
Yeah, it's true.
But what is for sure that we definitely want to organize it not in a virtual mode because we think it's really better for the participant to be in Rennes, and so that's the reason why we are optimistic, and I hope that it will be feasible in 2023. Yes.
Let's hope.
We still have time.
Yes.
Yeah, but we'll see.
Yes, let's see.
Mm-hmm. So I saw many nice presentations. I tried to wake up very early these 3 days. I'm jet lagged at home, so it's very funny. But it's a very nice symposium. Yes.
Yeah, it is. It is. A lot of good talk.
Todd is here, I think. Todd joined. Swadhin also here.
Good morning, guys. And good morning, Gilles. How you doing?
Hi, Todd.
Yeah.
Long time no see. I had my Ren ICOMC T-shirt from 2008 yesterday, but I switched it today.
Okay. So now you need more than a T-shirt. You need a jumper because it's quite cold. It's winter.
How are you guys?
So for me, it's okay.
Todd.
Okay. I have to sign off right after Gilles' talk because one of my own postdocs will be giving an institute lecture at 11 o'clock. So my apologies that I have to sign in and then sign out, and
no problem. No problem.
Difficult schedule here.
Don't worry.
Okay. So.
So
we'll wait 1 minute, then we'll start.
Okay.
So far, it's been a very exciting. All the presentations are wonderful. I think everybody enjoyed.
Yeah.
Okay, so let's start. So the chair for this session is Professor J. Shankar from IISER Bhopal. Shankar.
Thank you, Krishan. Thank you and all the organizers for giving me the opportunity to chair the session with 3 nice speakers lined up. And we are starting this 11th session with Professor Alcaraz starting the session. And I request Professor Alcaraz to present his work, and it will be followed by the discussion. Professor Alcaraz, it's yours.
Okay, so I'm going to share my screen. So do you see the screen? Yes?
Yes, it's clear.
Okay. So first of all, I would like to thank the organizing committee for this kind of invitation to participate to the main group Molecules to Materials conference. That's really a pleasure. And my lecture entitled BN Bonds Engineering from BH bond activation to polyaminoborates deals with BN and BH bonds in molecules, in coordination complexes, and in polymers. So I will start with the general case of the BN bond, and that can result from the intermolecular interaction between the non-bonding doublet of the nitrogen fragment and the MTP orbital centered on the boron of a borane if no frustration. The creation of the BN single bond goes with the pyramidalization of the boron atom that is now sp3 hybridized, and depending on the nitrogen nucleophile, if it is charged or not, you end up with a charged aminoborate or a neutral amine borane adduct, respectively, the nitrogen boron bond length being generally around 1.6 to 1.7 angstrom. Now, if the boron and the nitrogen are in an adjacent position, you first create the sigma bond between these two fragments, each one bringing one electron. The amino moiety within the non-bonding doublet is out of the RBR plane, and the rotation around the BN bond enables N-pi p-pi interaction, and this induces a shortening of the nitrogen boron bond that has now a double bond character, and it is now around 1.35 to 1.45 angstrom. Depending on the situation, the BN bond can be looked as a substitute of a double CC bond or a CC single bond. And when incorporated within the molecule, this can change its physical and chemical properties without significantly altering its sterics. The BNCC isosterism offers a strong potential to analog species and new materials that incorporate BN bonds. And I have quoted here the very elegant work of Liu, for example, in the case of the 1,2 azaborines as BN benzenes, but I could also have mentioned the work of Professor Thilagar that is present here for his work in the field of the BNCC isosterism. And the other very active research field is about the polyaminoborates as polyolefin analogs. This chemistry is often called the BN engineering and involves new synthetic strategies and methodologies, as seen, for example, yesterday with Professor Matthias Wagner. Among these strategies, the incorporation of a boryl fragment to a molecule occupies a special place, while hydroboration of an unsaturated compound with a Lewis acidic hydroborane works fairly well for this. This is not the case with alkanes or arenes. And in this field, the contribution of metals is unavoidable to modify and orientate the reactivity, the chemoselectivity, etc., as it is illustrated here. And many metals can do the job. Now, if we look more carefully at the general case of the catalyzed hydroboration of an olefin and at the elementary step of the mechanism, the oxidative addition of the metal to the BH bond represents the BH activation process. And as you will see, there are many scenarios possible for activating a BH bond. Before that, let's have a look when a BN bond is and the BH bond are tied within the same molecule, which is the case in amine boranes. Their general tendency is to lose the hydrogen upon heating. From a secondary amine borane, you generate this aminoborane that dimerizes. It is, however, observable in solution even if the equilibrium is strongly displaced toward the dimer. And from a primary amine borane, you generate the corresponding trimer, the cyclotriborazane, and that's the general tendency. Now, if you increase the steric hindrance at the nitrogen, as here with two isopropyl groups, you can stabilize the monomeric form, and the diisopropylaminoborane is isolable and easy to handle. And almost 20 years ago, we have started to use this aminoborane as a BN carrier that can be attached to organic molecule by CX and BH activation under palladium catalysis. And the borylation works well. And here the Villink species can be seen as an heterodiene. And in the 1H spectrum, this hydrogen couple with this one and with the BH as in a diene. It gives a doublet of doublet that collapses into a doublet upon selective homologic coupling experiment of the BH bond at 4.72 ppm. Okay, so what about the BH activation itself? The term bond activation mostly refers to a bond that has been broken in a process, but to better understand the process itself, it is important to examine how the bond is broken. And for this, the study of the formation and the fate of sigma complexes is particularly informative, as they can be seen as snapshots on the path to the oxidative addition or conversely to the reductive elimination. And they result from the coordination of a EH sigma bond to a metal center via a 3-center 2-electron interaction, like in the case of the coordination of an olefin to a metal center. So to study this activation, the tools that have been selected for this study are the ruthenium complexes developed by Bruno Chaudret that are well known for the ability for coordinate the hydrogen. And the first one, for example, is coordinatively saturated, stable, and isolable. It can lose easily 2 molecules of the hydrogen and liberate 2 vacant sites. The second one is coordinatively unsaturated. This is a 16-electron ruthenium complex with 1 vacant site, and it can liberate a second one by loss of this molecule of the hydrogen. And with the presence of the X ligand here, you can tune the electronic balance at the ruthenium, and then we can access to this 40-electron fragment that is really unstable but very reactive. Okay, we have the tool. So now, starting from the hydrogen ruthenium complex in the presence of the isopropylaminoborane, the reaction results in the formation of the corresponding bis sigma BH complex, the linkage involving the geminated BH bonds. They are elongated with respect to the starting aminoborane with 1.22 and 1.25 angstrom for the BH bonds. Their hydridic character is strongly increased with a chemical shift passing from around 4.7 to -7 ppm. And the coordination results from the sigma donation of the electrons of the sigma BH bond into the sigma star ruthenium hydrogen bond in transposition, and with a back bonding involving the a non-bonding electron located at the ruthenium towards the boron in the p star BN bond. The same approach has been performed with similar rhodium and iridium bis hydrogen complexes. This work has been done in collaboration with Andy Wehrle. And it is very interesting to note that the coordination of the diisopropyl aminoborane to the rhodium center is actually less efficient to that of ruthenium. The BH are less hydridic. The rhodium boron distance is longer than that of ruthenium. And this is due to the valence orbital of the cationic rhodium fragment that are actually more contracted, and the overlap is less efficient. However, with the bigger iridium that display more diffuse orbitals, the situation is rebalanced, and we are now in a situation similar to that of ruthenium with similar metric and similar chemical shift. So we are roughly in the same situation with the iridium complex, cationic iridium complex, than in the neutral ruthenium 1. Now, the same reactivity, but a different ruthenium complex. This 16 electron dihydrogen ruthenium complex. The presence of the chlorine strongly modified the electronic balance of the metal, and the obtained complex is not symmetrical anymore, as seen by 1H NMR. All the hydrogen around the metal are non-equivalent. But what is very intriguing in this complex is this hydrogen that is very strongly shielded at minus 70.6 ppm, and it displays a coupling with all its neighbors. This hydrogen, the boron, the 2 phosphorus, which is quite unexpected. On this basis, the question arises as to the representation of this complex. So we obtain the X-ray structure. It is of octahedral geometry. The ruthenium boron distance is relatively short, 1.92 angstrom, shorter than the sum of the covalent radii of the ruthenium and the boron. So it means that there is a strong interaction between these two atoms. This boron hydrogen bond is not elongated at all. This one is more than elongated. It seems broken with 1.53 angstrom. This ruthenium hydrogen bond is in agreement with the bond length for a terminal ruthenium hydride. The best representation should therefore be this one, a boryl ruthenium complex with a ruthenium at the oxidation state of 4. The problem is that the ruthenium 4, as this one published by Werner in 1996, should adopt a square antiprism geometry with 2 vacant sites in alternate position at 1 square basis, as it is represented here. And this is not the case with an octahedral geometry. Actually, the fine analysis of the electron densities by combining atom in molecules theoretical calculation and X-ray diffraction show that we are in a rested state, really in the middle of the oxidation process, the hydrogen initially bound to the boron being transferred to the ruthenium, but not completely yet. This is really a snapshot of the BH oxidative addition process. And what also it's important to note is that the BH activation can take place, but without altering the BN bond here that that has the same bond length. So it was an interesting result, and after that we tried to pilot and tune the activation process of the BH bond by incorporating a remote coordinating group to the aminoborane, and first with the phosphino group and different spaces, a methylene, benzene, benzyl, and swapping the 2 positions here of the phosphorus and the boron. This allowed us to develop the coordination chemistry of agostic sigma BH borane, each spacer leading to a unique situation, even to this one that is quite funny, which is a bis agostic sigma BH sigma CH complex. So in each situation, the coordination elongates the BH bond, which is activated, but not broken. And by changing the phosphorus to a sulfur, the situation is completely different. So with almost with the same spaces, all the complex obtained are borohydride type complexes, and the sulfur actually favor the interaction between the hydride at the metal and the boron at the expense of a pure sigma BH coordination. So no strong BH activation with these functional boranes. So we then turned to aminoboranes displaying a remote reactive function, such as a nitrile, and we do some catalysis. And in the presence of this bis dihydrogen ruthenium complex as the catalyst and the 2 bar of the hydrogen, the reaction leads to this benzosaborole. And we clearly see the disappearance of the BH and the CN vibration bonds, and the appearance of the NH, as we can see in this infrared spectrum. The reaction works quite well, and the corresponding benzosaborole could have been isolated in fairly good yield with different substitution pattern at the RN ring. The mechanism of this transformation is somewhat surprising and do not involve any agnostic sigma BH complexes. We work a lot, and finally that's not the case. I simplified the mechanism for more clarity, and I just present the main step. It involves the side-on coordination of the nitrile to the ruthenium, followed by its partial hydrogenation into the imine side-on coordinated, then eta 5 coordination of the azaborole 5-membered ring, hydrogen transfer from the ruthenium to the CH of the 5-membered ring, followed by an aptotropic rearrangement, and finally release of the benzosaborole. This intermediate has been isolated from stoichiometric experiment, and some intermediate has been characterized by NMR in solution. Okay, so now what about the concomitant activation of a BH bond and a NH bond? This catalysis has been strongly studied in close connection to the chemical hydrogen storage concern, and even in the understanding of the mechanism, and even if the understanding of the mechanism offers many possibilities and opportunities. And the general case of this reactivity is presented here and can be summarized as the catalyzed dehydrocoupling reaction of aminoboranes. The result, of course, depends on the starting aminoborane adduct, but also on the catalyst. And to my opinion, the most salient result came from Goldberg and Heineke in 2008, that with the use of the iridium POCAP complex as the catalyst, they were able to produce polyaminoboranes. So we were very interested in this transformation, and we tried it. And in our case, the reaction proceed with this ruthenium bis dihydrogen complex under stoichiometric condition, not in the catalytic condition. The dehydrogenation takes place perfectly, but the generated aminoborane is trapped at the ruthenium. And this allowed us to isolate for the first time the elusive and simplest aminoborane elementary unit. And here is the Toxi 1D experiment showing the connectivity along the complex. So it was a very nice result. But the reaction only works under stoichiometric conditions. So we then explore the reaction with an aminoborane and with a remote aprotic amino group. In that case, the reaction proceeds with the trapping of the corresponding B sigma BH complex at the ruthenium and the pendant amino group remaining distant from the metal center, as we can see with this X-ray diffraction structure. But in the presence of a remote protic amino group, the reaction leads to the dehydrogenative cyclization, with quantitative production of the corresponding diazaborolidine. This is a living catalysis. And as shown by the theoretical calculation, the interaction between the remote nitrogen and the boron coordinated to the metal center makes this NH more acidic, enabling the development of a dihydrogen interaction, followed by the hydrogen transfer to the metal and formation of the diazaborolidine. So in many transitional metal catalysts work for the dehydropolymerization of amine borane, and we have to admit that in our case the bis sigma coordination is too strong to enable the aminoborane form to evolve out of the first coordination sphere of the metal. But interestingly, and it's maybe a case of serendipity, in the absence of metal, the neat reaction of diisopropyl aminoborane with the primary amine at room temperature leads to a mixture of compounds, as we can see with the boron spectra of the crude mixture. And all the compounds in this mixture are represented here. We know that because they have all been synthesized separately, characterized and identified in the reaction mixture. But what is most surprising is that the same reaction, when conducted at -40°C, the reaction leads predominantly to the formation of the corresponding high molecular weight polyaminoboranes, probably by this aminoborane adduct. The reaction can be conducted at the multigram scale. It works well. And of course, we want to know better about the mechanism. And for that, to unveil the mechanism, some DFT studies were carried out. And indeed, the initiation involved the formation of the aminoborane adduct with proton transfer from this nitrogen to this one and release of diisopropyl amine and formation of this new primary aminoborane. Here is the energy profile of the initiation, and this is the route in black. And in red, this is the formation of some side product that result from hydrogen transfer between an aminoborane and an amine borane fragment. And this has been clearly shown by Ian Manners in this JAX in 2012. The propagation result from the interaction of the primary amine with the aminoborane with neutralization of the Lewis acidity of the boron. The amino moiety can in turn react with another aminoborane molecule to form the linear dimer. And as you can see on the energy profile, in green, the trimerization of the aminoborane into cyclotriborazane is thermodynamically favored, but involves a higher barrier. So with the decrease of the temperature, the self-condensation takes place at the expense of the trimerization, and then the reaction is under kinetic control. So it means that we were really lucky with our experiments. So, of course, the reaction can be continued. The aminoborane unit condensing in a head-to-tail fashion. That's the black route on the energy profile. The other green and red are the formation of the side product by hydrogen transfer, as I explained previously. And what is interesting is that practically you can access to a variety of polyamidoborane at the multigram scale. The precursors are really easy to handle. The approach enable also, which is quite interesting, enables the introduction of functional groups at the nitrogen, like here with an unsaturation with the allyl group at the nitrogen or a propargyl group. You can also easily prepare copolymers by just mixing the primary amine at the beginning of the reaction. So it's very easy. And the solubility depends on the nature of the R group, of course. When they are, well, for example, these two ones are really insoluble in polar organic solvent, and these two ones, this one derived from the metanyl amine and this one from the xylamine, are perfectly soluble in organic solvent. And when they are soluble, it's really easy to do some shaping, and you can prepare some film. And this is in the case of the starting from butylamine, and this is the film after several weeks and even maybe several months in air at the bench. So it's quite stable. An interesting feature is that they can be easily characterized in solution by standard NMR techniques, included cis-13 solid state NMR when insoluble. And for example, you can see here for the two polymer a good match between the two techniques. As you can see with this spectra, we can find the same peaks for the same carbon with the two techniques. An interesting feature is also the non-equivalence of the two methylenic proton on the methylene alpha and beta to the nitrogen in alkyl chains. We can see here for this CH2 two signal in addition with the NH that is superimposed here. Here you have the two CH2 here, and here they are here, and the third one is they are equivalent. So this is really a specificity of this polyaminoborane. And we have also something quite strange, which is the sharpening of the signal of the BH2 upon boron decoupling, the sharpening into two overlapping broad signals, as you can see here. And so this is quite new, and we have no really explanation to give at this stage. But what we think it's maybe it's due to the tacticity of the polyamidoborane as a possible explanation, as in polyalkyl metacrylates. And this is very interesting because it opens the way to the tacticity of this polymer, which is really new. So this work must be continued. And so I will conclude so now my presentation with maybe three generalities. So the first one is that the presence of the nitrogen attached to the boron plays a crucial role by decreasing the Lewis acidity of the letter, which is really expected, but it's impressive actually with all these reactivities. And in the presence of metal hydrides, the borohydride are less accessible. So this is because of the presence of the nitrogen in adjacent position. The BH activation with aminoborane remains an interesting field to explore, and many challenges are still remaining in connection with the cis-CBN isosterism. And for example, the double activation of the two BH bonds here. And finally, many efforts, as I'm sure you're convinced that they have been undergone in the field of the BH activation, and we have learned a lot, but finally our best results have somewhat been obtained under the simplest condition in metal-free process. This is a really, this is a humbling experience, okay? And I will conclude by, I would like to thank all the people who participated in this work, that started maybe almost 20 years ago, all the students, all the postdoc, Sylviane Savoitienne that is now retired, Chiara and Iker were now doing all the theoretical calculation, and Marc de Villars here, who was quite recently hired by the CNRS, and we are working together, so I'm quite lucky. And he's also developing a nice chemistry around silicon. And thank you for them, and thank you for your attention.
Thank you, Professor Alcaraz, for the interesting lecture. Yeah, we have time for a few questions, and the floor is open for discussion.
Yeah, I have one question regarding your molecular weight. Can you comment about the molecular weight of the polymer?
Yes. So, which aspect do you want to know about the polymer?
The later one,
This one?
Yeah.
Here?
Yeah.
So, actually, when you make the comparison between the polyaminoboranes and the polymetacrylates, so the tacticity is very indicative because concerning the CH2 in the polymetacrylates, for an isotactic polymer, you have a clear inequivalence of the CH. For the syndotactic, the distribution that you observe one single peak, and when it's atactic, you observe the two sets of signals. So this is well known for these carbon polymers, and so we imagine that this could happen with polyaminoboranes and induce some inequivalence of the chains, but at this stage I can't say more because really I don't know. And it's very difficult to study that by NMR because of the quadrupolar moment of the boron, which is broaden all the signals.
What is the value of N? Can you elaborate? The molecular weight.
Yes. So we obtain very high molecular weight, but the N is very difficult to define because to have an accurate value, we should use known standard polyaminoborane. And generally, by SEC analysis, you use polystyrene standard. And so that's just an estimation, but that's not the reality. So that's a first part of my answer. But what is very funny, and recently we had some new result on that, is that when you synthesize the polymer, since it's the polycondensation, even if you isolate the polymer and if you store it, the N chain can still continue to condensate. So if you store it at the solid state and you redo the analysis, you obtain a bigger molecular weight.
Thank you.
Yeah. So, Professor Thilagan. Mr. Thilagan, you are mute.
Yeah. Thank you, Alkash, for the beautiful lecture. I truly enjoyed it. So I have a couple of queries. One is, you have nicely placed these aminoboranes between the carbon units, right?
Yes.
If you heat them, will they release hydrogen?
Yes.
Will they release hydrogen, molecular hydrogen? Because
yes.
in the
it was before, I think. Here, yes.
What about in your polymers?
No, generally so when you heat them, you lose the hydrogen, and with the for example with ammonia borane,
yeah,
you in the first stage you generate this cyclotriborazane.
Yeah.
Then if you keep on heating, I need to go here.
Yeah.
If you keep on heating, you form the borazine. You still lose the hydrogen. And if you keep on heating, then you condense, you polymerize the borazine into polybarazilanes.
Yeah. But if
and you still lose the hydrogen.
Yeah. This one, if you heat it, you will end up with the insoluble product, which is a highly polymer, and also it's not possible to reverse it back. But if you take your polymer and heat it, it may not undergo such kind of insoluble polymer things.
Yes, we are looking at that, and we did some experiments, but that's too fresh, I would say, to say something. But what we saw is that, for example, under metal catalysis, you can generate the borazines from the polymer, for example. Okay, so the polymer can be broken, of course.
Thank you.
Okay, any other questions from audience or from students? If there are no more questions, please join me thanking Professor Alcaraz for a very interesting talk. And thank you, Professor Alcaraz, for the nice lecture. Yes. So now we are moving on to the second lecture of this session, which is going to be delivered by Professor Swadhin Mandal from IISER, Kolkata. Professor Mandal. Yeah.
Yes.
So,
Yes.
Mandal, yeah. So is yours, please.
Shankar, slides are visible?
Yes, visible. Yes.
Great. Yeah, thanks, Shankar, for being chairman for this session. And in the beginning, let me thank Krishnan and Saranappa for making it happen, because I was just realizing that last few days I have been seriously attending so many lectures. I could not remember when I did that in a symposium. So it's such an organized meeting, actually. Wonderful lectures. With that, let me begin this topic, actually, which we have been working on last 6 or 7 years. So I'll put rather in a perspective form, actually, what we have been developing, rather than telling 1 or 2 results. I mean, in this area of developing CO2 functionalization catalyst without any metals. So as a brief background, I mean, to tell you the broader scenario, if you look at global energy balance, actually this slide I built up from the data which I obtained from International Energy Agency at Paris. So which tells that if you look at the total energy terms globally, that is primarily from, give me a second, I'll just take my pointer. Yeah. Okay. So if you look at this, it comes from oil, coal, and natural gas. This is the 82% contribution comes, and all of them, while producing energy, it creates carbon dioxide. And no wonder, this is also data I got it from the same site. If you look at 2 decades CO2 emission, it's relentlessly increasing every year. You can see that total CO2 emission is ever increasing as a result, because we need more and more energy. Now, this is a question that how really you want to deal with excess emission. And if you look at several strategies, you can see that there are 2 broad strategies which are very well accepted. One is capture and sequestration. So where you can capture carbon dioxide and you can store below the seabed, or you can utilize it different ways. You can utilize it for enhanced oil recovery, or you can convert into value-added chemicals. So these are the 2 ways. And so what experts believe that, I mean, there is no one solution for this particular problem. And we need to keep on working, and with a bunch of solutions we should bring to mitigate this problem. So if you look at, as a result, we don't have good discovery in terms of transformation of carbon dioxide into useful material. If we look at this total emission, we have very non-significant amount of carbon dioxide we could convert chemically. And because this is a very challenging process. So if we look at several challenges associated with this is thermodynamic stability of carbon dioxide. And very often it uses metal-based catalyst and which is working under harsh condition and expensive and toxic, these metals very often. Of course, these are very energy intensive process. So what we have been working in this direction is that can we use some very reactive low-valent mangrove species as a metal-free catalyst to fix and convert carbon dioxide. Let me put a disclaimer, I mean, not disclaimer, but honest opinion that all this work we have been trying to develop a new reactions with carbon dioxide in terms of chemical conversion. So right now we are nowhere close to really come up with the industrial solution. So all reactions are done milligram scale and some of them have been scaled up to 1 gram scale. So nevertheless, as you can understand that if we want to achieve net zero by 2050, which is a what world has taken, we need to come up with new carbon dioxide conversion strategies. So what we have been trying to do is that, so I'll just take you a little bit background. So if you look at how metal interacts, if you want to use low-valent mangrove species, I think I'll take you back to metal because how metals interact, if you look back, because there are a lot of metal carbonates naturally existing, such as calcite, dolomite, magnesite. So where metal interacts with carbon dioxide, and also how carbon dioxide is captured during the photosynthetic process. So if you look at several interactions, how metal really interact with carbon dioxide molecule, you can actually look at it major 4 binding modes. So I would particularly draw your attention that mode 1. So if you look back and recall the molecular orbital diagram of carbon dioxide, you can realize that carbon is having the LUMO centered on carbon and oxygen is having the HOMO. So metal can interact with the LUMO of carbon dioxide and can make a bent metal carbon dioxide interaction. And likewise, if HOMO interacts with the empty orbital of metal, it gives a eta1 oxygen, or both it can give eta2 CO or the carboxylate linkage, which is very common. You can see that it can also interact with the metal. And so if you want to mimic this kind of interaction, so I think I'll take you back also how the nature is fixing carbon dioxide. As you know that Rubisco enzyme, the lysine bound amine actually interacts with the carbon dioxide to make a carbamate linkage, which is the first step of carbon dioxide fixation. In other words, the nitrogen acts as a donor center to capture carbon dioxide, and later on in the photosynthetic process, magnesium comes and binds to the fixed carbon dioxide. So no wonder this is a nucleophilic activation, and which is also later on, several scientists have studied that this kind of nucleophilic activation can be achieved with the help of different nitrogen donor bases. And in certain cases, this carbon dioxide not only captured, but also their excess structures was determined. Now I'll actually take you through the carbene-based donor, which can capture carbon dioxide and do further catalysis on that. So let me tell you that this is one of the slides me and Guy Bertrand when we were writing the review article. So we prepared this slide to show you that Arduino, although started the first carbene actually, which is crystallized. Before that, Guy Bertrand in 1988 first isolated, which was not crystallized. And later on, you know that GRAPS2 catalyst was created with the help of this carbene. And then in 2001, Crabtree reported a new binding mode of carbene, which is we will call abnormal NAC or mesoionic NAC. And Crabtree actually described in his paper as a wrong way of binding of NAC to the metal. And this took some time after 2001. You can see that 2009, Guy Bertrand came up with a solution of synthesizing and crystallizing it, and X-ray structure of the first abnormal carbene was reported in 2009. So we have been working last 10 years or more than that with this particular abnormal carbene to develop a lot of organometallic chemistry, not only with metals, main group chemistry, and also we have used small molecular activation, and also we use for CO2 activation. So why CO2 activation is interesting, could be interesting, because I'll take you back to the paper, original paper published in 2009, where they have calculated the HOMO energy of abnormal and isomeric normal NHC. You can see that HOMO of abnormal carbene is more higher in energy than that of normal NHC. So that sort of indicates that perhaps this carbene will be more reactive towards such a small molecule. So that was the idea. We thought that we can utilize this high reactivity of this particular carbene, although this is very reactive species, but you can store inside the glove box after synthesis at -20 degrees centigrade for several weeks, and you can utilize for CO2 capture. So if you furse CO2 at room temperature with this particular carbene, abnormal carbene, so immediately it forms a carbene carbon dioxide adduct. And this is a quite spontaneous reaction with carbon dioxide at room temperature. And now if you put boron hydride as a reductant, then you can prepare boron methoxide, and you can of course hydrolyze boron methoxide to methanol. So this is one of our early report, actually in 2016 we reported, where we have shown that the very low amount of catalyst, like 0.005 mole percent of catalyst, is good enough to do carbon dioxide to methanol conversion at room temperature under very mild condition with 6,000 TON. The time we reported, it was one of the highest active catalysts in 2016 in homogeneous condition, of course. So we worked out the mechanism somewhat in more details. So what we have shown that stepwise, if you look at carbon dioxide first from adducts, then the next reaction is basically this and boron adduct, further adduct formation. The DFT supports, we did not have any experimental evidence. The DFT calculation was done by Professor Ayan Datta, and then further CO2 can be inserted into BH bond, and then further it can get converted to boron diform. Now this particular intermediate we could crystallize, and then we could see in X-ray structure. This is the active intermediates catalytically, and then it further reacts with boron to generate boron formate, and boron formate, after that it creates carbene, regenerates back, which catalyzes the process, and then it reacts and forms a methoxyboron. So with this, we started our carbon dioxide chemistry with a metal-free process, and then this carbon dioxide what we used was taken from carbon dioxide cylinder. So next question we really started asking, is there any way that you can fix carbon dioxide from air? So as you know that it's a very difficult problem, because in air carbon dioxide exists in about 400 ppm and maybe more. It's increasing more and more in air carbon dioxide. However, this is a proposal many scientists are working at this moment. This is one of the picture I have taken from Robert Keith, who has established a process where it can draw carbon dioxide from air and it can convert to methanol. But I am not sure about further details how it works. This is a company ran by Robert Keith. So what we could see that this type of carbene boron adduct, which we can prepare and get crystallographically characterized, and if we keep it in air, this kind of carbene boron adduct, it changes color within few hours from yellow to green, and it fixes carbon dioxide from taking from air, which also you can crystallize and you can see in the X-ray structure. Now, what further you can do is that you can take this fixed carbon dioxide, and of course you can see the boron part is hydrolyzed because of the moisture present in the air. And then you can treat with boron hydride further, then you can get ethoxyboron, which can be converted to methanol, or you can treat with sodium hydroxide to prepare sodium formate. So in a sense that you can prepare methanol and formic acid from air captured carbon dioxide. However, this process was not catalytic because you can see that boron is hydrolyzed and our system is not stable. So we could do only in room temperature, but in stoichiometric, not catalytic. Now I'll take you that further, not only reduction, but carbon dioxide can be utilized as a reagent for organic synthesis as a C1 source. Now, if we look back some of the literature, that carbon dioxide was used as a reagent, especially this is a formulating reagent. This is through a process called reductive functionalization, where amine can be treated with carbon dioxide and hydride. And this process can give the formulated amine, which is a very important reaction for organic chemistry. Now, if you look the literature, you can see that ruthenium and rhodium-based catalysts are quite well known in this chemistry. And later on, Kanta et al. From France, they showed that nitrogen-based or carbenes are good enough to do this reaction. You do not need any metal-based catalyst. So that was a quite nice development by Kanta et al. And then what the time we started is that it was completely missing a reaction of similar formulation process with amide. Because amides are known to be more inert because of additional C double bond O, which kind of brings the nitrogen lone pair in the resonating form. As a result, this does not work with this process like in normal carbene. So what we showed in this work, actually some time back, that carbene can be used as a metal-free catalyst for doing formulation of amine. If you look, really, I mean, there was no method available before our report which can convert amide to formulated amine. It was only known in stoichiometric, but it was not catalytic, and of course not with carbon dioxide. But we could show that carbon dioxide can be used for formulation of amide. Now, what you can do with the amide formulation is the following. You can create some value-added chemicals. This we have created in gram scale, alatamide and lanzoamide A. These are anti-larvicidal compound which can protect the mosquito transmission of malaria, and also chikungunya and dengue fever. So with this, we started asking another question actually. So it was more of a fundamental than that of application. What is thought of asking that if we can do with low-valent carbon compounds, this kind of functionalization, then why not low-valent phosphorus compounds can be utilized? Because if you look at periodic table, carbon and phosphorus are diagonally related. So if we can, we wanted to ask if we can use phosphinidine instead of carbene for the same process. Well, we have picked up the phosphinidine, which is available already in the literature. And then we tried to do this reaction in presence of silane and phosphinidine, in presence of carbon dioxide at atmospheric pressure. And so we could see an excellent yield of formulated product up to 82% yield in several examples. So let me tell you that no catalytic application was reported before this work with phosphinidine. And once again, we came up with a mechanism where phosphinidine and silane forms an adduct actually. This is mostly we could not see experimentally, but DFT calculation by Professor Arun Datta really helped us to understand what kind of interaction is going on. And then this adduct formation facilitates the carbon dioxide fixation, and it gives a silicon format, and then formal transfer happens with the activated amide to give the product. Now, I'll further move on that how carbon dioxide activation with the metal-free catalyst can do further use of carbon dioxide as a reagent. Now I'm going to talk how carbon dioxide can be used as a methylating reagent. And here I'll introduce, actually, my job has been very easy actually, because I would like to thank Eric Ribert, who has given yesterday excellent talk on NHO. So I do not need to tell you much introduction, but NHO are excellent donor in terms of, if you look at TEP, it shows that it is even better donor than that of normal carbene, abnormal carbene, or normal NHO even. So this mesoionic carbene, NHO, was prepared last year by Huntsman and co-workers. We followed the same technique. So we took from abnormal carbene, methylation with methyl iodide, and KHMDS gives you this mesoionic NHO. And you can see that this can exist in a number of elydic form where the significant negative charge is existing on the CH2. That means it could act as a very good donor to capture carbon dioxide. Now, what we could do is that we could take carbon dioxide, take a mesoionic NHO in 5 mole% at room temperature, 1 atmospheric pressure of carbon dioxide. We could do methylation of secondary amide, and in a number of examples we have shown. Some of the examples are actually anti-hypertensive drug or anti-malarial drug we could produce by using CO2. And this methylation process, when we wanted to see how the catalyst is stable in the reaction medium, then we could show that the catalyst is remaining alive in a number of successive cycles where we added substrate after each cycle, but we did not add any additional catalyst. We showed that catalytic activity is not dropping. That kind of indicated that the catalyst is long-lived catalyst. And then what we went for further consecutive reduction, because as you know that carbon dioxide to methylation involves 6 electron reduction. And then we went not only for monomethylation, but also dimethylation and trimethylation. So up to 18 electron reduction was possible with our catalyst. Just very recently published this work in chemical science. Now, the mechanism we came up with, the first step is boron, the NHO adduct, which has been crystallized and has been observed in X-ray. And then there is an insertion of CO2 in the BH bond that can be observed in the NMR. And then there is a transfer of CO2, and then there is a standard step to give you N-methylated compound. Now, so further what we can do actually, so now we could show that metal is not required to do a lot of chemistry with carbon dioxide. Now, can you integrate 2 very challenging processes such as hydrogenation and formylation or reductive functionalization of carbon dioxide? Can you integrate both molecules in a metal-free? We have been working towards that direction. So we are just developing a system where metal can be used, metal-free catalyst such as borinium ion can be used as a metal-free catalyst to do hydrogenation of the quinoline derivatives. And of course, we have done the hydrogenation mechanism with the help of detailed calculation by Professor Shapanpoti, as well as certain standard experimentation, where we have seen that this is going stepwise manner, but this is not the talk. I'm going to talk about hydrogenation. But what we could show is that a number of quinoline derivatives at room temperature, at atmospheric pressure of hydrogen, we could do hydrogenate without using any metal. And then our process, which is just showed, we can use the methylation process using carbon dioxide to get compounds of anti-tumor activity, anti-malarial drug, N-formulated compound, all metal-free and room temperature. So what we could do, we could integrate hydrogen and carbon dioxide this way to get N-methylation compound. So we start with quinoline, hydrogenation, then CO2. Also, we can prepare the anti-tumor activity, biologically active gallium-pinene. Once again, we did the same way. MnHO, the first step is the borinium, then MnHO, and also we could prepare the anti-malarial drug. So with this, I will take you to the last part of talk, that what are the variety of metal-free process you can introduce in terms of carbon dioxide functionalization, not only nucleophilic based catalyst, but also you can introduce ACT based catalyst actually. using carbon-based radicals. For some time, we have a lot of interest, and we have been developing an area where carbon-based radical have been used as a metal-free catalyst to do especially those transformations which are not known without metal-free. For example, we have been successful to do Higgs-type carbon-carbon cross-coupling, direct CH cross-coupling, CH functionalization without using metal. Right now, we're working with Hartwig-Buchwald amination process. We have successfully developed a model. We have also we have been getting successfully results on Shonogashira type coupling, where you do not need metal, but just a radical can mimic the function of metal. So we are just curious that can you develop a separate type of carbon-based radicals? And I have heard two of my good friends gave very nice lecture, Anukul Riana and Rajendra Garwal, on this radical chemistry. But what I'm trying to tell you is that how do you utilize further this type of radical? Can you use the electron transfer catalysis using this type of radical, not just after synthesis, stopping after synthesis? So what we can do, this particular radical, we synthesize starting with the same salt which we create the abnormal carbene. For example, the abnormal carbene, Guy Bertrand prepared using this salt by utilizing a base which can abstract a proton and then give you abnormal carbene. But instead of putting a base, if you use an electron reducing agent, then you can create this corresponding carbon-based radical. And what we could show is that this particular cation, if you take treat with potassium graphite in THA, and then you can create this radical, which the crystal was grown inside the globe box fridge at -20°C after extracting in Nixon. And it's a deep green crystal, actually almost black. So you can see the structure of this compound. And just to see that it does electron transfer chemistry. So what we did is that we did a control experiment by taking a very well-known acceptor molecule, that is the TCNE. So TCNE we treated with this radical, and then there is electron transfer. You back the cation and TCNE radical, which once again we could crystallize. Now you can see that after the electron transfer, it becomes red from the deep green crystal. And then you can look at the, all cationic properties came back in terms of bond length and angle, and also TCNE radical seen in the EPS spectroscopy. Now what we could do is that we could do we could take this radical as a catalyst and then take CO2, boron hydride, and at room temperature we could convert to methoxyboron, which is methanol analog, by just using very low amount of 2, which acts as an ACT catalyst. So I'll not take you step by step to the mechanism, but what we assume is that several steps are also proposed, and there are some evidence by NMR and sometimes XRD that the first is electron transfer to boron hydride to boron radical. However, I have to tell you that I don't have any experimental proof for this process. What I have proved is that after you treat with this radical, we start getting this carbene and we start getting hydrogen evolution, which have been detected by NMR spectroscopy. And then carbene, once it generates, it follows the same path we have discovered earlier and showed you in the beginning. So we could show several reactions, not only carbon dioxide, but also aryl iodide to deiodination reaction, and also hydrosilylation reaction using this set chemistry, using this particular radical. Now, this metal-free catalyst, we have written a recently perspective article that how to design metal-free catalyst in this area. And I'll just quickly take you 2 reactions, which are brand new reactions, which are discovered, which we have developed, which is not known with carbon dioxide. One is methylation of amides, which we just got the result we are developing right now. Methylation of amide was not known earlier, but right now we have developed method how to do CO2 for introducing methylene group in between 2 amides. And also we have developed another method which is not known with carbon dioxide, is a thiol formylation. So you take thiol, take formylation, do carbon dioxide as a formulating reagent. Using the metal pre-catalyst, you could do thiol formylation. So with this, let me tell you that there are several, I mean, this is the uphill process that from, if you want to take from lab to bench to market, because you need to come up with a lot of solution. One of the issues we need to think about is that silane hydride and boron hydride, whatever we are using, they are creating Si or BOB byproduct. So these byproducts are basically sacrificial. If you can regenerate by electrochemical process, or if you can make whole process as a, heterogeneous. So that is what we are right now working, some of the areas. And with this, I would like to thank my group. Shaumaresh actually started this chemistry with this carbon dioxide to methanol reaction. And then Pradeep worked on amide formylation reaction. Shubir is working on NHO catalyst, Srijyoti on phosphinidine, and Arpon has worked on radical-based carbon dioxide fixation. And I'm thankful to IISER Kolkata and STARS program for funding us on this project. And I'm grateful to Shopan Pati and Professor Ayan Datta for their useful calculation and DFT calculation, especially, which are very helpful to understand the mechanism. With this, thank you very much for your attention.
Thank you, Professor Mandal. It was a very exciting talk. And we have time to ask for 2 quick questions. And Prabhu, please.
Thanks, Shankar. Thank you very much, Professor Swathi. Nice work and nice presentation. So my question is from slide number 24, where you are trying to explain the mechanism of CO2 conversion using ADACT.
Yes.
Yes. So it's about the intermediate 1A versus 5. In 5, it appears that only SiH2 is active for this particular process. Can't you do the, I mean, have you checked the direct reaction between silane and CO2?
I'm sorry, what is the question once again? Come again.
So my question is about the transition state 1A versus 5.
Yeah.
Right. And in 5, you got a silane as intermediate.
Yeah.
Right. It appears that only silane is actually mediating the entire reaction, but not the phosphine. Have you ever tried to...
Oh, we did the blank reaction, of course.
Yes, okay.
We did, of course, blank. Without that, it does not work. Right? So that's the first reaction.
Without phosphine, it doesn't work.
Without question, yeah, of course.
Right?
Without not only phosphine, if you
need
put
a
normal
phosphine.
carbon also, it doesn't work. Normal NaC also, it doesn't work. So this is a very tough reaction actually, amide formylation. So of course, there's a blank reaction we did. It doesn't work.
Okay. Ajay, please.
Yeah, you need a phosphine, right?
I'm sorry?
You need a phosphine to do this particular process.
Yes.
Okay. Thank you very much. Thank you.
Sure. Thank you.
Congrats.
Yeah, please, Ajay, please.
Hi, Swadhin. Excellent talk.
Thank you.
I was impressed with your carbon dioxide reduction with the NHC, and especially those efficiency of the catalyst. I was quite surprised when you decrease the catalyst loading, the efficiency goes up. What is the? I was curious to know, like, what actually happens during such processes.
Like.
Yeah, here.
Oh no, actually, this is a TON.
Yeah.
So if you have more catalyst, actually TON will go down, right? I mean, turnover number. So did I get?
Yeah.
Turnover number. This is a number of molecules.
Okay.
Catalyst is converted. Right?
Okay. Yeah.
It's not conversion.
Okay, okay. Second short question. You had this borinium cation.
Yes.
And what role does this carbene have at the boron center? Is it giving some, is it inducing some electronic properties which?
It's a very good question. Actually, we are trying to understand because, you know, I mean, we created a number of borinium cation. Okay. So with different types of carbene. So carbene has a very important role actually. So we actually created a series of borinium ion. Out of 3, 1 is working, the other 2 are not working. So you need to maintain electrophilicity of boron, because if that you can monitor. I did not show you those data actually. So if you take the boron NMR, more electrophilic boron is required for hydrogen activation. So if you are giving a more donor carbene, it does not activate hydrogen. Okay.
Yeah, yeah. Excellent talk. Thank you very much. Thank you, Shankar.
Okay, yeah. Anukul, one short question. Yes.
Yes. Yeah. So I have a Professor Mondal, I have one quick question. So the carbon dioxide with the abnormal carbene, that's adduct. Is it what will be the thermal property? Is it stable, or under thermal condition it degraded to or release the carbon dioxide?
Oh, the adduct. The adduct.
Yes. Yes. Compound 3A. Compound 3A.
So carbene and adduct, carbon dioxide adduct. Right?
Yes. Yes. Yes.
We did not have data actually to tell you, but we do.
No, I can tell you why I'm asking. Why I'm asking.
Yeah, right. Got the
two reasons. Whether it could be form a release the carbon monoxide, it could have a CO corresponding carbonyl, or the oxygen will go away, bind with the carbon monoxide.
Honestly, we did not do it. It's an interesting proposition. Actually.
Yeah, actually, the if for example, if you have a adduct with the carbon monoxide, then maybe the structure will be the ketene type. The point is that your carbon dioxide, there is a one, and oxygen is getting a release like a silicon oxygen also. So if you have a CO, then one oxygen no need to be there. That I don't know. That's why the thermal stability. That's why I'm wondering. What about the?
No, we did not do any study on thermal stability. We do our
and then the corresponding pose. Yeah. Okay, so congratulations for your fantastic work. Okay, thanks, Professor Mondal. Thanks, Professor.
Thank you, Professor Mondal, for a very interesting talk. And yeah, thanks a lot. We'll move on to the third speaker of this session, Professor Adinarayanan Dodi from IISER Berhampur. Professor Dodi, around?
Yeah, I'm there.
Yeah, please, the floor is yours.
I'm here. So could you able to see my screen?
Yes, please go ahead.
Yeah, full screen you can see, right? Able to see.
It does not on the slideshow.
Oh, really? So then I have to stop sharing and share it. Yeah, maybe now it's perhaps.
No, it's not yet on the slideshow.
Now?
Yeah, it's fine now.
Yeah, okay, good. Thank you for the chair for introducing me. Today I'm going to speak about some anhydrocyclic carbene supported main group adducts and the novel ligands for stabilization of reactive organometallic fragments. But first of all, before I go to my talk, I would like to honestly tell that to start our main group chemistry in my transit campus, it takes time, as you know that. So we have some very good results, but most of the results are still inconclusive. So I need some time to make them more conclusive. So based on that justification, I decided to speak about a little more from my postdoctoral work and recent work related to my postdoc stay. Okay, with that, I first would like to thank the organizers of TRIPLM2, and also I would like to exclusively thank Dr. Nambenna as well as Dr. Krishnan for their kind invitation to participate, to be part of this main group chemistry conference. Actually, I'm really excited to see a lot of excellent talks on low valent as well as carbene chemistry. In the next few minutes, you will see the lot of carbene chemistry. So before going to my talk, let me quickly use this platform to thank DST Serb for their generous support through my Ramanujan Fellowship in 2019. then also recently awarded a Startup Research Grant. I'm really thankful to SERB and DST. And of course, my ISR Barampur for seed grant support. So with that, let me move on to the today's relevant topic of main group chemistry. So main group chemistry, since almost I think 20 years, has expanded its branches towards several areas. It's not anymore this classical main group chemistry, but now it's advanced main group chemistry. This is perhaps, it has an excellent applications in diverse fields. For instance, ancillary ligands in homogeneous catalysis, effective tools for stabilization of unusable species, for example, and most importantly, the material science. Actually, it has a lot of applications. So I'm always wonder why main group chemistry has expanded like anything since 20 years. According to my understanding, that I would like to put it on this platform, that when you consider mostly of group 13, 14, 15 elements, these are +3, +4, and +3 and +5 oxidation state. These are not really greatly interesting. These are sort of classical main group chemistry. But when you go to the modern main group chemistry or advanced main group chemistry, that is mostly follows that by reduction. If you reduce these high valent species to their low valent species, which is as possible as low valent or low coordinate state. So in this state, we generate free electrons or lone pairs or radicals. So as we know that in this physical state or chemical state, such compounds are not stable. They try to undergo oligomerization or polymerization, etc. And they're not stable actually, right? So then what they do, they try to they get back to their normal oxidation state. So that's what exactly we exploit the reactivity in terms of FLPs, activation of small molecules as ligands for the stabilization of unusual organometallic and transition metal chemical compounds. And most importantly, as ancillary ligands, for example, metal-free catalysis, as well as precursors for CVD applications. So we have seen since 2 days excellent talks about group 13, 14, and 15 elements, all the low valent main group compounds. But today, let me confine to group 15. So in group 15 elements, just consider these hydrides, ammonia, phosphine, arsine, stibine, and bismuthine. Just remove 2 hydrogen centers, hydrogen atoms from these species. Then we end up with nitrines, phosphinidines, and arsenidines. Actually, these are most low valent species of this group elements. As we all know that this kind of species is not stable at room temperature. They are only stable at the organometrics or in the gaseous phase. So if we can able to trap them using suitable ligands, and store them, let's say in a Schlenk tube or Schlenk flask in a glove box, one can able to do some new chemistry or new applied chemistry, for instance. So that's what exactly the work has been designed. So how to stabilize such kind of compounds? As we know, once we start from the nitrines, in my opinion, this is one of the phenomenal work from Bertrand. This is one of the naked nitrine reported by Bertrand in Science 2012. So nitrine chemistry, as we know, is greatly expanded. It has great application. So let's come down the group phosphinidines. So what are the phosphinidines? As we have seen already, Professor Mandal nicely showed excellent applications of carbene phosphinidines, CO2 activation and its conversion to useful compounds. So such kind of element 1, these are phosphorus 1 compounds. Since they have 2 lone pair of electrons, mostly, let's say if you consider it as a singlet, when they attach to the metal centers, they do exhibit metal phosphorus multiple bonding. That you will see in the next slides. So those are the phosphinidines. Such kind of phosphinidines, first time seen, observed experimentally by Gasper. They reported in JACS 1994. He could able to achieve this generate the free phosphinidine in situ by photolysis of the phosphorus 3 compound. So then recently, this is one of the milestones of main group chemistry, in my opinion, that Bertrand could able to isolate a naked phosphinidine center, actually phosphorus center, which is stabilized by anhydrocyclic phosphine ligand. So by employing a very sterically bulky air double star ligand, because it protects this the naked phosphorus center. Otherwise, it will undergo oligomerization or dimerization, etc. So what I mean to say, the ligand plays an excellent role for stabilization of such phosphinidines. So since today I might talk about group 15 elements, let me take you to group 15. In group 15 elements, in the trivalent state, they have lone pair. Let's say we reduce them with 2 electrons. then we can generate 2 more electrons on the main group element 1 compound. So as we know that these are highly elusive species, so they undergo dimerization or oligomerization. They are highly reactive. So somehow we have to engage these free electrons into bonding. So this is what exactly the great applications of anhydrous cyclic carbons come into the play. Anhydrous cyclic carbons are excellent tools to stabilize such kind of elusive species, because as we have seen just now, Professor Mandel's work, that the carbons has these PG orbitals, which are sort of perpendicular to each other. So then these electrons can be somehow engage them into the back bonding. So what happens, these guys are not that much elusive as when they are in the free state. So anhydrous cyclic carbons are used extensively for the stabilization of such elusive species. So today talk, we will see that carbene nitrines have been greatly studied, and they have been employed in not only in coordination and organometallic chemistry, but also in homogeneous catalysis as ancillary ligands. So what about their other, other brothers? For example, carbene phosphinidine, carbene arcididines. Can we be able to develop new synthetic procedures for neutral as well as anionic species? So that's what our target. Since if we have such kind of compounds, one can use them as ligands for trapping or isolation of unusual organometallic fragments, or use them for the activation of small molecules, for example. So on. There can be many applications that can be studied if we have such compounds in access. Okay, so let me quickly tell you the history of these phosphinidines. The carbenes, as you know, anhydrous cyclic carbenes especially were introduced by Ardvingo, stable ones, crystalline ones in 1992. This is perhaps the first applications of anhydrous cyclic carbenes for the adduct formations of main group compounds. For example, he took up Ardvingo tetramethyl carbene, he treated this compound with tetraphenyl phosphorus compound. He could able to break this pentamer into monomeric, then it forms a carbene phosphinidine adduct. But quite recently, Bertrand able to develop new synthetic procedure by simple potassium, caseate reduction. Actually, with that method also, one can able to synthesize a series of carbene phosphinidine adducts. So we thought that the molecular structure of these compounds were not reported until then. So we decided to see the molecular structures and a little bit about their electronic structures, electronic details. As you can see, these compounds can be considered as inversely polarized phosphoalkenes. Please remember, inversely polarized, because the carbene carbon takes a positive charge, is other way around supposed to be. The phosphorus takes a negative charge when you polarize these double bond towards the phosphorus center. So then it can have two lone pairs of electrons actually. So that can be seen nicely, the NBO orbitals, that is CP, phosphoalkene type structure, the double bond, and there is a lone pair which is of just according to the shape you can see it's most of S character. And if you put two lone pairs, this is the extreme version, the carbene with arrow bond. So then you will have a sort of banana type of electron density around the phosphorus center, which means that it has a lot of space around the phosphorus. So these compounds can be new candidates towards activation of small molecules or to attach them into the loose acidic species, because they can be act as two lone pair electron donors. Actually. So we first need to understand their coordination behavior. So as you know that rhodium scale is one of the very well established procedure to understand the coordination electron donating character of such compounds. So we have made a rhodium complex, of course, the square planar complex. As you can see, phosphorus makes a rhodium bond as due to the doublet. And when you compare this average touching frequency together with similar compounds, for example, NHOs, anhydrous cyclic olefins, carbodycarbenes, other carbenes, including triphenyl phosphine. Please look at this, my cursor, that triphenyl phosphine gives 2052 as a average touching frequency in the phosphorus 3 form, but once you make it phosphorus 1, it comes to 006, which means that these phosphorus 1 compounds can be strongly electron donors with respect to the phosphines, and these are also comparable with anhydrous cyclic olefins. Actually, we have seen similar scale by Eric Reward in the last 2 days. So this shows that these ligands can be promising ligands for coordination chemistry, for instance. So using on that, we have exploited the two lone pairs on the phosphorus center. So we made monometallic as well as bimetallic complexes of coinage metal, for example, copper, silver, gold. And also molecular structures clearly shows that the phosphorus here takes up a pyramidal geometry, which means that there is one lone pair available on the phosphorus. If you occupy that lone pair also, now phosphorus takes up a tetrahedral geometry. Both lone pairs are attached on the phosphorus center. Okay, so we did not stop at the place. So since these bimetallic complexes has 2 chlorides on each metal center, so we try to explore their reactivity by reacting those compounds with sodium barf. Then we have got, irrespective of how many equivalents you use sodium barf, we always used to get these tetrametallic complexes. For example, tetra copper, tetra gold, these are dicationic complexes. When you look into the molecular structures, the solid state structures, they do exhibit quite strong cuprophilic as well as orophilic interactions. These are in the range of strongly coordinating copper-copper or gold-gold interactions, as a matter of fact. So then we have seen here, the chlorides are somehow blocking the cluster actually. They always bridge. So we wanted to get rid of this chloride. So how do we get rid of this chloride? We took up the same digold complex, but now we have done the same chloride abstraction reaction, but now in the presence of THT, tetrahydrothiophene, because gold likes to have bond with sulfur atom. So then we did excess THT, then we could be able to block the chloride bridging gold atoms. That we can see from the excess structure now, gold is sort of occupied by the THT ligands, which are sort of labile that we can find out at room temperature from the NMR spectroscopy. So then once we have these 2 trimetallic as well as bimetallic dicationic gold complexes, we made some fun reaction that we took up these 2 clusters separately, gold compounds separately, which are only soluble in THF or dichloromethane. We did a very simple reaction, methanol reaction with EDA, ethyl acetate. So then what happens, we could see within 12 to 15 minutes, there is a 100% conversion of this the esters. So then with that, and you can also see nicely, nitrogen gas evolves immediately. Once you put the catalyst in 1 mole%, you immediately see nitrogen, a lot of nitrogen gas comes out, which also evidence that these 2 carbene gets generated at the gold center by release the dinitrogen gas. So with that simple motivation, we employed these 2 catalysts, these 2 gold complexes, for instance, into little more complicated, organic cycloisomerization reactions. For example, enines. So once we employ these 2, we can see we did not isolate, we did not separate these 2 compounds, but we have made it as a mixture of those 2 compounds. You can see that within 1 to 2 hours, that we got excellent yields. For example, almost quantitative in case of catalyst, like one and both catalysts. For example, AA gives an excellent yields, almost quantitative, but B is not really as good as A case. But more or less, both are comparable. Both have similar catalytic activity. So far we have seen the coordination chemistry or organometallic chemistry of carbene phosphinidine derivatives. These are neutral species, right? So let's say, can we be able to isolate or design a synthetic procedure by which we can access a synthon, NHCP, and it's sort of like an heterocyclic carbene phosphinidenide synthon? How is it possible? Can we get rid of this R group somehow so that we can have, it can act as a NHP mononegative center? So what is the use of that? If we have such kind of organometallic motif, one can able to load the phosphorus center with 3 metals. Of course, as we know that phosphinidenes are known to bridge bimetals like 2 metals, 3 metals, exactly. But now we have the carbene attached to the phosphorus center. So that is sort of interesting part. So how do we able to make such kind of moiety? Then we have seen a paper, JAX. Somebody reported a difluoroimidazolidine, so some by chloroimidazolium chloride. So we made that compound and reduced the phosphorus 3 center to phosphorus 1. You can see now we have used, because TMS fluoride can go away easily, then phosphorus 3 becomes phosphorus 1, carbene phosphorine derivatives. And interestingly, these 2 compounds were subsequently and easily converted into the phosphorus 1 parent phosphinidines, carbene parent phosphinidines in quite good yields. Of course, phosphorus NMR spectroscopy is handy in this case. You can see a beautiful doublets at -46 in highly Scheler regions with coupling constant of 165 Hertz. So the molecular structure of carbene PTMS derivative clearly shows that the imidazole ring is nicely, the carbene ring and phosphorus are in the same plane. but TMS is like a big proton, it is out of the plane. This is the molecular structure of the compound. So then we have employed this compound into transition metal chemistry to isolate or trap some new and unusual organometallic fragments. For instance, when you treat this compound, as you can see now, the TMS can go easily when you treat that compound with metal chloride containing organometallic compounds. For example, see that carbene PTMS reaction with parasamine ruthenium chloride as well as CP star rhodium chlorides, they exclusively yielded their respective carbene phosphinidine derivatives. When you look into the molecular structures of those compounds, you can see that they do show the formation of piano two-legged piano stool type of molecular structures in the solid state, and their phosphorus NMR chemical shifts did indicate the presence of multiple bonding character between the metal and phosphorus, which is a true characteristic properties of phosphinidines, for instance. So similarly, we also extended the same procedure to the heavier metals, for example, osmium and iridium. So we got similar molecular structures. So this shows that using this ligand, one can able to stabilize 16 valence electron organometallic fragments that can be stabilized by carbene phosphinidenide. This is now negatively charged NHP unit. Okay, so far we have seen monometals. What about bimetallic? As I said in the beginning, we have two lone pair of electrons on the phosphorus center, which are now engaged in pi bonding. So we can also pull down those pi bonds by reacting with the gold chloride, for instance. We could able to isolate a series of, again, bimetallic complexes. Now two metals are sitting on the low valent phosphorus center. And the molecular structures did indicate, right, the two metals are on the phosphorus center, but we still have another lone pair on the phosphorus center because this is carbene P minus. And yeah, as you can see, these heavy metals always show some sort of interaction in the solid state. The gold has some sort of interaction with the osmium, which is 2.63 angstrom units. So what about trimetallic? So this is one example of trimetallic complex. We treated this carbene PTMS with the rhodium cord dimer. We could able to see that the phosphine, carbene phosphinidine, like just two metal centers that can be seen as a triplet because phosphorus coupling with two rhodiums, and the molecular structures clearly shows the formation of bridging phosphinidine supported dirhodium complex. Now phosphinidine center now P has a pyramidal geometry, which means that it has a lone pair of electron. In other words, this compound can still act as a ligand towards any loose acidic centers. Then we have thrown another equivalent of gold chloride and isolated in good yield the respect to trimetallic complex. Now we can see the two rhodiums are still intact. That is, can be seen in a triplet form, and the molecular structure clearly shows now the phosphorus has two rhodiums and one gold, where phosphorus takes up tetrahedral geometry. So this is how one can able to, like in a stepwise manner, can load more metals on the low valent phosphorus center. Okay, so far these are you have seen that these are bridging. What about terminal? Terminally, can we able to coordinate metal center? So here is one example. When you take the CP star iridium chloride phosphinidine derivative, when you treat with one equivalent, you get bimetallic complex. If you give two equivalents of gold chloride, you can able to put three metals in the terminal fashion. None of them are bridging actually. So you can see this is bimetallic. This is always a true trimetallic complexes that you can see two gold chlorides are sitting on the low valent phosphorus center, which is supported by an anhydrous cyclic carbene ligand. Okay, so as we have seen that these compounds are also interesting precursors or starting materials for activation of small molecules. Of course, let's say if you consider hydrochloric acid as a small molecule, we treated these compounds with triethyl ammonium hydrochloride. Now hydrogen chloride nicely adds up to along the metal phosphorus bond to give 18 valence electron complexes. So because you may ask me why you have not used hydrochloric acid. So we have used hydrochloric acid in ether. It simply destroys the compound because these are highly reactive. So that's what we have gone a salt actually, so that we can do a controlled reaction so that the hydrogen chloride can add up between the metal phosphorus bond. This is one representative example to show that the presence of pH bond. You can see the phosphorus NMR, which is minus 75 ppm as a doublet it arises due to the pH coupling, which is around 160 hertz actually. Yeah. So far we have seen one set of neutral complexes. can we able to make cationic complexes with different geometry? So as I just now said, these carbene NHCP, this synthon, this can act as a mononegative ligand, which can be considered as analogous to aryl phosphonidins. Actually, you can see this also aryl phosphonidin P1 compound. This can also be NHCP minus compounds actually. So these guys can be considered. They do have isolable relation, provided we must have sterically bulky R groups on the phosphorus interaction. This is very important. Otherwise, they undergo oligomerization or dimerization. So Lamartz et al. Made excellent chemistry with the aryl phosphanidins. He made a series of heavier transition metal chemistry as neutral compounds containing this sterically bulky phosphanidin ligands. So we wanted to develop similar chemistry, but now with the NHCP synthon containing 16 valence electron complexes. So here, as I just showed you in my previous slides, the NHCP multiple bond containing compounds, for example, with respect to the metal P bond, you can consider this as an G isomer. Once we remove this chloride using sodium bar in presence of a loose basis such as trimethylphosphine or sterically not bulky anhydrocyclic carbenes, you can able to get rid of the chloride and instantaneously you can stabilize the metal center with that ligand we used. For example, see that this ligand trimethylphosphine and tetramethylcarbene can nicely coordinate with metal center and thereby it becomes cationic complex. Please look at this. Now, before in the neutral version, these are G isomer. This, for example, once we make them cationic in presence of a sterically not bulky ligand, now they become E isomers. For example, look at that metal P. If you consider metal P as a double bond, these ligands are now trans to each other. If you look at this osmium P, now the osmium P double bond is stabilized by two different anhydrocyclic carbenes actually in a trans fashion or like an E isomer. So these compounds are sort of rarest compounds where metal phosphorus multiple bonds are stabilized by two carbenes, two different carbenes. This concept is quite well established in main group chemistry, for example, diphosphorus, diarsine, diboron. So in a similar way, one can also consider metal P multiple bonds which are stabilized by two different anhydrocyclic carbenes in a trans fashion. So that can also be seen nicely from their molecular structures. They are trans in they are coordinated in a trans fashion. It's very similar to that iridium phosphorus chemistry. We have done that in case of trimethylphosphine and carbon monoxide. We are isolated their respect to E isomers. For example, in case of CO, it is only trans isomer or G isomer, but in case of tetramethylcarbene, now it is E isomer. Okay, so these are the molecular structures. You can see the CO. In case of CO, it is very small ligand that can nicely sit into this small space. Now it is a G isomer, but in case of two carbenes, this is sort of E isomer. So this slide is quite important that when you look into the resonance structures of these two compounds, Weber bond indices, for example, carbon P bond length is mostly of single bond, but in case of metal P bond, it is sort of more than one. So it means that one can say that the metal P has a multiple bond character that was also established from the 31 phosphorus NMR chemical shifts. You can also see the NBOs, right? The metal P pi bond and sigma bond, and we still have a lone pair which is of S character actually in these compounds also. So as I just now said, not only the metal phosphorus multiple bonds, you can see the shortest bonds, but also the phosphorus NMR chemical shifts can also be seen that, right? These are highly deshielded, low field shifted chemical shift that also indicates the presence of metal phosphorus multiple bonds. So very similar to the carbene phosphorus chemistry, we also done similar molecules with arsenic. For example, using this difluoro compounds, we could able to reduce arsenic 3 now to arsenic 1. This is carbene arsenidine. You can consider that. And we could also stabilize their respect to parent arsenidines, which are stabilized by anhydrocyclic carbenes in pretty good yields. So the NMR of one of the simplest derivative, you can see that is IMS arsenic hydrogen compound. So you can see nicely the presence of arsenic H attached to the arsine as a sort of triplet and a doublet to the backbone protons. And all those molecules were structurally characterized. And we also employed these compounds into the coordination chemistry. You can see we used this compound and treated this CP star iridium chloride and isolated the respective NHC arsenidenide supported iridium-3 compound. And we can see the molecular structure again. It also shows like a sort of two-legged piano stool geometry, which is very similar to the its phosphorus derivative in the solid state. So let me use this opportunity to show a little more hardcore main group chemistry radicals. Since we had a beautiful starting material, which is carbene phosphorus TMS, which is phosphorus 1. Now this very well established carbene arsenic trichloride. Now it's arsenic 3. Can we able to couple them so that one can able to isolate arsenic monophosphide? Right, arsenic monophosphide can be combined in this modular procedure. So we reacted with phosphorus 1 with arsenic 3 and isolated the respective dichloro arsenic phosphorus derivative. So this was again used, treated with 2 kilograms of potassium graphite and isolated the respective dicarbene supported in a homoleptic fashion, dicarbene supported arsenic monophosphide. Right, and the phosphorus NMR chemical shift minus 60.7 ppm nicely supports the formation of arsenic P compound. This is the molecular structure, which is very similar to the its diphosphorus diarsenic compound, and also very similar to that phosphorus derivative, which also takes up trans band fashion with a very similar bond length, which is reported in the literature, where the phosphorus arsenic phosphoarsine was also reported in the literature in 1983. Okay, since we have this neutral heteroleptic, sorry, this is homoleptic. This is now heteroleptic. Now we can see 2 different carbenes were used to stabilize this arsenic P in heteroleptic fashion. So this was dark red compound. We treated this compound with ferrocyanil PF6, and we were able to isolate a radical cation now. This is a sort of intermediate to the dication. So you can see the molecular structure of this compound very similar to the the neutral arsenic phosphorus compound, and the radical nature can also be seen nicely from the EPR spectrum, that a sextet is nicely matches with the simulated pattern. So what about SOMO? The singly occupied molecular orbital nicely shows that the radical is somehow now localized on the phosphorus and the arsenic centers, right? Very similar to the diphosphorus, dicarbene diphosphorus monocation. What about dication? So dication, we could also make that compound heteroleptic, dicarbene stabilized heteroleptic arsenic monophosphate dication. We took up this compound, treated with gallium trichloride, so thereby it nicely gives a dicationic arsenic monophosphate. And now you can see the phosphorus NMR chemical shift, which is plus 464, which is quite low field shifted, deshielded region. So this is also indicates there is a presence of phosphorus multiple bonding with any other atom. So that is also says that we can have a phosphorus arsenic double bond character in this dicationic species. The molecular structure also shows clearly a trans band geometry, but now the arsenic P shorter bond length with respect to the monocation as well as the neutral species. Okay, this is the HOMO of the compound. You can see the pi bonding character between the phosphorus and arsenic derivatives. So with that note, I would like to conclude my seminar. I hope I am at the time. So I hope I could able to show you some new chemistry of carbene phosphanidine adducts. In the beginning of my talk, I discussed the electronic characters of this carbene phosphanidine compounds. These are strongly donating electronic ligands towards the transition metals, for instance. We could also develop NSC analogs of nucleophilic phosphanidines, which is very similar to the aryl phosphanidines. Thereby, we could able to isolate a series of ruthenium, rhodium, iridium, osmium cationic complexes, which has metal phosphorus multiple bonding characters. And I hope I could also show you how we have isolated a series of carbene supported parent phosphanidines as well as arsenidines and their molecular structures. And of course, we have used them as ligands in the transition metal organometallic chemistry. So I also showed you that how we can stabilize the carbene phosphinidine compounds by monometallic, bimetallic, as well as trimetallic derivatives. And I could show that. I discussed also the molecular structures of those compounds. At the end of my talk, I discussed that how we have synthesized homoleptic as well as heteroleptic dicarbene supported arsenic monophosphide as well as more arsenic monophosphide radical cation as well as dicationic species. So with this, I would like to use this opportunity, this platform, also thank Professor Matthias Tang for his kind and generous support during my stay in 2019 for a few months in his laboratory. And I also would like to thank Dr. Thomas Bannenberg, who did a lot of excellent calculations, NBOs and DFT, and also Duke Bockfeld, who made excellent contributions to the single crystal X-ray measurements. And lastly, I'm very much grateful to my group at IISER Berhampur. Here you can see all my PhDs and master students at IISER Berhampur. So with that, thank you all for your kind attention. Thank you.
Thank you, Dr. Dodi. We have time for one short question. Ajay?
Yeah, Adi Narayana. Quite an interesting talk. So this antimony hydride, which you are talking about, or is the arsenic hydride.
Arsenic hydride. Yeah.
Sorry, yeah. Have you tested any reactivity? Yeah, like how polar this ASH bond is?
No, actually, in our hand, for example, these compounds, right? These are highly reactive species, actually.
Is it a polar bond or is it like a pure covalent bond?
Maybe I would consider it as more towards covalent, actually, rather polar, actually. Yeah. But the unfortunate thing is that these compounds are highly light sensitive, for sure. Immediately you see arsenic metal, in the black form. It's better to store them at low temperatures. So difficult to handle them as a matter.
Thank you.
Okay. Thank you, Dr. Dodi, for a nice, interesting lecture. Yeah. With this, this session is coming to an end, and I'm handing over this to Krishnan.
Yes. Thank you, Shankar, for sharing this session. And I also take this opportunity to thank Professor Alcaraz and Professor Swadhin and Adi Narayana for their very inspiring presentations. So since we have some couple of minutes, we'll start for 20. Yeah, 5 minutes late. We'll start in 5 minutes. Yeah. Students, if you have any queries, anything, you can interact with the whoever you are interested in, over in the online.
Hey, Krishnan.
Yeah.
What has been the attendance? Because we have YouTube also parallel running, you would not know the actual attendance, but here only about 70 to 80 people attending all the time, I think, right?
So it's around 65, sir.
No, do you have any estimate of the YouTube hits? How many people are attending in the YouTube?
Yeah.
For example, yesterday I myself chose to attend in the YouTube. Although it was 30 seconds delayed, that was much more clearer. And then also you can rewind and fast forward,
Yeah, around 20 was there.
Okay.
YouTube. Yeah. So here I think in Zoom around 60 to 90 also it went.
Ajay Venugopal is still hand raised.
That's the old one, I guess.
I know, I'm just kidding. So where is the meeting going next? Going to Pune, is it?
No, sir. It's IIT Hyderabad. We'll announce at the end.
Yeah. So 25 is Bombay or 24 is Bombay?
Probably 25, sir.
Are they going to do it after 1 year or after 2 years? Better to go back to the whole cycle.
Technically, we planned 2 years after 2 years, but this one got postponed.
Yeah,
So
that's what I'm saying. Next meeting, better to do it next December, not to postpone it, for 2 years, 1 more year.
Okay, that's fine, sir. That's fine. Yeah.
That's what I would say. Because that makes it anyway 3 years since we met in 4 years since we met in Bangalore. Okay?
Yeah.
This is only an online meeting. But this is my suggestion. Of course, talk to VC, Bala, KCK, and other seniors. I would say that let Hyderabad guys do it next year, and then the 24, the Bombay guys can do it. Like this.
Yeah, absolutely fine, sir. Let them decide.
We should not collide with the MTech. It's the only thing that I want to say.
KCK?
We should not collide with MTech.
I know.
Because MTech, I don't know how long they're going to postpone it. There is a problem there. They also face a problem.
MT, I thought this December he's going to do it, but I think nothing happened after that.
Yeah, nothing happened because I think he's not able to do it often anyway. So we don't have any news about that one.
Okay.
Sir, good afternoon. Prabhu here. Hello, sir. Good afternoon, all.
Prabhu.
Sir, we have planned to conduct this conference along with the University of Hyderabad. And, as you discussed, as you said, we should actually look at the MTech schedule. And so in case if it happens in December 2022, then we should actually think about it, sir.
Anyway, just check it, because I remember when the first meeting happened in Bangalore, we just talked about some milestone years.
Yeah, so, 2018. So after that, every 2 years, that's what we discussed.
Anyway, I think 24 is okay. I think for Bombay, 25 is also okay, Bombay. Because our Bala would, we have to celebrate Bala's birthdays. I mean, that's what I'm looking at 24,
We should make sure that this COVID disappears.
The COVID, I see.
That is the problem.
KCK is not going anywhere for another 5 to 10 years. Okay, we have to learn to live with it. Okay, it will come back Omicron and then E-micron. Names only will change. This is going to be
but your zinc compounds also look like that only,
Yeah, that's what I'm saying. You don't go away. Only I have to retire from zinc compounds to retire. Okay, same way. I think you have to learn to live with corona, wear mask and take care, and then keep doing things.
You deceive them by using your zinc. That they look like that only. Some of your zinc compound. I think one of them. I thought they look like that.
Oh, you're saying that? I thought you were saying that my zinc compound I'm doing for long number of years.
No.
I'm just kidding. I know.
I think Mukesh is here.
Mukesh is there.
Can we start?
Hello, sir. Yeah, we'll start.
Good evening.
Yeah, good evening. Okay, so let us start. So the last session of this conference will be chaired by Professor Vijay Anand from IISER Pune. Anand.
Thank you, Krishnan. Welcome you all to this concluding session of this very interesting and well-organized conference. In fact, we had very good talks for the last 2 days, and today also we had very good talks. And we had a very befitting person to conclude this session. And we have with us Dr. Mukesh. He is a professor at the Indian Institute of Science at Bengaluru. He did his PhD from IIT Mumbai, and later he had a postdoctoral stint in the United States of America, and later he joined IISc. He is one of the most accomplished scientists that we have in our country. He has been recognized by various awards. To name a few, I think he is the member of all the 3 Academy of the Sciences. He has been recognized with the Santi Swarup Bhatnagar Award. And of course, he's also on the editorial and advisory boards of many journals, both in RSC, ACS. And with this brief introduction, may I now request Professor Mukesh to speak on his talk, which is entitled as The Main Group Elements of Life. Professor Mukesh, please.
Yeah, thank you very much, Anand, for the kind introduction. Good evening to all of you. and I take this opportunity to thank the organizers, Dr. Krishnan and the organizing committee for inviting me to give this talk. And I thought, some of the main group elements in biology, and we do a lot of biological studies now, and I try to skip as much as the biology as possible, and I will try to focus on a couple of aspects. Just to share my screen. Can you see the slide?
Yeah.
Yeah, very much. Yes, we can.
Oh, yeah, thank you. So I picked up this title, The Main Group Elements of Life, and how many of them, main group elements playing key roles in biological systems. And I'll start with the periodic table. As you all know, 2019 has been celebrated as the International Year of, Periodic Table. If you take this periodic table and we are familiar with all the elements, how many of them are biologically important, right? And the first question that we ask when we start, try to understand the elements, is life organic, right? You look at the composition of the Earth's crust and the human body, right? And if you look at the number of atoms present in biological systems, carbon, oxygen, hydrogen, nitrogen, phosphorus, and sulfur comprise more than 98% of the human body. So like carbohydrate, nucleic acid, protein, hormones, and vitamins. So initial look at this will give an indication that life is organic, right? But there are also metal ions which do play important roles. If you compare metal in seawater and the metal ion in human plasma, if you look at iron, for example, seawater is very less, and plasma is, if you see the ratio, it's 400,000 more in human plasma than the seawater. Zinc 250 times, copper 1650, molybdenum, cobalt, chromium, vanadium, manganese, nickel. So when we talk about biomolecules, we talk about the carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur to some extent. And then we go to metal ions, right? All of them are transition metal ions. What about the main group elements, other heavier main group elements, right? And the human diseases related to metal, either deficiency or excess can lead to a problem, right? The calcium deficiency can lead to osteoporosis. Anemia is related to metal deficiency as well as excess. Lung diseases, psychotic disorders, heart failure, convulsion, Wilson disease, both copper deficiency and excess can lead to diseases. And when we talk about metal ions, generally people think that they are poisons, right? They are toxic. When you say metal, toxic. But all things can be poisons, right? It depends on the dosage, individual health, and way of administration. And if it exceeds certain concentration, even the essential elements become toxic, right? So in biology, one need to understand how much of these elements are present. So I tried to, summarize how many elements are important for life. So we can say approximately 28 elements. They can be bulk biological elements like sodium, magnesium, potassium, calcium. And if you consider the main group elements, carbon, nitrogen, oxygen, phosphorus, sulfur, and chloride is present in large quantities. But there are also elements which are possibly, which are essential, right? You can see the red color highlights here. Most of them are first row transition metals, and one from second row transition metal, and one from the third row. If you look at the main group, boron, arsenic, bromine, they are considered as trace element, possibly essential, but certainly there are some essential elements, fluorine, selenium, and iodine, right? And you go further and analyze the main group elements, you look at this one, it's interesting. Boron is essential, not necessarily to human, but there are many boron containing compounds are used as, in the medicine as a drugs. But if you start from carbon, only one element one can consider essential for human, right? And when you go to the next one, the 15, group 15, there are two elements, nitrogen and phosphorus, and go to the next element is toxic, right? Arsenic. If you go to the next 16 group, oxygen, sulfur, selenium. So 3 elements essential. You go to tellurium, it is toxic. And go to the group 17, fluorine, chlorine, bromine, and iodine. All 4 are important, but the human body somehow opted for iodine, not fluorine or chlorine. It's interesting. And if you go from carbon group 14 to 17, you can see the diagonal, the carbon, phosphorus, selenium, and iodine, all 4 elements are essential for human life. And this is the maximum number of elements you can see diagonally in the periodic table, which are essential for human life. So I picked up a couple of elements. One is a selenium, other one is iodine, because we don't talk about carbon, nitrogen, oxygen, phosphorus, sulfur. They are bulk elements, and many biomolecules contain that. But if you go to heavier main group in the P block elements, selenium and iodine, these are the 2 elements play key role in human body. So in my talk today, I will restrict myself to these 2 elements, and particularly selenium is considered as the toxic element, but it is essential, right? That means without selenium, human cannot survive. And these are the trace elements. So the main function of selenium in biology is related to controlling the oxidative stress in human body. Oxidative stress is a hydrogen peroxide, right? Hydrogen peroxide is one of the oxidant present in human body, and that is responsible, is a necessary evil, right? Hydrogen peroxide is a necessary evil for cell signaling. Without hydrogen peroxide, cell signaling does not happen. Apoptosis, global change in gene expression, proliferation, all these are related to gene expression, signal transduction. But also it can lead to oxidative damage. Again, I said, the amount is important, right? How much is present? Hydrogen peroxide is highly reactive, but it's essential, right? And one question people ask, when we drop an iron rod or iron chain in water, right? Leave it to open for some time. What we see is rusting, right? So iron, water, and oxygen is responsible for rusting. And one fundamental question we can ask, although human body stores 4 to 5 grams of iron, why there is no rusting takes place in the human body, right? And rusting does take place in diseases. For example, Alzheimer's disease, Parkinson's disease. Many diseases associated with reactive oxygen species originates from these metal ions. So iron in biology is tightly regulated, but still it can cause problems. So in today's talk, I'm going to talk about certain enzymes using main group elements, particularly selenium. And this is an enzyme that controls the hydrogen peroxide level, one of the enzymes that control hydrogen peroxide level. And this is named glutathione peroxidase. And the people work on selenium compounds, they definitely know about this enzyme, glutathione peroxidase, one of the 25 selenoproteins in human body that plays a key role. And this controls the hydrogen peroxide level and keep below the toxic threshold. If you see this reaction, organic peroxides or hydrogen peroxide is converted to water or alcohol by this enzyme using glutathione as the cofactor. And glutathione is a tripeptide present in large amount in our blood. It's a tripeptide. So this enzyme uses this cofactor to mediate this reaction. Very unusual reaction because there is no reactive oxygen species generated. It's converted cleanly to water. How this enzyme is able to achieve this is because it uses selenium in the active site. And this is called selenocysteine. And those who are working with the biological aspects know that selenocysteine is considered as the 21st amino acid, right? We know normal 20 amino acids which are genetically coded. They are used to make proteins, but this is called 21st amino acid. Incorporated into protein, very unusual pathway. I'm not going to describe about how selenocysteine is incorporated into proteins, but let us look at the reactivity. The main difference lies at the pKa of selenol group in selenocysteine. You can see the pKa of a selenol group in selenocysteine is 5.2. That's much lower than the pKa of a thiol group in cysteine and the pKa of 13 for serine in the same in the proteins. So just to one atom change, oxygen to sulfur to selenium, all three amino acids naturally exist, and you can see the change in the pKa. So therefore, a selenocysteine confers a dramatic catalytic advantage in this protein, and that's why nature took all the trouble to introduce selenium to the active site of these enzymes. And chemists tried to mimic the function of these enzymes. So to understand the structure and function, one of such compound I would like to describe next few minutes is epsilon, right? And epsilon is a very simple cyclic selenium compound, which was reported. It's a long history for how this was discovered. Reported in '84 by two independent groups from Germany. And this is one of the key selenium compound. Anybody who is doing selenium biology will know epsilon, right? Epsilon's biological activity. This acts as antioxidant, anti-inflammatory, anti-atherosclerotic, and anti-thrombotic agents. So the chemistry and the molecular design played a key role with this enzyme, with this compound, which is essentially non-toxic. When we say selenium compounds are toxic, and this is an example where we have completely non-toxic. And I will tell you why. The selenium deficiency is detrimental to normal growth and development in mammals. And a narrow range of chemopreventive, chemotherapeutic, and acute toxic dose level are defined. The most toxic selenium compound is sodium selenite. But people who have selenium deficiency have thyroid problems and gene expression problems, so protein folding problems. So they are generally given Brazil nuts. Brazil nuts have about 8 to 83 microgram of selenium per gram of the nuts. The most, the Brazil nuts have the highest amount of selenium. It is given as a treatment for selenium deficiency. So when we started the work on epsilon to understand why epsilon is in clinical trial, right? What is the fundamental chemistry that plays a role in epsilon being in the clinical trial, right? And when we compare the sulfur with selenium, again, one atom change, the sulfur analog of selenium, which is called F-sulfur, is biologically inactive. But if you substitute the sulfur with the selenium, it's highly active and it controls the reactive oxygen species level in mammalian cells. And the first study we undertook was to understand the chemical mechanism of epsilon. And it took several years for us to come to this mechanism. I'm not explaining them in detail, but the ring opening of the selenium nitrogen bond is important. By thiol, it produces a selenyl sulfide, then a disproportionation reactions leading to the disulfide and diselenide formation. And then this undergo further reactions with the hydrogen peroxide. This is how the hydrogen peroxide is reduced to water in the presence of a thiol. We can use glutathione or any aromatic thiols. This reaction still works. So several papers we published, and I'm not going to the details of that, but only one point I would like to bring out here is that we found that why epsilon is, the toxicity of epsilon is very low, right? And we found that the reversible cyclization, that means it goes to open chain like this, selenosulfide, diselenide, selenic acid, but finally, all of them come to the cyclic compound, cyclic seleninamide. Okay, and that we correlated with an enzyme called PTP1B. It's a protein tyrosine phosphatases. And this is an enzyme that removes phosphate group from tyrosyl phosphate and controls the redox regulations in human body. And we found there is a similarities between the cyclized compound and the cyclized enzyme. So this was two papers in Nature in 2003 talked about how important this cyclization. And this is the only example even today where a cyclic sulfinamide has been identified in a protein. And so far, no selenilamide has been identified in protein, but at least in small molecules, we were able to show that the reversible cyclization, or reversible inactivation pathway, and that protect the selenium moiety from oxidation. So the stability of the carbon selenium bond, when we talk about toxicity of selenium compound, how stable they are in biological systems. So the carbon-selenium bond in epsilon is very, very stable, and that is responsible for the low toxicity. Why it's very stable? Because of the reversible cyclization pathway. And after that, we developed many small molecule-based glutathione peroxidase functional mimetics, which include epsilon analogs and tertiary amide-based compounds, secondary amide-based compounds, secondary amine-based compound, tertiary amine with the methoxy group here, and then a tertiary amine group without the methoxy group. So all this, we did structure activity correlations. I'm going to discuss only a little bit about that. How important to fine balance the chemical reactivity, biological activity, and the toxicity to be able to use these compounds as the therapeutics, right? And this is a simple synthetic routes. What we did, compared to epsilon, we removed the carbonyl group here by putting just the CH2 group. And then we put a methoxy group here because we wanted to force this cyclization. As I mentioned in the previous slide, the cyclization is important. That prevents the selenium moiety from elimination, so it becomes less toxic in the body. So for that, we wanted to put a methoxy group which forces the selenium to form the cycle. Otherwise, we do not have a carbonyl group to form the cycle. And this helped us to come to this compound, which actually worked, very nicely in mammalian cells. And this is the catalytic mechanism. The first step is the reaction with the hydrogen peroxide to produce a selenoxide. And then you can open up the selenium nitrogen bond here to get the selenol that reacts with the hydrogen peroxide to produce selenic acid. With the elimination of water, it can go to the cycle again. So this is the key finding of our study, is that don't leave it as an open chain. Bring it back to the cyclized compounds at the end of the catalytic cycle. That brings down the toxicity, and also it maintains the half-life of these compounds in biological systems. And we studied that in human cell lines, and we showed that, in fact, this functionally mimic the enzyme in the cells. You can see with the hydrogen peroxide, an enhancement in the fluorescence due to high amount of reactive oxygen species. And then by treating with our compound, you can see that it became normal, right? The untreated cells, you can see the level of hydrogen peroxide has become normal, right? And this gave indication that these compounds, in fact, get into the cells and function like glutathione peroxidase by using glutathione as the cofactor. So this functionally mimic these enzymes. So what we can do when it functionally mimic the enzymes, what type of diseases that one can address? One of them we try to address is the DNA damage, because DNA damage is caused by hydrogen peroxide, highly reactive molecule in human body. Although for many years, people did not believe that hydrogen peroxide can exist in human body, but now it is clear that hydrogen peroxide is a signaling molecule, and it's a messenger, and is important, right? Hundreds of reactions are basically controlled by the level of hydrogen peroxide. And two types of DNA damage can happen: single strand break and double strand break. And double strand break DNA is difficult to repair compared to the single strand, because of the complementary base pairs are lost. But still, we see that these compounds can prevent the single strand break and double strand break DNA damage in mammalian cells. And what we have shown here, why is this different? When we bring out a new compound, selenium compound, the questions that come from referees, how good is this compound compared to epsilon? So always we compare that with epsilon, but we were able to bring up, the differences just by removing the carbonyl group. What are the changes that you can achieve in the cells? One of them is unexpected complications with epsilon, right? That we reported a long time back. When we have a selenium-sulfur bond, there are two possibilities that incoming thiol can do, right? One is that attack at selenium, other one is attack at sulfur, right? For glutathione peroxidase enzyme, for the enzyme to be active, the attack should happen at the sulfur, not at the selenium. But all small molecules, the attack happens at the selenium, because selenium is more electrophilic than the sulfur. So therefore, the incoming nucleophile always attack at the selenium. This this is a major challenge in designing a mimetic for glutathione peroxidase. And we have done a lot of DFT calculations, substituents, and then found that this type of compounds are not good as an enzyme mimetic, but they are good for inhibiting an enzyme by forming a covalent linkage with the sulfur, right? That's what these studies, for example, the proteins have cysteine residues, the free thiol groups, can be targeted by epsilon to block that. And that's what we have shown in the case of glutathione reductase. A covalent linkage happens between the epsilon and the cysteine residues, which inhibit the enzyme. So what we have shown, this work actually a lot of attention, it got a lot of attention because we are saying that epsilon is bad as glutathione peroxidase mimetic when thousands of papers says epsilon is a good GPX mimetic. And we proved that why it's bad, because it inhibits glutathione reductase, which recycles the oxidized glutathione. And it forms a covalent linkage. And this has been confirmed by mass spectral studies. But this can also be useful in a system where you want to block the cysteine residues. One of them happened recently, right? This is one of some of the news articles you may come across. The human trial suggests rescue drug could be safer treatment for bipolar disorder, right? And epsilon, abandoned as stroke treatment, has successful first human trial as scientists aim to repurpose it as a treatment for bipolar disorder, right? Because epsilon has been tested in human and found that it is safe, and therefore epsilon has gone from identification as a potential bipolar treatment to human trial in a less than 2 years, incredibly fast for any drug discovery efforts, right? And this is a part of the National Institute of Health's clinical collection and a chemical library of bioavailable drug considered to be clinically safe but without proven use. And even in this case, there is no proven use, and that people used recently as a potential drug for COVID-19, because this is exactly our 2005 papers talked about. You can use epsilon to block an enzyme because there is a thiol exchange reaction, say a complication that happens. What we termed as complication is actually useful in blocking the COVID main protease. And what happens, epsilon blocks the main protease by covalently binding to the cysteine residues, forming a selenosulfide linkages. And you can see that the structure of the protease from COVID-19 virus, screening of 10,000 compounds identified epsilon as one of the 6 potential COVID-19 therapeutics. And this relies on the irreversible inhibition of the protein by epsilon. But for functionally mimic glutathione peroxidase, what we suggested was not that inhibition of an enzyme, but it's functionally mimicking the enzyme activity. So what other aspects of selenium in biology is related to thyroid hormones. And next few minutes, I will talk about these systems, and you are all familiar with the thyroid gland and the thyroid hormones, thyroxines. And in India, millions of people suffer by thyroid related disorders. And one compound which is important that has one of the main group elements, the heavier one, iodine, right? As I mentioned in the beginning, that nature left chlorine, bromine, fluorine and went to iodine, right? And iodine is not, when we look at just, the choice, one may think that why iodine? Because, it may not be soluble in water, but nature still chose that for obvious reasons, okay? And this is the frog cycle. I show this in my presentation. And we know about the metamorphosis, right? The tadpole turning into frog. And I think the kids start studying from 5th or 6th grade, right? But we do not know what is responsible for the transformation. Many of us think that there are multiple pathways, for such transformation, but only one compound that makes this transformation is thyroxine, right? If you grow the tadpole in water, which does not have iodine, the tadpole never turns into frog, right? It remains as tadpole and die. And the remarkable changes happens by the thyroid hormone thyroxine. And Kendall won Nobel Prize in 1950, who isolated thyroxine from pig thyroid gland in 1914. And the enzymes which activate, inactivate thyroxine in human body are selenoenzymes. So they contain selenocysteine in the active site. Again, the pKa plays an important role. And we were trying to, functionally mimic these enzymes with the small molecules, synthetic compounds. And we started sometime in 2000, 2001, and it took 10 years for us to get the first mimetics. And that happened because of some information about the protein structures, the sequencing. We thought, by having a naphthyl ring with the sulfur and selenium in the close proximity may help us in removing iodine, because although people say carbon iodine bond is more polarized than carbon bromine or carbon chlorine, the carbon iodine bond in thyroxine is very, very stable. So it's not just a removal of iodine by a nucleophile, because we have hundreds of nucleophiles in human body, but none of them can remove iodine. Only this enzyme containing selenocysteine in the active site can remove. And 2010, we got the first success after 10 years of work. And this is the first molecule which removes iodine from thyroxine selectively under physiologically relevant conditions. In water, 37 degrees Celsius, it selectively removes iodine from the inner ring of thyroxine to produce reverse T3, or T3 removal of iodine from the inner ring of T3 to produce T2. Physiologically relevant conditions, highly specific to inner ring deadenations. This we followed by HPLC. You can see very clean, right? No additional P. That means it is quantitative conversion of T4 to reverse T3 occurs. And a lot of structure activity correlations we have done, substituted that with sulfur, 2 sulfur, 1 sulfur, 1 selenium, 2 selenium. And you can see the reactivity change. When we have a 2 sulfur, it's not active. When you substitute one of the sulfur with the selenium, there is an increase in the activity. But if you substitute the second thiol with the selenol, you can see there is a dramatic increase in the catalytic activity. And these all we have done when nothing was known about the mechanism of the enzymes. Now, nothing about the structure of the enzymes, right? We were trying to, understand what would be the molecular mechanism for these reactions. Increase in the reactivity does not change the selectivity, whether you use this compound or highly reactive this one. Still, we see only 1 iodine removed. Whether you use a 5 equivalent or 10 equivalent of the catalyst of the compound, nothing happens, right? Only 1 iodine is removed. And that was a bit surprise. And we started looking at the molecular mechanism, and we found that halogen bonding plays an important role. Halogen bonding, as you know, is a non-covalent interactions between halogen and electron donor. And the positive potential, which is called the sigma hole, the positive potential increases along the CX axis. And when you go from fluorine to iodine, iodine forms strongest halogen bond. And this probably the reason why nature selected iodine, because iodine can form stronger halogen bond to selectively remove iodine from thyroid hormones. We did a lot of DFT calculations to show that in fact all the iodine atoms have sigma hole. And we did calculate the halogen bond energy. If you can see here, if there is only 1 selenium, it's 23.4 kilocalorie per mole. If you put an additional group here, it goes to 68, right? What happens if you put in the 8th position, which is a peri position in naphthalene ring? What happens is that initially this negatively charged selenium starts interacting with iodine through the sigma hole, forming a halogen bond. You can see the covalent bond distance, covalent bond length, CI bond length is 2.14, and the selenium iodine is 2.44 to 3.84. But the strongest halogen bond is 2.755 angstrom, 77 kilocalorie per mole. And this is one of the strongest that we could get through DFT calculations. And that happens because of the next selenium, which interacts with the selenium when it becomes electron deficient, right? And initially it both repel each other because they are negatively charged. But once this selenium forms halogen bond with this iodine, that leads to the elongation of the carbon iodine bond, because this electron goes to the sigma star antibonding orbital of the carbon iodine bond, elongating the carbon iodine bond, but that's not sufficient to cleave the carbon iodine bond. You need an additional atom which can donate electron to this one at some point during the catalysis that lead to complete cleavage of the selenium iodine bond. So finally, we proposed a mechanism where a cooperative halogen and chalcogen bonding. So this is a chalcogen bonding, selenium interactions, and this is the halogen bonding, selenium iodine interactions. So the lone pair interacts with the sigma star antibonding orbital of carbon iodine bond, elongating it in the beginning. When this becomes electron deficient, the second selenium starts interacting with that through chalcogen bond that further strengthen the halogen bond, leading to the complete cleavage of the carbon iodine bond. So this was the mechanism we proposed for the selective deiodination of thyroid hormones by the selenium containing enzymes. So we were curious to know why nature stopped at selenium, why not tellurium, right? You go down the 16 group element, oxygen, sulfur, selenium, and tellurium. So we prepared the compound with tellurium, like, you know, 1 sulfur, 1 tellurium, or 1 selenium and tellurium. And we repeated the experiments with thyroxine. And the HPLC, you see here, it's not as clean as the previous one, multiple peaks, right? We isolated all these compounds and characterized. What we found was interesting, right? T4 undergo inner ring deadenation to reverse T3, and outer ring deadenation to T3, and these two undergo outer ring inner ring to T2, then T1, then T0, right? And all 4 iodines are removed by the tellurium compound. So by now the selectivity is lost, and that's probably the reason, you know, selenium is sufficient. You go down, there is no selectivity. The nature cannot control the selectivity. It's too high to be, you know, selective. And this gave some clue that you can use under mild condition to remove halogen atoms. One of the other examples that we studied was halogenated nucleosides, because the DNA damage happens if halogenation takes place on DNA, right? Because they can, by irradiations, they lead to strand break, cleavage. What we did, we took an iodinated nucleotide and the brominated one. We found that the bromine one undergo Michaelis addition elimination pathway, and the iodine one undergo halogen bond. These X-ray structures which clearly shows that there is a halogen bonding between the lone pair of selenium and the sigma hole of iodine. So what we are thinking, this could be a gentle method to actually remove halogen atom from the repaired, from the damaged DNA. And we are looking at halogenated DNA and nucleosides, long oligos, for example, and use these compounds to remove halogen atoms selectively. So with that, I stop here. I thank the group members who have done a lot of work in this area. I thank the funding agencies, CRB, and private funding agencies who support our work, and our collaborators. And finally, I thank you all for your kind attention.
Oh, thank you, Professor Mukesh, for an excellent talk, particularly looking at the main group elements in life systems. It was very interesting. I'm sure there'll be a couple of questions many people may be eager to ask you. So it's open for discussion now. Anybody having any questions for Professor Mukesh? So,
any questions?
Any questions from the audience? Okay, I have a small question. Mukesh, it was very interesting to show that you were able to rationalize the selenium-selenium interaction. So was there any spectroscopic method to identify that, or is it just a mechanism that has been proposed as of now?
No, see, we have done DFT calculations, and also selenium-77 NMR can be used to understand the chalcogen bond, also the halogen bond.
I see. So the chemical shift for the 77 selenium decreases or increases, something happens like that, or?
Yeah. So when there is an electron, decrease in the electron density, it goes to more downfield. That very significant in selenium NMR, given that long range, right? It goes from -2000 to +3000.
Yes.
Right?
Yes.
So it's easy to detect that by selenium NMR.
Oh, that's very interesting indeed. So, are there any questions from the audience? So, seems like there are no questions. So, I thank Professor Mukesh for this excellent talk on the selenium chemistry, especially at the interface of inorganic chemistry and life systems. It was fantastic. Thank you. And yeah, and I thank the organizers, Professor Krishnan and Professor Sharanappa, for giving this opportunity for me to chair this session. And now I hand over the power to the organizers for the content. Thank you.
Thank you, Anand, for sharing this session. And also, we would like to thank Professor Mukesh for his excellent presentation. Okay, so we are done with the conference. Almost we are done. So now we are going to kind of announce the winners for the poster presentation. And RSC and ACS are very generous to kind of support 5 poster awards and 6 poster awards respectively. RSC is generous to support 5 poster awards, and ACS is giving 6 poster awards. And we had a kind of a jury from University of Hyderabad, Professor Muralidharan, and IIT Hyderabad, Prabhu, and from IISER Pune, Momita. So the jury decided to give this awards, and on behalf of the jury, I request Professor Muralidharan to announce the awards.
Yeah, thank you, Professor Krishnan. All participants, mainly the students, we selected the 11 posters as is mentioned, but it's not like ranking 1, 2, 3. No ranking in these posters. So mostly we try to cover all areas of the chemistry and main group, special importance to main group chemistry, and also to see that how they made the slides and then how they made the presentation. Nothing to judge about the chemistry. It's just about the how they made the slides, how they made presentation. That's the thing. Okay, I just share my PPT of awards on behalf of my team of 3 people. I hope people can see it now.
Yeah. So
just let me read it. RSC posters for PP poster number 1, Aditya from IISER Bhopal. PP number 3, Arindam from IIT Madras. PP number 5, Garji Kundu from NCL Pune. PP number 19, Nilanjana Sen from IISER Pune. And PP number 29, Ranjit Misra from NISER Bhubaneswar. This is for the 5 posters award of RSC. Now it's the RSC ACS awards. ACS gives separately for independently to individual journals also. PP number 7, Jusaina. This is for IAC from IAC Bangalore for this ACS Material AU award. PP number 12, Mamta from IISER Mohali. This is for ACS Omega award. PP number 16, Muneswar from IIT Hyderabad for Organometallics award. PP number 22, Prakash Nayak from NISER Bhubaneswar Inorganic Chemistry award. The PP number 28, R. Das from IIT Roper ACS Catalysis award. And PP number 14, Preetham Maheshwar from IIT Delhi for ACS Organic and Inorganic AU award. Thank you all. This is from my side. I just leave it for 2-3 minutes.
Yeah, that's fine.
I congratulate all the students who got the award. At the same time, I also want to mention on behalf of our team of 3 people that it's not that others are not good. So this just small difference between the presentation and how you made the files and how you talk, all those things.
Okay, Murali. So now I think I request Professor Sharanappa to conclude the session. So he will give the vote of thanks. Then we will conclude the session. Okay.
Can I stop sharing this one, Krishna?
Yeah.
Yeah, I hope people noted, so I'll remove it from.
Yeah, that's fine. That's fine. Yeah, yes. Thank you, Murali.
All right. Thank you, Krishna. Yeah, audible, right? Yeah. First of all, on behalf of the local organizing committee, I thank all advisory committee members of main group Molecules to Materials who allowed us to host the second MMM2 International Conference at NICER, Bhubaneswar. We are very much interested in hosting this conference offline. However, due to COVID restrictions, we forced ourselves to go online. We will meet each other on some other occasions in person to interact better. However, on behalf of the organizing committee, I warmly welcome all participants to visit NICER, Bhubaneswar in the coming days. I would like to thank Professor Sudhakar Panda, Director NICER, Bhubaneswar, for his opening remarks on MMM2. I would like to thank Professor V. Chandrasekhar, Director TFR Hyderabad, for welcoming all participants and setting the event's background. I thank all plenary speakers and other invited speakers who accepted our invitation. More importantly, I thank them for their excellent talks on main group molecules to materials. We witnessed all 3 days, starting from the spectacular magnesium on chemistry by Professor Cameron Jones to the last one on the main group elements for life, just delivered by Professor Mugesh. We truly enjoyed all lectures. Once again, thank you all speakers. I thank all professors who chaired the sessions. I thank all the students who put in their efforts and delivered poster presentations. I thank RSC and ACS for sponsoring this conference by giving our students the best poster presentation awards. I congratulate all winners, and also I thank all jury members. I take this opportunity to thank Professor Himanshu S. Biswal, Chairperson, School of Chemical Sciences, NICER, and all faculty colleagues of SCS for their support. I thank Professor B.L. Bhargava for his kind help. I thank all the computer section and SCS staff members who helped us to conduct this event hassle-free. I thank all student volunteers, particularly Prakash, Sayantan, Adya, Mahapatra, and Nabeen. If I miss anyone to acknowledge, please excuse me. Although it was a virtual conference, the take-home message is loud and clear that the main group chemistry is flourishing rapidly around the globe. Finally, thank you all for making this event so successful. Now, I will hand over to Professor Prabhu Shankar, IIT Hyderabad. Thank you all.
The next conference will be held at Hyderabad. So I request Prabhu to give a maybe 5 minutes or 2 minutes presentation regarding the Hyderabad, IIT Hyderabad.
Hope my slide is visible. Oh, sorry.
Yeah.
Wait a minute.
It's fine, yeah.
Oh, yeah, it's fine. Yeah, go ahead.
Okay,
Yeah,
right.
if it starts
Perfect.
speaking, yeah.
Yes. There are. Yeah, this is perfectly fine. Okay. Very good evening and very good morning. This is Prabhu, faculty from IIT Hyderabad. I'm here to speak on behalf of IIT Hyderabad and University of Hyderabad. So I must sincerely thank the committee of MMM for kindly accepting our request to conduct this conference here in Hyderabad. It will be organized jointly by University of Hyderabad as well as IIT Hyderabad. I welcome you all formally I welcome you all to the MMM3 conference here in Hyderabad. So the Hyderabad is actually located here. The first conference was held in IISc Bangalore, 2018. The second one is happening now in Nizar, Bhubaneswar, and we just concluded the conference. Right. The third one is going to be here in Hyderabad. I must thank my colleagues for supporting me to organize this conference here in Hyderabad. So Hyderabad is actually is packed with several premier academic institutes. To name few: University of Hyderabad, IIT Hyderabad, and TFR, CCMB, Osmania University, IICT, or within the city limit. Okay, and moreover, the Hyderabad climate is very pleasant, particularly in December. The fourth largest city in India, and city area is about 650 square kilometers. Population is about 10 million. And we are very well connected with the public transport facilities. And Hyderabad Airport is one of the best airport in India. So we will not have any issue for your travel. Historically, Hyderabad is also very popular. For instance, the first Nobel Prize was awarded to Sir Ronald Rose, who worked in Osmania University on malaria-related disease. And this is his original, of course, observation notebook. And you can also visit his museum in Osmania University, which is also maintained very well. Though Hyderabad has a classic history, it is also popular for IT, information technology, palaces, and pharma industries. By the way, formerly the Kohinoor diamond traveled all the way to the world from Golconda Fort, which is located not far from University of Hyderabad and IIT Hyderabad. I'm sure you will also have a good time to visit those places when you visit here for the conference. And certainly it's a nice place, okay, with plenty of opportunities. I'm sure this is an iconic statue which is located in high-tech city, which itself speaks a lot. We'll update you soon. We will be in touch with you, and see you at Hyderabad. And thank you very much.
So on behalf of University of Hyderabad, I also extend warm welcome to all of you to participate in MMM3 when we are conducting along with the IIT Hyderabad.
Okay, so once again, thank you all. If anybody want to share anything regarding the conference, you can share.
So hello, this is Adi from Barampur.
Yeah.
So Prabhu, actually, when is it going to be? 2022, 2023?
Adi, we will be discussing with the committee and
okay.
Let you know soon.
Right. Thank you so much.
Yeah, thank you very much, Adi.
Let's congratulate both Krishnan and Sharanappa. They done a commendable job given the constraints, whatever they had and what we have been going through. And I also appreciate the optimism of Prabhu that he is talking about the travel and other things. I think so. I like the optimism. I think he almost, I think, kind of decided that it's going to be a physical conference. I also hope it is that way. So thank you guys. I think the younger main group chemists, I think, is the time for you guys to really step up the next several decades of main group chemistry. I thoroughly enjoyed the conference, although in between I missed a few lectures. But good thing is these guys also have put it on the YouTube. I think you can go back and see the links are active, at least as of now. I request both Krishnan and Sharanappa not to take it off, at least for a few days. Whoever has missed this some lectures, I want to go back. And then, in fact, I watched VC's lectures and Moder's lecture and all only that same night, because the day I was caught in another institute meeting. So thank you all. I think we really enjoyed this last 3 days. Thank you.
Thank you, sir.
Okay, Muruga, well, I think it will be 99% offline only. I should say that 99% it will be.
I really want to, I also like to travel. How long will be sitting in your office and looking at the screen and speaking? You want to see physically people and then talk to them,
Yes, I want to see you also.
I know.
Yeah.
Thanks, KCK. Thanks.
Okay then. Yeah.
Okay, thank you, sir. Yeah, thank you, everyone.
Take care. I didn't switch on my camera. I've been taking see, this is another thing, switching off the mic and camera switching on. The synchronization is another big job, Okay, take care, all of you. Stay safe.
Thank you very much, sir.
Very soon, hopefully, the pandemic is behind us, not in front of us. Bye. Yeah.
Thank you very much.
Happy holidays, everyone.
Thank you.
Thank you, Krishna. Congratulations to both of you, Swarnappa and Krishna.
Thank you, Murali.
Thank you, Krishnan. Swarnappa, thank you.
Thank you,
Good job.
Thank
Well done.
Bye to all of you.
KCK is showing both the hands up.
Yeah.
Yeah.
Okay.
Bye.
Bye-bye.
Okay, sir. Thank you very much.
Bye. Bye, Tilagar.
Thank you.